Good morning, everyone. How are you? So let's start. I'm Tom. I work for Semiotic Labs, and today I'll have the pleasure to present you our work on reinforcement learning in query pricing in the graph. So first, let me start with the outline. I will tell a few words about Semiotic, what we are doing. Then I will introduce what's really we are doing in this area, automated price discovery. I will formulate the problem. I will add a few words up when it comes to modeling, how we model that problem. Then I'll briefly went through reinforcement learning basics, let's say, just a refresher for those ones of you who know or maybe do not know reinforcement learning. Then agent-based modeling is the core of that talk, and I will show how we're using that for testing system properties and for testing, different behaviors when it comes to using single and multi-agent setups. And then I will show that actually we deploy that solution in production, what are the results, and finish with a small summary. All right, so let's start. So first, Semiotic. Semiotic Labs was founded in 2020 by AI and cryptography researchers. We are focusing on applied research, and we are one of the core devs of the graph protocol. Also, we are developers of Oros, the optimal text aggregator. Actually, the lead of that product is giving a talk at the very moment on a different stage. So bad luck. Okay, so our expertise, we combine cryptography with AI. That's our core expertise, and of course there's software engineering involved. And we focus mostly on building infrastructure. We focus on crypto economics. Today's talk is actually focusing on this, on crypto economics. All right, so what's the scenario? So the scenario in here is that, I don't know which one of you know the graph actually. Who knows the graph protocol? All right. Okay, 50-50, good. So basically, in this scenario, we just focus on one part of the graph system, right, of the graph protocol. But imagine that you've got some customers that are sending queries, right? And you've got indexers that are indexing blockchain and are kind of serving those queries. So between those guys, there is an entity called the gateway, which is kind of acting as a query market, right? So depending on the price, depending on the quality of service, a given query sent by the customers would be distributed to this or that indexer. And indexers earn money by serving queries, right? So they can control the prices of the served queries. And the core idea that I'm going to talk about today is basically wanted to have dynamic pricing based on query volume received by an indexer, and we call that AutoAgora, and I will explain in a second why we are calling that AutoAgora. So this is how we model the scenario, right? It's simplified from one point of view because as you can see, there are no let's say agents in here. We get rid of the customers for the purpose of that modeling, of those simulations. Instead, we've got a traffic generator, right? Something that just says, okay, at a given time stamp, this is the query volume that needs to be served, right? We also got query distributor, so something that basically look at the bids of the agents. So the agents are putting their bids, and then depending on those bids, the queries will be distributed across those different agents. And those bits are expressed in a domain-specific language called Agora. That's why that product, we call it AutoAgora, right? Because it automates that bidding. Otherwise, the users will have to, the indexers have to basically create those price models manually, which is kind of tricky, right? All right, so some assumptions, selected assumptions, what is happening in here. So this is only about how we generate that query volume. So we've got in here, so this is basically the shape that we model. So at the x-axis there is this price, query price slash, this is a budget of a customer. That customer are saying, okay, this is how much I can pay for that query. This budget is unknown, right? That's important. Then it's not sharing that with the agents, it's not sharing that with the indexers, it's something that is setting on its own. So this is something that we want to discover, right? And the budget can move, right, from left to right, which means that if the indexer will set its price bit higher than this, well, he won't be picked, right? Also, there is some kind of like a noise. We added a noise to that volume, to that query volume. And important is to know that there's a game happening, right, in here. And the game is, so agent's goal is to maximize the revenue, but gateway's goal, and basically protocol goal, is actually quality of service, right? We want all the queries to be served, 5 nines and so on, right? So there's a game happening. All right, so if you know how we model, let's now switch gears to reinforcement learning, just one-on-one, most classical thing. So down there in reinforcement learning, we've got two main entities, agents and environments. Agents interacts with environment by executing an action. Then agents' actions change the state of the environment. Agents get reward and observations after. Oh, okay. And agent can update its policy based on the received reward. In short, that's reinforcement learning. So we're using different types of agents in our simulations. In here, I put two most important criterions. One are trainable, reinforcement learning, online learning, and the other ones are like rule-based, so there are some predefined behaviors. And also we've got this second criterion, so the agents can be stochastic or deterministic. In here, I put some simplified classification of reinforcement learning algorithms, and I highlighted the two that basically we'll be using in our simulation. So we'll be using vanilla policy gradients, and most of our agents will be using PPO. There is one important type of agents that actually we are mostly focusing, which are, we call them Gaussian bandits. So the idea that this is a trainable stochastic agent with policy that is represented with a Gaussian, and then when an agent is supposed to perform an action in something from that Gaussian, right? So imagine that there's this distribution, and when the agent is supposed to make an action, it's just sampling, right? And in this case, okay, the agent sampled 0.8, and from that blue distribution, second agent sampled 5.24, right? And why bandit? Bandit is because the agent is not building an internal model, an internal representation of the environment. All right, so going to the most important part, so testing properties with agent-based modeling. So in here, so I already kind of explained this, but in the first set of experiments, we focus on single agent simulation, just testing the properties of an agent. And this is a single Gaussian bandit with a modified PPO policy update rule. The query distributor is like a super naive, let's say, version of that. What could happen here is that we've got like just, okay, depending on the price, this is just inversely proportional. And in the first step, we've got a fixed customer budget with some noise, of course, right? And what we are checking in here is the following. We've got market conditions. We've got two criteria. For every experiment, we've got some criteria and a property that we want to test, whether the bandit is fulfilling that criterion is operating the way we want or not. In this case, the criterion is customer budget discovery. As I've highlighted before, the agents do not know the budgets, right? But so we want to discover that. So first, there will be lots of things happening, right? Because we are tracking many things there are in simulations. So let me try to, let's say, unfold that and go step by step, explaining what you will be seeing in a moment in those animations, in those videos that we captured during the experiments. So first, there are 5 plots, right, in a single video. First one is kind of the most important. So what we've got in here is that budget, right? The query volume plus customer budget. The solid red line is the agent's current policy. The dashed line is the initial policy that the agent is starting from. In the second plot from the top, this is basically query volume served by the agent at a given time step. So what happened in here is agent actually didn't serve a query, right? Didn't get any queries because he sampled somewhere in here, right? Like a few steps ago, he sampled some, like the price was too high, right? So the agent didn't get any queries. So which also is shown in here. So this is the aggregated query volume served by a given agent in red, and the blue ones shows basically how many queries were dropped, weren't served at all, right? So you can see in here there's a tiny step which actually is associated with this. Then in the next plot, we've got agents revenue and aggregated agents revenue over time, all right? So let's run our first experiment, right? So once again, what we are testing in here, what we are trying to discover is where that budget is, right? So as agent is learning, right? So first the Gaussian was super wide, right? Like it was like much wider. And once the agent, as you can see, it's sampling from time to time somewhere in here, right? Above the budget. So it's getting more and more sure that, okay, this is the max that I can get, right? That's the highest price. That's the highest bid that I can make. So as you can see, the agent is dropping some of the queries, right? But its revenue is nicely growing. All right, so first property test, right? That was the static environment. So how about dynamic environment, right? By dynamic, I mean that the customer budget can change, can vary over time, right? So in this case, we are also testing the same property, whether the customer budget can be discovered by the agent, but in more difficult market conditions, let's say, right? So once again, we are starting, agent is kind of like a converging, capturing the price, right? Which is kind of optimal, and then the price changes. So what happens is the agent is not getting any queries, right? So it's saying, okay, I don't know where am I. So it's pressed the Gaussian, and once the queries are once again captured, it moves to the left, right? So it's like, okay, I was above the budget, let me go back, right? And that is happening over time, right? So there are plenty of queries dropped, but still we are making some nice revenue, right? And we are reacting to the dynamic market. Cool. Second property, check. So in third experiment, we said, okay, so there are some subgraphs that actually have no queries at all, right? There is a moment where nobody is asking for queries, so what will happen then? So that's a different scenario. In this case, we call that the market conditions. Basically, there is no demand for your services, right? So we wonder how we should act. So it will happen in a second, right? So there will be like 3 iterations. We're recording a few of those videos, but as you can see already, there's a hint in the right-hand corner that something is not right. All right, Gaussian spread, this is great, and time set 400 because every 200 steps we're like, generated. Okay, so what just happened? There are no queries, so according to the design, the agent just said, okay, let me spread, right, so I can sample from wider distribution, but actually spread all across the price-based domain. So we said, okay, actually this is not a good behavior, right? If this is happening, then the agent can sample with the same probability, like some super small price bids, and at the same super high. Moreover, recovery from that will take a lot of time. So we said, okay, can we improve that? So we implemented something that we called graceful init pool, which basically the idea is that, okay, there's this initial distribution that the agent is starting from. This is something that the indexer will parameterize the agent when the agent is deployed. And when there are no queries, you just slowly spool towards that initial distribution, right? And when the queries will appear once again, it will get from there and once again start sampling and optimize. I'm losing from time to time the voice, I think. Okay, cool. So we passed that property. So now let's move into multi-agent simulation. So this was great. At that point, we weren't competing with anyone up till that moment, right? Now we are starting we're competing with some deterministic agents. The idea is that right now all the indexers have the Agra models that is like a fixed, right? They are not changing the models, so it can be seen as a rule-based, right? So there's like, okay, that's my bid, and I'm sticking with it no matter what, right? So this is what we are trying to model in here, competition with deterministic agents. And the property that we are testing is called discover of price bids of competitive agents, right? So we want to make sure that we also will, we can, let's say, compete with them and discover what were their bids without actually knowing them, without having that explicit information. So those 3 lines in here, actually, those are the three competitive agents with deterministic policies that they're just set. And the blue agent, in this case, is the bandit, right? And as you can see, after a while, it set up like a price just below the cheapest agents, which means that it's trying to, once again, snatch the whole market. If you'll see a number of total queries, right, you can clearly see a difference, right? That agent is dominating, right? So I will say, okay, this is nice. Check. Cool. So how about stochastic agents? Similar experiments. We also want to discover the price bids of other agents, but their policies are stochastic. So we model them in a similar way as Gaussian distributions, right? But they do not change, right? So we observe similar behavior. This is great, right? So the agent our agent, right, our bandit moves somewhere in here, and of course it's sampling, you know, the red agent, stochastic heuristic agent is also sampling from that distribution, so it's changing. But as we can see, the agent kind of moved slightly below and trying once again to capture the market, right? All right, great. I think we checked that property. Awesome. So how about if we'll right now compete with, like, make a competition where we've got plenty of those bandits deployed. And we hope that actually this is that's the most interesting case, right? Because we want AutoAgora to be run by all the indexers in the graph ecosystem. So same property, slightly different market conditions. All right, so what is happening in here? Sadly, it's not good. It's not good. So the agents are acting actually as designed, but as you can see, they're like fighting, moving to the left-hand side, which means that they're lowering their prices all the time, right? And as you can see in here, oh, you can see the labels, but this is the revenue that they're getting, right, at a given time step. Basically, it's converging to zero, which means that after a while, the agents will be basically serving for free, right? And so that's not a good situation for the indexers, right? Because in here we're not even modeling we are modeling the revenue, we are not modeling the costs, right? So at that point, agents will be, well, indexers will be actually, well, paying for that instead of making money. All right, so we call this phenomenon or this outcome race to the bottom, and we run many simulations. We discuss that a lot, and actually we realized that, well, this is the expected behavior, right, in this setup. So we've got some agents that are basically trying to snatch the market, right, and they're purely driven by the query volume, right. So if this is the case, and the environment just naively distributes, you know, the queries based on the price bit, race to the bottom is the expected outcome, right? So it can be addressed in many ways, but we look at the graph protocol, what are the features, right? And down there, and what are the assumptions? So one assumption is that all the indexers should have freedom with their pricing, right? There should be any limitations to that if they want to serve queries that are super expensive or super cheap, it's okay. And all the indexers should be able to make any profit. So the conclusion was that actually is the gateway, right? That the thing that controls the market should implement this kind of anti-dominant policy. And so happened, it does. It already does. So in our next step, what we did, we wrapped the existing ISA, right? ISA's indexer selection algorithm is one of the components of the gateway, right? So we just wrapped it in here, and using the simulation, we are once again testing the same conditions, right? Competing, you know, many Gaussian bandits competing with each other, and the property, okay, can we discover each other's prices and maximize our profits? So the outcome is totally different, right? By changing the way the queries are distributed, actually we reach kind of like a consensus, right? So all the agents are discovering the market, right? What's the market? At the same, gateway is looking, the ISA is looking at their quality of service, at their prices, and trying to kind of like feed everyone, right? Not just, okay, you're the winner, you're snatching all the queries, right? So this is really nice. So please note that the gateway also leaves some kind of like a budget, right? That it's designed in such a way that actually it's not enabling the agents to consume all the budget, right? So the budget is, there is a portion that is left to the let's say to the customer. Okay, so we run some more simulations. Of course, it's like, okay, free. Can we run that with 10, 20 agents, right? Will that still work? It seems, yes, it does. So we are testing the same properties, right? We are just a little bit changing the market conditions, right? This is looking really good. If you look at the query served and the revenue, it's like all the agents are, you know, are making money, which is the desired behavior, right? And they're rediscovering the market. Cool. So what we also did, we wanted to see whether, okay, so how about different initial conditions, right? So we are assuming that different indexers said, okay, that's my mean price, that's my variance. I want to maybe move a bit more expensive or less expensive at the beginning. We wanted to see whether the system will kind of converge to that equilibrium. And it seems that this is really happening, right? So disregarding the initial conditions, this is good. We also run some additional experiments with weaker and stronger policy updates. So this one is our modified PPO agent. As you can see, it's much faster than Okay, the red agent is the vanilla policy gradients, like very elementary policy, very elementary update rule. And the other one is just pure PPO, right? So our agent is kind of like dominating, and it's kind of interesting to observe that it's serving less queries, right? The blue or cyan line is clearly below, and this is the number of queries that are served, but it's making bigger revenue, right? So in short, it's making less work for more money. So policy really matters, right? All right, so having those results, we are quite happy with those. We said, okay, so can we deploy that in production and actually test our solution, on a battlefield? So once again, there are many things to unfold in here. So let me try to focus on one thing at a time, right? So first, this is the mean. So this is kind of where the Gaussian is on that x-axis, right? So what happens is that the initial value was too high, so the mean was going down first, but then steadily it was going up, up, up. Good, so it was moving to the right. At the same time, variance was steadily going down, which means that the Gaussian was more and more narrower, which means that the agents were like, okay, I think I'm there, I'm good, right? I'm more confident that I should sample from that narrower, smaller distribution. So the outcome is that the reward goes up. Maybe you cannot see it in here like super nicely, but that's the revenue, right? That's the total revenue, and you can clearly see that it's going up. There's this tendency, right? So we deployed that. The results were great. So I think we are, well, this is the moment where I should start telling, okay, if you're an indexer, please go ahead. There's a repository to download, play with it, and there are some additional materials. Okay, but actually in a second. Okay, so let me first summarize. So agent-based modeling for crypto economics, that was the core of that talk. In here we focus on the dynamic pricing for applied to the graph protocol, to automated price discovery, and we use reinforcement learning and multi-agent simulation, multi-agent modeling for revenue maximization. So we can show how to use that for kind of testing the properties of the protocol, right? We came with that framework that, okay, those are the market conditions, those are the properties, and systematically started test, right? Our agents, our solutions against those. And finally, we have deployed Autogera in production and have shown that actually it makes sense. So future works, of course, better policy, better updates, better policies, agents with multiple rewards, so taking quality of service into account. We are not doing that right now. We are just looking at the query volume. Modeling and putting consumer agents into play, right? So that right-hand side that we simplified, actually putting that back in the simulation, it will give us some more insight in what is happening, right? So that's kind of that will give us simulator with higher fidelity, and kind of redesigning the game, right? So in this case, there was no information. The agents were like acting totally independently. The question is, if you redesign the game, redesign a little bit the graph protocol, would that kind of perfect information will help, right? Here are some additional resources. So my friend Alexis, he wrote this blog post which describes more the technical side of deploying Autogera in production. He also gave a talk around this, about this during the last Hack episode in June, I think. So there's a recording on YouTube. And of course, this is open source. So I encourage you, go ahead, play with it, right? All those visualizations are there. Basically, you can reproduce that and try to deploy your Autogera in production, right? Finally, I wanted to highlight some of the other works that Semiotic is doing. So there's talk actually that's happening right now that our friend Matt is giving. He's the product and research lead of Oros. He's giving it right now. So that's said. And Sevi is giving a talk today about our work and let's say our trip to the Snarks world, and we are focusing on this is more like cryptography. We are focusing on verifiable payments for the graph protocol as well. So if you're interested in those topics, please come to us. We've got plenty of positions open. If you're interested, please go ahead. Thank you for your attention. Excuse me, there's a gentleman who wants to be back.
Hello, and thank you for the talk. I was wondering if the customer has a very, very low budget, will you try to match it and make a loss, or will you shut down?
That's a great question. Actually, I wasn't showing this in here, right? Because it's tricky. Like I said, the goal of Graph is to have 5 nines. So right now we are working with the guys that are, implementing the gateway, updating that a little bit, because for now, if the customer will say, okay, I want that for basically free, the gateway will still try to distribute that, right? It's not the best outcome, I would say, for the indexers, right? But we are changing that. We've got a tool right now, right? So you can think about, I was showing you that we're working, in this work, we're focusing on the agents, right? But we develop a tool that enables us to test the properties and the outcome of the whole thing, right? When there are different players in the game, including gateway. So, great question. It's a tricky, right? It's a tricky thing. What do we want to achieve? We want the indexer to make money, or we want 5 nines, right? The quality of service to be super high.
I have another question, sorry.
Yeah.
Maybe more technical. When you showed the experiments, whenever the budget of the client was going down, the spread of the Gaussian was widening, but the mean was staying the same, which means that you are still sampling to the right side where you know it's not the right price. Would it be more effective to move the Gaussian to the left as you spread it?
Mm-hmm. Yeah. So what's the question actually? Because you just repeated the behavior. That's the design behavior, right? If we overshoot with the price, then we don't know whether the reason was there were no queries or we were too expensive, right? So we spread because we want to sample from wider distribution, right? All right. If there are any additional questions, I'm here. I'll be delighted to answer your questions, but it seems that my time is up, so thank you for your attention.
Okay, cool. Hello, everyone. I am Darren Langley, and I work on Rocket Pool, which is a decentralized liquid staking protocol. So at Rocket Pool, we've spent the last 6 years building our liquid staking protocol. So today, I'm going to take you through some lessons that we've learned along the way. So in this talk, we're going to break down what is a liquid staking protocol? What are some of the design choices? What are the challenges of building a truly decentralized protocol? And then what are the opportunities? So, liquid staking. So, liquid staking is built on Ethereum's proof of stake system. A little tangent. I couldn't be more excited that Ethereum is now a proof of stake chain. And congratulations to all the researchers, core developers, and coordinators that have made it happen. It's fantastic. So when you stake, you are participating in Ethereum's proof of stake consensus. Why would you want to do that? So the most important thing is that you're contributing to the security of Ethereum. You also earn staking rewards for being a good node operator. So Ethereum has a couple of kind of barriers. Ethereum staking has a couple of barriers. First of all, you need technical experience to run like a validating node. You also need a fixed 32 ETH per validator. The staked ETH is actually kind of naturally illiquid. It exists on the Beacon chain earning rewards, but you can't really use it for anything else, which is by design, but most of the 32 ETH that you stake is not actually at risk, except under the kind of most dire of consequences or situations. Currently, it's also a one-way thing, so withdrawals are coming soon, but at the moment, you're staking and that's it. So, the rewards from staking ETH come in two juicy flavors. The first one is consensus rewards, which comes from new ETH inflation. And then you get that by kind of performing your node operator duties. So that's attesting, being part of a sync committee, and proposing blocks. As I said before, withdrawals aren't available at the moment, but they will be potentially after the Shanghai hard fork. The next type of reward is the execution rewards. They come from users. So they come from priority fees, which are the non-burnt part of a transaction fee, and then potentially MEV if you're extracting MEV. That's actually available today and pretty much in real time. So how a staking protocol captures and then distributes those fees or those rewards is key to its design. So how does liquid staking work? A liquid staker deposits any amount of ETH into the protocol, and in return, they receive a liquid staking token. The ETH that they deposited gets matched with the node operator. The node operator interacts with the protocol and deposits the ETH into the Beacon chain. Node operators then earn rewards by being good node operators, and the liquid staking token accrues the value as yield. So to unstake, a liquid staker burns the liquid staking token and gets back their ETH, or actually more ETH than they put in generally. And you can either do it kind of in a primary mechanism or you can do it on a secondary market. So this is the very basic outline of how liquid staking works. But as we'll see, every step has some design choices and trade-offs to be made. So why liquid staking? So it's kind of important to know why you're doing this. What benefit does it serve? So it turns out that there are significant benefits to Ethereum as a whole. So liquid staking encourages greater participation that in turn provides greater security and decentralization. There's a little star there because it only contributes to decentralization if the validator set or the node operators are decentralized and not just one entity. Liquid staking facilitates unstaking through like a primary mechanism through the protocol itself or on a secondary market. So it reduces validator churn. It also fosters innovation and capital efficiency through the use of these liquid staking tokens in DeFi. Okay, so on this section, I want to focus on liquid token design, but there are some equally big design spaces on the node operator side, and definitely some interesting challenges on that side as well. So first thing you realize when you're designing a liquid staking token is that node operators earn rewards at different rates. They may also be penalized, and in worst case scenarios, they can be slashed. So there's a couple of ways of handling this. The first way is to have a fungible token that shares rewards and losses across the entire protocol. Or you can have a non-fungible token where rewards and losses are specific to each node operator or each validator. Then you can kind of have this hybrid of the two, although you've got to be careful you don't end up in a worst of both worlds. Each of these approaches have some different trade-offs, and you have to kind of weigh up which ones. So the next one is safety. So there is ETH backing the liquid staking token. So what mechanisms are in place to protect that collateral? Ethereum's proof of stake system is a very forgiving protocol, but it is possible to lose your stake either partially or in like the extreme cases fully. Safety mechanisms built into the protocol need to account for things like slashing protection, aligning incentives, and general risk management. So rewards. So how are rewards delivered to token holders? How does the token reflect the yield that the protocol actually is producing? So generally there are two approaches to this. There's rebasing and non-rebasing. So a rebasing token, its exchange rate is like a notional one-to-one with ETH. But the quantity increases. So the token increases in quantity over time. That's how the yield represents itself or gets delivered. With a non-rebasing token, the exchange rate increases, but the quantity is the same. Quantity stays constant. So the actual token increases in value over time, and there's definitely some kind of pros and cons of each of these. Mainly that, so with the rebasing token, it's very simple to understand. You're literally getting more of the token, but it's extremely hard to integrate. So if the quantity is changing all the time, that's not really compatible with most DeFi protocols. With a non-rebasing token, it's harder to understand, and if you go down that route, you'll spend most of your life explaining to people what a non-rebasing token is. But it is much easier to integrate. It's just a standard ERC20, and it's supported by most DeFi protocols. It actually turns out that a non-rebasing token is more tax efficient as well. So it depends on your jurisdiction, but with a rebasing token, you have like a taxable event every single day. Whereas with a non-rebasing token, you have a taxable event when you stake and when you unstake. So, liquidity. By tokenizing staked ETH, it can be traded on secondary markets such as exchanges. This provides liquidity for people to unstake their ETH. The price you pay on secondary markets is dictated by the market. So it may present a liquidity discount or potentially a liquidity premium. With large orders, there can also be slippage, and so staking protocols can offer if they can offer a primary mechanism for unstaking ETH, so that it can allow liquid staking token holders to actually swap back without the discount and without the slippage. Both of these mechanisms of unstaking kind of reduce the need for validator churn. Okay, so now you've got your token out in the wild. I mean, everyone's going crazy about it. You need to start building utility. These come in the form of integrations with other DeFi protocols. So there's kind of like a Maslow's hierarchy of DeFi integrations. It goes something like this. You integrate into wallets and explorers first, then you build up some liquidity. This is the bit that takes time, a lot of time, to build up liquidity. You need to get breadth of liquidity and depth of liquidity. That's important to kind of get to the next phases. You also need to get good liquidity on layer 2s, because you want to build up support in those ecosystems and also provide good UX for stakers. So then the next layer is oracles. So once you've got some liquidity, you can get oracles. The next one is DeFi protocols, particularly lending platforms. but also kind of options and index platforms and fixed income products and loads of things. The last one is vaults. So vaults are kind of like yield optimization platforms. They sit over top of loads of different DeFi protocols and optimize that yield. So a decentralized staking protocol is a set of smart contracts that mediates between depositors and node operators. It kind of escrows funds into the Ethereum's proof of stake system and then back again. On withdrawal, the protocol transparently distributes those funds and ensures that each party receives what they expect. In short, withdrawals are where most of the action happens. Okay, so it's at this point in the presentation that I need to give a bit of a disclaimer. The information on this slide is not final. The Capella specification is still being kind of drafted, but at this point, this is what it looks like. So after the Shanghai hard fork, hopefully, consensus rewards will be fully withdrawable or partially withdrawable. So fully withdrawn is a node operator initiated thing. So a node operator submits an exit message, they get processed by the beacon chain exit queue, they come into this withdrawable state, and then their funds are returned to a withdrawal credential. At that point, they are no longer validating. They're done as a validator. Okay, that's full exit. With partial withdrawn, you're still validating, and in fact, this is like an automatic and ongoing process. So this essentially skims the rewards off the top. So you have 32 ETH is your kind of initial deposit, and then anything else you make on top of that will be kind of continually skimmed and sent to your withdrawal credential automatically by the beacon chain and the consensus clients. So withdrawal credentials are a key element of the Ethereum spec, and they come in like two types. There's a 0x0, which is this BLS signature credential, and 0x01, which is an Ethereum address that receives the withdrawn funds. So most credentials in use today are 0x0, and that's because they were introduced first, and then much later 0x01 came ahead. So in the current plan, 0x0 credentials will need to be converted into a 0x01 to allow you to withdraw. And there'll be like this special kind of migration process that'll facilitate that. So 0x01 is important because it facilitates the development of these non-custodial staking protocols. Essentially because the 0x01 address can be a smart contract. And so that smart contract can take custody of funds, it can deposit them into the beacon chain, into the deposit contract, and then when it withdraws, it can then distribute the funds to all the parties. So building a decentralized staking protocol is easy. Not so much. There are significant challenges to developing a truly decentralized staking protocol. First of all, permissionless. Being an open and public piece of infrastructure is key to a protocol's success. And it's also important for its alignment with Ethereum. Being permissionless is a noble pursuit, and it's critical for Ethereum for retaining its credible neutrality. So being permissionless subsequently leads to trustless designs, which I believe are much more resilient in the long term. Like Ethereum itself, decentralized staking protocols have to rely on a combination of cryptography and cryptoeconomics to balance incentives and penalties, ensuring that the participants have aligned interests. But it is challenging. But personally, this is what makes it interesting work. So scaling. Being a competitive market participant is important to ensure that Ethereum remains decentralized. Scaling a decentralized staking protocol is much harder than scaling a centralized provider. The two aren't even really comparable. A decentralized staking protocol has to rely on ingenuity to scale, but never lose sight of its kind of core value. A decentralized staking protocol is actually a community of node operators who are passionate about securing Ethereum. Scaling is certainly a challenge, but it is one that can be overcome. So reliance on oracles. So semi-trusted oracles are essential for decentralized staking protocols today. The consensus and execution layer are separate concepts. They've only just been merged together. So oracles are required to aggregate and report validator performance information to the protocol smart contracts. There's actually an EIP that's being considered for Shanghai, and it's EIP 4788. What it does is it adds access to the beacon chain state root to the execution layer so that smart contracts can verify proofs about the beacon chain state. This is key to reducing the role of these semi-trusted oracles in decentralized staking protocols, but it is important generally to combine those two concepts and allow innovation, particularly around validator status and finality on the execution layer. So what are the opportunities? Okay, so this might be a bit counterintuitive, but Ethereum doesn't need more stake, it needs more individual node operators. So I believe this quote is from SuperFizz, so thanks Fizz if you're watching. Decentralized staking protocols have an opportunity to redress the balance. So by lowering the collateral requirement for node operators, there are more potential node operators available. By streamlining setting up a node and running a node, it's easier to onboard new node operators. And if you lower the barrier to entry for spinning up a staking business built on top of a decentralized staking protocol, this allows a whole ecosystem of niche staking businesses to compete with large providers, more node operators. The more node operators we have, the more decentralized Ethereum is. Being a node operator is not as hard as you think. Okay, so execution reward smoothing. So execution rewards, so the ones that come from like transaction fees and potentially MEV, are extremely variable. This is because block proposers are chosen at random. So at this time, if you have like one validator, you'll receive approximately 5 proposals per year on average, but you could get 2 or you could get 10. So this variability hits small node operators hard, the hardest. As a decentralized staking protocol, there's an opportunity to provide a reward smoothing pool that participants pool their proposals to achieve a consistent return rather than this highly variable return. So a smoothing pool actually levels the playing field for small node operators. They can kind of compete with the larger node operators. This is particularly interesting when you think about MEV. MEV, you can have, on average, you can earn a decent amount from MEV, but every now and again there'll be one of these lottery blocks. The highest block I think that's recorded was 100 ETH block. That doesn't happen very often, but hence why it's a lottery block. But if you do get one of those blocks, then this is what the smoothing pool helps with. So I'm Darren Langley. I'm from Rocket Pool. You can catch me on Twitter, and that's me. Thank you very much. Yeah.
So I understand Rocket Pool nodes are collateralized. One moment.
Yeah.
Hi, my
Hey.
name is Benjamin with Rubicon.finance. I wanted to ask, I understand Rocket Pool nodes are collateralized with RPL. How do you protect against a tail risk scenario where if the price of RPL ETH is dropping, the average collateralization of the network starts to fall, and how can the protocol become robust in light of basically relying on RPL ETH price to guarantee security?
So in actual fact, so RPL is used as a backstop. So the first thing that with a Rocket Pool node, the node operator supplies 16 ETH, and the liquid stakers supply 16 ETH, and then the node operator also supplies some RPL, like it's minimum of 10%, so it's about 1.6 ETH. And but the ETH is hit first. So if they get slashed, or if they're an absolutely terrible node operator, then it's actually their ETH that gets hit first, and then RPL is used as a backstop, because you can actually lose a little bit more than 16 ETH in like the worst case scenario. Yeah.
Multi-part question.
Okay.
So first part, how hard is it to run a Rocket Pool node? Like, do you need to know Unix, or can you just run a script and it installs everything? Second part,
Okay. Yep.
how many nodes can you run on one powerful PC?
Right, cool. Okay, good question. So running a Rocket Pool node, you do need to know probably a little bit about Unix maybe. You can run it on different things. We don't necessarily support Windows, but you can run it on a Linux box. You do need to know a little bit about Linux. Spinning up a Rocket Pool node is, I think, pretty much 4 commands. And it's 4 commands, and you've spun up a validating node. So we've streamlined the process. We have this thing called a smart node stack, and it streamlines the process of actually spinning up a node. We connect everything up for you. We handle upgrades for you. It's really easy. The other part of that question was, right, that's all right. That is a hard question to answer. So terminology-wise, a node is like the box that's running it, and then you have validators. So you can have a lot. Now, whether that's a good idea or not is another matter. So what you would tend to do is you probably want to distribute across multiple nodes if you had a lot, but you can run a lot. Different clients, different consensus clients, and different execution clients have different performance profiles, but you can run a lot on. We haven't modeled it, but it's in like the hundreds. Yeah. It also depends on the box. If it's a powerful machine, then you could do that. Yeah. Cool. Yeah. All right. Awesome. Thank you very much, guys.
Thank you. So, hello everyone. Excited to be here talking today on the Patreon of Zaragoza, which is La Virgen del Pilar. And I'm Alex Viñas. I'm a marketing manager at Cow Protocol. And today I'm going to talk to you about how does Cow Protocol reduce MEV by optimizing transactions through batch auctions. I've broken down the talk into 4 topics, which is the first one, MEV, the good, the bad, and the ugly. Then what is Cow Protocol? Then the difference in the mindsets of maximization versus minimization. And lastly, where are we heading? So MEV, the good, the bad, and the ugly. Will Ethereum remain under this utopian dream of building decentralized finance for fairness for all the users? Or will the dystopian side take over? And as always, will the bigger fish eat the smaller fish? So first, let's try to define what is MEV. MEV was first coined as miner extractable value, but now has been recoined as maximal extractable value. And maximal extractable value is this hidden power that the block producers have. And what this hidden power allows them to do is the ability to arbitrarily include, exclude, or reorder any transaction in the block. Of course, this is a bit of a problem because right now with the introduction of MEV Boost, we're incentivizing the block producers to only care about the maximization of the profits and not care about like the overall healthiness of the network. Before, block producers, miners, only had the source of revenue, which was gas fees, but with the introduction of MEV Geth and also the boom of DeFi Summer, then suddenly maximal extractable value became a thing, and Ethereum kind of like turned in the wrong direction and starting hurting what makes Ethereum great, which was their users. But in reality, where does MEV come from? MEV comes from two ways, from either the execution layer and the application layer. In the execution layer, it comes from the fact that, as we just saw, that the block producers have this sort of hidden power to order the transactions in their own will. And basically, like as we all know and we've seen, data shows that they're constantly doing this. But not only that, it also comes in the application layer, because it is important to realize that the different trading mechanisms that you use when interacting in Ethereum will expose you to less or more MEV. So be careful out there choosing your trading mechanism when you're executing your trades on Ethereum. Not only that, but it also comes from the fact that we're always going to live in a world that there's going to be a difference in prices between the reality that's happening off-chain and the reality that's happening on-chain. In other words, there's always going to be latency arbitrage, kind of like this competition to get the opportunity to buy cheap in either Uniswap or whatever, and kind of sell at a higher price in a centralized exchange. And lastly, what is truly like a little bit the nonsense in here is that even though the transactions are truly atomically happening in Ethereum, the prices are not. We often see that we have blocks that have multiple transactions and they're happening atomically at the same time. But if you kind of look carefully at the data, you can see that there's a price disparity with the same token pairs and even in the same token, even in the same trading venue. This is a bit of a big issue in finance because it's very nonsense that the transactions are happening at the same time, but the prices are completely different. And now that we know the definition and we know where MEV comes from, let's see what you can do with the power of inserting transactions at your own will. So there are three main forms of attack in MEV that are well known. The first one is front running. And basically front running consists of any transaction that has any sort of value, such as like a liquidation on our arbitrage, will go from I get it to basically the block producer get it. And they do that because they have the power to insert the transaction wherever they want. But not only that, the irony is that if I send the transaction to kind of get the liquidation through the mempool, what the block producer will do will replicate the transaction, put their transaction in front of mine, and even like the ironic thing is that my transaction will also be included after, so that they can earn the gas fees that I've paid, and in the end, my transaction gets reverted. Then we have back running, that even though it's kind of notorious that people argue that back running is less harmful in the ecosystem, one can argue that still back running is harmful because it's still taking away the opportunity from someone else. And basically, this is if you're like a large hedge fund or whale or like a big trader, and you're doing like let's say $1 million trade against a single AMM, you're gonna like leave the reserve pool, the reserve prices of that AMM on balance in comparisons to the other AMMs. Of course, you're gonna do that because you know what you're doing, and that means that your first trade is gonna create kind of like an arbitrage opportunity to rebalance the other pools, and you can try to sequence the trades in a way that you are the ones that snatch that opportunity, but because you don't have the power to kind of sequence the trades in the order that you want, mainly as soon as your transactions hit the mempool, someone else is going to take that opportunity from you. And lastly, the most famous one, the sandwich attack, and the one that is most hurtful to the users. And the sandwich attacks happen because in reality, you think that you're placing a market order when you're trading on an AMM or an aggregator, but essentially what you're doing is setting a limit order that is controlled by your slippage tolerance. And this is how the block producers take advantage from you, because what they do is basically insert a transaction in front of yours that pushes the price up to your maximal slippage tolerance pain point, then insert your transaction, so it pushes the price even higher, to later on execute another transaction in the opposite direction. And what this finalizes is that the miner has been able to make profit at your cost by basically buying low and selling high at the expense of you getting a very bad price. But how damaging is MEV? Well, according to EGEN5 website, which is a website specialized in DeFi and MEV analytics, throughout the last month of September, in the last 30 days, 90% of the top 10 exploited contracts are either AMM or aggregators. Not only that, but 10 out of the 13 billions that MEV volume has moved in September have been used to perform sandwich attacks. And as we just saw, this is the most hurtful attack for the users because it gives them the worst price. And lastly, ChainSign Analytics, using the data from the Flashbots team, has estimated that since 2020, there's been a total of $1.3 billion of MEV extraction from the users. Now, why are these numbers a problem? These numbers are a problem because if Ethereum truly wants to become the world computer due to its ability to settle transactions in a decentralized, open, and atomic manner, we need to try to fix MEV. And we need to try to fix MEV because I think we all want to and believe that Ethereum will indeed become the world computer and absorb all the transaction value of the world. And then if that happens, the logical thing to say is that at the current stage of things, also MEV is going to increase. And if MEV increase, this is going to poke the regulators, and basically the regulators are going to come in and kind of try to dictate how we should operate the market. We've already seen that in several reports from the Bank of International Settlements, how they try to establish like whether front running or sandwiching is illegal activity, or even more particularly in Europe, where I'm from. We can already see this in the MiCA regulation, that the current forms of front running or sandwich attacks will be deemed illegal under the ESMA market structures. This, of course, is a problem because I think we all don't want to have the regulators to come in and dictate how the market should run, but rather we want to just build technical solutions that like address this problem so that the regulator doesn't have to step in and kind of like run the party. So, what is CAP protocol? CAP protocol is the trading mechanism that underpins, hopefully now, the famous UI, Chaos of Exchange. And it's similar to an AMM or an aggregator, but with the fundamental small difference that we add a theme batching layer on top of them that allows us to execute, that allows us to aggregate multiple trades together and execute them in a single Ethereum transaction. Not only batching allows us to do this sort of aggregation for transactions, but it also allows us to give structurally better prices via chaos, which stands for coincidence of ones. And these give better prices because if the counter opposite orders are in the same batch, we can match the user peer-to-peer, and therefore they don't need to go to the liquidity pool, and thus save on transaction costs, on liquidity provider fees, and on price impacts. Batching also allows us to be the sort of MetaDex aggregator, similar to Skyscanner. We can query all the AMMs or all the liquidity on chain, as well as all the other aggregators, so that in a sense, your kind of baseline price is always going to be the price that the AMM or the aggregator gives you. But because batching offers certain benefits, we almost always improve it. Then it also offers MEV protection because one of the key reasons for batching is that the batch executors have to guarantee the price that you get. So either you get your price or your trade is not going to go through, and thus you're not going to be faced with failed transactions. And lastly, for all the ETH maxis that we're all here, it also allows you to do gasless swaps, which basically allows you to pay the gas fees in your cell token. And you don't need to ETH actually for trading on CowSwap. So how do we actually reduce the MEV on chain through batch auctions? Well, the goal is that through batch auctions, we want to reduce the overall interactions with AMMs. And if we have to go to AMMs, then at least we're going to try to diminish the level of exposures that the trades are going to have against MEV by applying certain rules to the batch auctions. The main way to actually reduce MEVs, as we just saw, is executing coincidence of ones. And because you don't need to trade against a liquidity pool, and the trades are matched completely peer-to-peer, therefore, there is no matter in the order of those transactions because it's a pure, simple transfer between two parties, and there is nothing, like no one can get in the middle. Then second, if we have to go to the AMMs, then we try to break order dependency by having a single price per asset per batch. And basically, this is achieved because every single batch settlement that happens in Cow protocol has uniform clearing prices. And uniform clearing prices, that means that like the people that are trading the same token pairs in the same pairs are always going to get the same price, unlike what is happening right now, that we see a lot of price disparity. And this is guaranteed because the executors of the batch commit to a price vector that, regardless of the order of the trades, are always going to give the same outcome. In other words, no, the order of the factor does not alter the product. And lastly, batch auctions allows us to reaggregate fragmented liquidity via ring trades. This is something very interesting because it allows us to actually kind of match different users without the need to go through many liquidity pools. And for example, here we have a batch where we have 4 different users and where we have kind of like a coincidence of 1 and a ring trade, where the 4 different users are trading 4 different tokens, and they're all trading in the same batch, and without having to touch an AMM, because each user is kind of providing the liquidity needed for the other user, kind of like in the circle. So in the first one, it would be like in the top. Now we have DAI against Aura, and actually the liquidity for the first one that's selling DAI goes to the other one that's trying to buy USDT, and so on. And like we make a circle, no? USDC, USDT, and USDC against Aura. Now, how do we actually compete for MEV minimization? Cow Protocol outsources the settlement of these batch auctions to a competition of third-party algorithms. Whatever algorithm gives the best price improvement for the user and thus that minimizes MEV the most is the one that actually wins the right to settle the batch auction. Not only they win the right to settle the batch auction, but it also gets rewarded for doing so. Currently, right now, there are 12 different solvers competing against each other for kind of like minimizing the amount of MEV, or in other words, maximizing the value for the users. And they can be grouped into 4 different types of solvers. We will have single order solvers that basically specialize on just settling one order in a batch. Then we will have batch count dex aggregator solvers that specialize on finding this coincidence of ones amongst users. Then we will have mixed integer programming solvers, which kind of are able to settle multiple trades against like Uniswap V2 or Uniswap V3 style kind of pool. And lastly, we will have the quasi-linear solver or Quasimodo that specialize in settling trades of the batch auctions in more fancy pools like Balancer. So what are the differences between the maximization and minimization mindsets? Is really MEV protection, is all the MEV protection out there the same thing? Well, of course not. Although one can argue that, in my opinion, no, Flashbots technology and Cow Protocol technology are kind of 2 sides of the same coin. They're 2 sides of the same coin because both technologies outsource the settling of the transaction to a competition of third parties. And in that competition, the winner is the one that optimizes the bundle of transactions in the best possible way for the users. The difference here is like who is the monarch in both systems. In the case of Flashbots, no, they're trying to maximize the value for the validators and thus kind of like maximizing the extraction from the users. But in the case of Cow Protocol, we're trying to maximize the value for the users and thus minimize the value for the validators. So what are Flashbots goals and mission? Well, Flashbots is a collective group of individuals that have done a lot of work in kind of like highlighting the issues of MEV in the space and kind of educate a lot of people and make us realize what are the consequences of building systems that are prone to MEV. But from their website, you can take that their goals is divided into 3 steps. The first one is to illuminate the dark forest, and they've done so via MEV Expect or MEV Explore. And basically, this helped educate a lot of people within the Ethereum community by putting a number and seeing how hurtful MEV is. The second one is democratized extraction. Before MEV Geth or MEV Boost, the extraction was only available to a very few set of players. But now with the democratization of their tool, a lot more people can do it. And while it's good that a lot more people can actually do extraction, we need to try to realize that we're kind of democratizing a weapon that is harming the overall Ethereum users. So it's kind of like a tricky situation here. And then lastly, distribute the benefits. This is still a not very clear part or very clear how they're going to achieve it. But right now, one can say that they're redistributing the benefits to the wrong people, because the benefits right now that are coming from MEV extraction are going to the validators, which are not the ones that are creating the opportunities, because in the end, the opportunities are created by the traders. Yeah. So what are Cow Protocol's goals and missions? Well, Cow Protocol goal is to actually achieve one single price per token per batch, and we want to try to achieve that by basically executing one batch settlement per every block. But if we are to compare as well into 3 main points, we will have that the first one is protection from the dark forest, and basically we do this by executing the coincidence of ones, where the user doesn't have to go against the liquidity pool, and also through a delegating trading model execution, where the user doesn't send the transaction directly to the mempool, but rather sends it to an off-chain set of relayers that will be the ones that kind of like handle how the transaction hits the mempool. Then the second one is, if we have to go to the AMMs and if we have to go to the mempool, we try to avoid extraction by enforcing certain rules to these batch auctions. And the most important rule is the uniform clearing prices, which in the end breaks the order dependency and thus makes those trades much more or less MEV-able. And lastly, distribute the benefits. If you're trading on Cow Support Rate today, you already know this. If not, I recommend you doing so. But already today, kind of like the price improvements that these so-called solvers or searchers are able to find are given to the users instead of being kept for them. And for example, in this case, we can see the kind of like the patch in the middle that there was like 18 different trades, and on average, there was a surplus of 2.5% for each order. But to sum it up, how are they different, no? In the case of Cow Protocol technology, if we look at the key metric that evaluates the success of the technology, is the overall reduction of the exposure of MEV, versus in the case of Flashbox technology, the key metric is how much MEV is being extracted. Looking at the word democratization, no, one can argue that the Cow Protocol technology is democratizing the tools for protecting users, versus Flashbox technology that they're democratizing the tools for extracting value from the users, or from attacking the users or hurting the users. And if we are to look at how these two different technologies interact with on-chain, the goal of Cow Protocol technology is kind of reduce the amount of AMM interactions that the users have, because in the end, like AMMs are the reason that MEV exists. But in the case of Flashbots, they want to maximize the amount of MMA interactions, because these ways they can maximize the slippage tolerance from your trades and kind of extract the most value from you. And lastly, if we look at how both systems kind of like play by the rules, in the case of Cow Protocol, we see that the more money to the users, the less MEV, and the higher the chances of have for winning and the right to settle the batch. And in the case of Flashbots, the more money that goes to the validators, the less money that goes to the user, and therefore, the more MEV, the higher the chances you have of winning. So where are we heading? As I said before, not all is lost. Like, we believe in building technical solutions that can kind of address this type of problems, and we think we're on the right path to kind of like reduce all the big chunk of MEV that is happening right now on Ethereum. So what is the future of DEXs? We believe that the future of DEXs is one that focuses on fairness and cost improvement for the users, rather than just let them trade in kind of like suboptimal ways. It is one also that offers MEV protections, because as we said before, if the transaction value in Ethereum is going to increase, MEV protection is going to become more and more important. It's also one that puts the users at the center of it. No? In the end, in our system, the users are the monarchs, because they are the ones that are creating the opportunities for different price improvements. So they are the ones that should actually be rewarded for it, and not other parties in the system. And lastly, it's one that abstracts users from complicated technology. It is unrealistic to expect that everyone is going to know what is an RPC or how to add an RPC, or even stay up to date on all the different liquidity pools to trade your token, or what is the like hottest new DeFi like trading venue. And how are we going to get there? No? What does the future of finance look like? Well, the future of finance looks like one that we have a Cow batch builder, where this builder commits to have the first transaction of the block to be a Cow Protocol settlement. And this is important because if the first transaction of the block is a Cow Protocol settlement, then we're going to have uniform clearing prices in all the trades that are happening within there. And therefore, there is no MEV that can happen with the trades. Then if that's the case, and we have that first transaction, then the transactions that are going to come after are going to actually be like true intents of arbitrage from the market, and we're going to be able to like have the overall Ethereum ecosystem, in a sense, focus on the real market efficiency. Because right now, a lot of the arbitrage that's happening is toxic arbitrage, and it's not arbitrage from the market, but rather the leftovers that the MEV attackers are kind of living in there. And lastly, it would be like the combination of the utopian side of the Flashbox technology with Cow protocol. So how does this look like? Well, currently we have this scenario right now in Ethereum where we have the mempool and we have the different searchers or private order flow that submit their bundles to the builder, and then it goes to the relayer and the validator. But for us, the key is to kind of break the order and kind of transform searchers into Cow builder and put Cow protocol and Cow swap in the middle of it in a way that if we convince builders to focus on the utopian side and kind of shift their revenue mindset from hurting users to actually protecting and maximizing to the value of the users, then we're going to have a much overall better outcome within Ethereum. And will the market fix MEV? Well, the question is that if MEV maximization takes over, we will have not built the future of finance, but rather have just built the new old system, but just with new rails. So help us build the future of finance, because we're hiring for a lot of positions. And thank you very much. Questions? Excuse me.
Hello. Alex.
Sorry.
No problem. Question. So the batch auction process you're describing is one in which you have a bunch of orders from individual traders, and then a collection of solvers each submit a price vector that can satisfy all of those orders. How do you get the individual traders to commit to an order without them knowing the final price?
Well, basically, it's like they see in the way it works is that when you go to CowSwap, you sign a message with your intent to trade, and basically your baseline price is the quoted price that we give you. So from there, the solvers start working on trying to improve the price. So you're always at least at base, you're gonna get what we have showed you in the UI, and from there, if there are price improvements that the solvers can find via coincidence of one or some sort of batching, then it's going to be rewarded in the form of surplus from you. So you're going to get more. How is the course price calculated? By basically looking at the on-chain, the on-chain prices, and from there, like we discount the gas.
Okay. Here.
Sorry.
Thank you for the talk. The question is, do you have any guarantee that the individual user is going to have its trade executed in a batch?
Like the way it works is that you sign a message, and then if your prices get out of market, then the trade is not going to execute, but you're not going to get charged for a failed transaction or anything, because simply the trade doesn't execute. So in a sense, like the guarantee is that if your order is more or less within the market pricing, then within a matter of 30 seconds to 1 minute is of course going to be included.
Hi, I'm here.
Sorry.
Hi, thanks for your thought. I was just wondering, you compare FlashPulse and CowSwap, but isn't CowSwap solving for like a subset of the MEV that FlashPulse is trying to solve for? And also, how do you feel about MEV maximization with MEV rebates being equal to MEV minimization?
Can you repeat the question? Sorry, I didn't hear.
Yeah. So you compare FlashPulse and CowSwap, but how do you feel about? To me, it seems like CowSwap is solving for a subset of the MEV that FlashPulse is trying to solve for. As in, for example, you don't solve for illiquid pairs, and you only solve for MEV that goes through AMMs.
But Flashbox is not trying to solve for MEV. Flashbox is just making a tool that is making MEV extraction more accessibly common for whatever user. But in the end, the goal of their action is that the more MEV, the more I'm going to pay, and the more likely I'm going to be included. Like my bundle is more likely going to be included on the next transaction. And they do that because they're in the execution layer. And the problem is that they are able to do that because the trading mechanisms that people use, like AMMs, expose their users to MEV. But what we try to do is kind of like fix the MEV at the application layer so that then Flashbox wouldn't have like a way to extract MEV. So if like, in the end, if the solvers kind of like find the optimal prices and uniform clearing prices, the MEV that will go to the block producers is non-existent because there's no, like it doesn't matter the order of the transactions. don't know if I convince you. Thank you.
Hi, good day to y'all, buenos dias. My name is Ken Smith. I'll be talking about does it make sense to aggregate and average fee recipient rewards, commonly referred to as MEV, using a smoothing pool. And very glad to talk about a number of things. I'm with a firm of my own called NextBlock Solutions, but I'm also a rocket scientist with the Rocket Pool protocol, and most importantly, a member of the Node Operators Association. So one of the things you can do is you could download a copy of this report that was published early summer. There's a QR code here in the corner that you can grab. But this presentation will cover the highlights of that report, or at least give you a good orientation to read it. But I do encourage you to go there for more additional information that I can't cover in 24 minutes and 9 seconds here. So to begin with, let's spend just a short second talking about the taxonomy of MEV, right? You've heard a lot of talks about it. One of the first things you might be asking is, why would it make sense to aggregate rewards in a smoothing pool? This is something that kind of comes from the mining industry, right? Where the chances of you actually solving a cryptographic hash and being rewarded is so rare that it makes sense to go in collectively with other individuals to have a constant income stream. This here is a graph that shows the probability over 5 years of receiving a block proposal, right? So if you have a single validator, and sometimes I might refer to those as mini pools in rocket pool terminology, but validators, over 5 years, given 4,025 validators, we're a little bit more than that now on the blockchain, you will receive on average about 30 proposals over that 5-year period. Now again, that's just an average, right? You can see in the probability histogram, you might be unlucky and might only receive 12 proposals over that 5 years. You might also receive 50 or so, right? And it scales linearly. If you have 2 validators, you can see here that the average is going to be 60. You would think that there's no advantage to having more validators in there if each proposal was rewarded uniformly with the same amount of beacon rewards. But obviously, in addition to getting beacon rewards, you also get a chance at MEV, right? So let's just take a little bit at looking at MEV, right? You know the definition, right? I think one of the things we lose a little bit, though, is that it's viewed somewhat as a theoretical limit. It's the maximum extractable value. And I would argue, and I think a lot of the data supports, that we're not actually extracting that full amount, right? So the Flashbots team has used this term, I don't think it's quite as catchy, called rev, which is the actual amount that we're able to extract from the block, right? And there's some amount of earnings, right, that is not captured, right? It's just left on the blockchain for the next block. I'm just going to call that ullage until somebody comes up with a better name, right? There's some really great metrics coming out now, post-merge, about if we look at this rev, how much of it is actually going to the searcher, right? How much of it is going to the block builder, right? What part of it may go to the relayer? Right now, the relayers seem to be providing that as a no-fee service, right? But there's a potential they might capture some revenue from there. And most of it, from the metrics we're seeing right now, is going to the block proposer, right? That's the validator. And so I've been calling this term in my report here the proposer payment value. It's the amount paid to the validator to put those transactions into the block, okay? One of the things that we did is performed a Monte Carlo simulation looking at it pre-merge. We looked over a period of 60 days. We looked at the amount of MEV that was extracted by miners. Now, this was done in the kind of May, June time period, but MEV seems to be about pretty much stable in that time period. It's not maybe declining slightly, but pretty much in there. And it is this long-tailed distribution, okay? Most of the MEV, this line right here, this is the median value, right? So 50% of the blocks received a value that's less than 0.05 ETH in their block, right? 50% of the blocks had ETH payments and MEV payments or proposer payment values that are greater than that. The average is actually quite a bit higher than the median. And the reason for that is of this long-tail distribution. In fact, it's so much that, you know, in looking at some of these metrics, if we just look at the top 0.1%, right? Let me get it here. 30% of all the ETH values is in that top 0.1% of the blocks there, right? And it's because it's just so long-tailed here. I mean, that ends right here at 1 ETH, but it actually continues on, right? We heard earlier that, you know, some of the blocks would be, you know, near 3 digits ETH, right? Okay, adds tremendous value to it, right? So because of that long tail, right, even the top 1% have 45% of the proposer payment value in there, right? It creates these very rich ETH blocks, right, that we've been calling lottery blocks, right? And if you win a lottery block, it could be very rewarding in terms of an income stream, right? So this is why it makes sense to start aggregating them into a smoothing pool. So one of the things we did pre-merge is we started looking at, okay, I think this was originally proposed by Flashbots. There was a dev on the Rocket Pool team that actually came up with an ideal and a mechanism to implement it, Joe Kappas. And so what we did is I created a Python program, and you can get it from the GitHub, that went ahead and it went through a Monte Carlo simulation. And so just briefly what it did is it said, okay, let's figure out some time period. And that's important, right? Because the way that this works is that if you validate for an indefinite period of time, right, you all approach the average, okay? But we're not going to validate for an indefinite period of time. There's some investment, right? Maybe you start staking, you earn income, but maybe it's a 5-year, maybe it's a 10-year or 20-year. There's some limitation of time. Perhaps it's even much shorter with proposer builder separation, right? Maybe that will come in 3 years or 4 years, right? Or as we heard in the other talk, maybe there are other technologies that could prevent a lot of this MEV from occurring. So there's some finite determination. The software goes ahead and it performs a try. It grabs a validator. It makes a guesstimate about the number of proposals that it will get over that 5-year period for most of my graphs. It then, for each of those proposals, randomly assigns an amount of MEV based upon that 60-day historical period, okay? Because MEV seems to be somewhat random. We don't know when the NFTs are going to drop, when the arbitrage is going to happen, okay? It then goes ahead and does that for a validator or a set of validators that you have. It then also compares another set, like type, set A, set B. Set B is where that validator, instead of running by itself, something I call a solitarious mode, is now running as part of the smoothing pool, okay? And the size that I chose for the smoothing pool initially was about 3,000 validators that are working collectively, sharing their proposer payment values. And then it did that for the entire validating period, and it simply compared. It said, okay, would you, in this case, in this try, did the solitarious mini pool earn more income in proposer payment value than if it was in a smoothing pool, right? And so we've got some results that we could share about this. It records it, and then it repeats it a whole bunch of times. And you can set that number for anything, but you get enough power at about 1,000 tries running through this thing here. And then finally, it produces a lot of neat graphs. So let's go ahead, let's take a look at those graphs, okay? So let me walk through it with you a couple of times. And let's just start with one. We have one validator who over the course of 5 years produces on average about 60 blocks, right? And you can see here that it runs for a period of time. It gets a block and it receives a small amount of MEV. Here it proposed again and received a larger amount. And you can see as it steps up here, it's not receiving any blocks. It was never selected to be a block proposer. Here it's a block proposer and it went up, and so it just goes up every period, right? And I had the periods kind of slice in 28-day periods. And at the end of it, you can see over that 5-year period, this run of this single validator earned about 2.5 ETH in MEV, okay? We could run it again, and we could say, given that same performance, what about if it was in a group of 2,999 other validators? And so therefore, the mini pool had 3,000 validators. And we could see here that if I put both of those slides together, that it outperformed, right? It was much better to get a small constant share of a larger pool over time. Now this was just one run, right? Okay, maybe it just so happened I picked one that it outperformed it. We need to repeat that a little bit more, right? So let's look at that a little bit more here, right? So again, I said, well, try it 10 times, right? And you can see here back to the solitarious validator that maybe it only earned 2 ETH, maybe over here in this trial it earned about 6 ETH, right? Okay. There's greater variance because of just the long tail randomness of the MEV. But if it's part of a smoothing pool, you could see here, even at 10 tries of a smoothing pool, the variance is much less because now we're averaging a share over 3,000 validators, right? And when you put them together on the same chart and the same axes here, you can see that at least in this trial of 10 runs, that nine times out of 10, being in a smoothing pool, you earned more income over that 5-year period than if you had just ran independently. Only in one time, you had a very lucky solitarious mini pool that had actually outperformed the smoothing pool, right? So this is just another chart that's looking at it where I normalized if you were by yourself, and you can see that most of the runs you earned, in this case, about 3 ETH more over that 5-year period than if you had ran solitariously. That's the red line. Okay. Well, again, 10 times is not a lot. You need to start increasing that very large to get your orders of power in terms of your ability to see resolution. So here I ran it again. Now all these lines start to overlap. And it looks like from here, again, the blue lines here are the smoothing pool. And you might say, wow, look at all these here that are up here earning hundreds of ETH over the smoothing pool, right? But it's a little bit of an optical illusion, right? Because the majority of the lines are here in this very dark purple at the bottom, right? In fact, how many of those are there? We can start looking at it, right? And I'll just point to this one spot here. If you had one mini pool of your own, and you were joined a smoothing pool of only 100 other mini pools, 78% of the time in this run of 1,000 tries, 78% of the time the smoothing pool outperformed a solitarious mini pool, right? We could show the same chart here, just shown on a line here, and you could see that it will underperform in kind of a unique case when you are the smoothing pool. If you join a smoothing pool before you reach the 50% mode, right? So don't join a smoothing pool. If you have one validator, don't join until there's at least 2 or 3 validators in the pool, right? Okay. But as soon as you become the small fish in the pool, right? If you join a pool of, let's say, 3,000 mini pools and you only have 10 or 15 validators, right? You could expect about 80% of the time that smoothing pool will outperform your solitarious mini pool. So it does provide that, the kind of takeaway here is that a fractional share is going to outperform most of the time, okay? Now, another rocket scientist in Rocket Pool, Valdroff, I think, looked at the report when it was in the early phases, and he said, Ken, that was pretty interesting stuff. I love the code, but he says, I think I could show it in one graph, okay? And so he put together this graph. I got to give him the full credit. And what it shows here is it shows the probability of you earning an amount of ETH, given whether or not, and we'll just look here at the blue line, which is 1 validator, versus joining the purple line of 3,000 validators. And so this blue line, you can see that there's some probability, right, that you might even get up to 10 ETH over the 5 years, right? But most of your probability is that you are going to get less than 5 ETH, okay? Versus if you're in a smoothing pool, you're in the purple line, right? You're almost assured not to get these low values. Most of your probability is getting some value close to 5 or 6 ETH over that period of time. And then again, it becomes very unlikely that you're going to win the lottery, right? Because the pool won the lottery and you're just getting a share. It's also shown down here, lower below here, which is that if you're in the pool, right, you are nearly guaranteed to get at least 1 ETH, 2 ETH, 3 ETH, 4 ETH, 5 ETH, 6 ETH, and then it starts dropping down to almost a negative probability, right? Versus the blue line, you can see that, yes, the chances are I'm going to get much less than 5, but I give up some chance of winning the lottery, right? So it does provide, the takeaway here is that if you participate in a smoothing pool, right, you are more likely to receive larger monthly ETH rewards, okay, especially if it pays out on a monthly process, than running your own mini pools by yourself. Okay. Now, why is this important, kind of post-merge? Well, let me share a couple of things post-merge. I mentioned that Rocket Pool already has a smoothing pool for its node operators. They can opt in to it, right? You're not required to, and there's a great tool. Again, you can scan the QR code. A great tool called Rocket Scan by another rocket scientist, Peteris, that actually shows the Rocket Pool validators, and I did this last night when I was putting these slides together, and you can see what proposers, or what blocks they proposed, and if they have a little, looks like a smoothie, right, they're in the smoothing pool, okay? And you can see here, this person got pretty close to a lottery block, right? But they're in the smoothing pool, so we all benefited from it. But you can see most of them here are these just, smaller MEV amounts, and you can see what MEV relay, won that block auction in there, right? There's also another great dashboard here by Genex, another Rocket Pool member, who put together a Dune dashboard that was showing since the smoothing pool launch, which was a few days, I think, after the merge happened, so about 30 days ago or so, that, it is trending very close to our model predictions, right? We have a median of about 0.6 ETH. So if you were a solitarius, that is what you would expect in terms of your rewards. And then if you were in the smoothing pool, you can see the performance enhancement from it, right? In the smoothing pool, you get the average. If you run by yourself, you get the median. It's basically kind of how it works. And they're adding about 1.5% if you're in the smoothing pool in terms of your APR to have a validator in the smoothing pool because of MEV. They're tracking it very much like our model predictions that we can see most of the MEV are these very small amounts that occur. But you may not see it here, but I'll just kind of point. There's one around 4, one around 5. And the biggest MEV block we've got so far in the last 30 days is about 8.4 ETH. That was right after the merge. There was a very fortunate block proposal that came in and got bidded. But it models very close to our predictions, so that's good to see. Now we only have 30 days of data. It needs to go. There's a great command here in the Rocket Pool Discord, the InvestBot. It actually shows the number of Rocket Pool nodes that have opted in. It seems to be very popular with about 70% of the node operators in the network joining it. We've been told, or at least seen chance, that one of the reasons some of the larger nodes are not joining yet is they do not require yet that MEV boost be running on these things. But that is the plan, to make it that if you're in this smoothing pool, it's a MEV boost smoothing pool. But already it's performing quite well, and this is, it pays out every 30 days. This is only in the last 14 days. We're about halfway through the reward cycle. It's already generated 70 ETH among these participating 4,000 mini pools that are in there. Right. Now, obviously, this is a model that kind of showed how it works. It's an example from the Rocket Pool protocol about how a smoothing pool can work, but I actually think it's a value to other staking services, right? I can certainly see a need for solo validators to perhaps aggregate in a smoothing pool of their own. I could see other protocols begin to create their own smoothing pools. One of the interesting things is I know that the Ethereum Foundation and the research side is looking as one of the possible solutions to proposer builder separations is the establishment of a protocol including smoothing pool that redirects those MEV rewards. And so this could be an excellent model for them to look at in terms of getting data, and that was one of the reasons I wanted to present it here at Devcon, because I think it does offer some example on stuff. Last but not least, so I have time for questions, I would like to thank the Node Operators Association with their financial support that I was able to attend here and present this paper, and shout out to all those in the Rocket Pool Trading Discord that gave me a lot of support to actually submit and present this and write the paper. So with that, I'll conclude my prepared talk and open it to questions.
Hi there, thank you, great talk. Simple question, what's the right number of validators to have in a smoothing pool? At what point does the probability of rewards begin to approximate your 3,000 validators? Would you get the same effect at 30, 300?
Yeah, I think the numbers on a slide, maybe I can pull it back up here, well, maybe not. But if you look at the slide that shows it, even at a mini pool of about 100 mini pools, right? As I go back for it, you start to get it, right? Even at 3,000 and so forth, the numbers, maybe this is a better slide over here. I mean, look, you're at 78, 80%, right? Which is pretty close to it. It does not take that much to start getting those rewards. Obviously, the more you have in the pool, the less variance you get, and it becomes a very predictable stream of income. I'll wait for the mic to get back there. Well, it does. I'll add over here that, certainly if you join where you're a small part and, you can see the numbers, they start moving more. And, again, it's a Monte Carlo simulation. So if you see little variances as to why this is lighter shade and not, it's just you run it again on another 1,000, you get a slightly different picture. But it all looks this. In my report, there's a really nice one where I let it run, over the weekend and, generated a number of Monte Carlo tries.
Is there anything special about Rocket Pool that makes it only work for them, a smoothing pool, or could potentially other home stakers join the Rocket Pool smoothing pool, or could they have their own do you need oracles for it to check participation of the validators? Yeah.
Yeah, no, the math and the mechanism works regardless of the protocol, right? So just if you get enough validators together working collectively to share the rewards, the math all follows, right? Now, I understand it's actually come up a couple of times. I understand from the Rocket Pool community if they would open the Rocket Pool smoothing pool. Right now, they have it only to Rocket Pool validators that are with their protocol. But I know it's been talked about. You'll have to ask some of the dev team in the front row about what their current thoughts are. But it doesn't surprise me if others start creating similar approaches.
You mentioned that joining is voluntary, and I was wondering, of like the people that know about it, how many people actually join, would you say?
Yeah, I think my slide said that there was about 70% of the existing node operators. So a little bit of terminology here. A node operator is an individual who has a single piece of hardware, maybe, I guess it would be a single piece of hardware, and about them, 70% of them have joined, right? So out of the 1,600 node operators in Rocket Pool, just a little bit more than 1,100 have joined. We do think that from some of the other node operators, I think they are waiting for MEV extraction to be required. Like right now, I believe it's about 90% of those in the smoothing pool have MEV boost on, but 10% don't. And so you can kind of think of it if, you know, somewhat as a strain on it, right? Because they're not actually going after any MEV, but they are getting a share of the rewards. The plan in Rocket Pool is to make it mandatory as part of joining the pool. But because of the merge and the new technology on MEV and the relays, right now it's just truly an opt-in. But most of the node operators are obviously profit-seeking, and they are turning on the MEV boost. But excellent question, by the way. All right, well, I don't see any more questions, so I thank you very much for allowing me to present here at Devcon.
Not works. Okay. Hey, folks. My name is Vasily Shapovalov. I work in Lido. And what I want to talk about today is what I think will be the future of liquid staking. Really love the crowd, by the way. There's so many of you. So does it work? Yeah, okay. So a bit about us and about me, why I'm talking about this. I'm a tech lead at Lido, which is a DAO that's headquartered on Ethereum that makes liquid staking protocols, and it maintains the largest liquid staking protocol in existence, Lido on Ethereum, which has a bit more than 4 million Ether in it. Currently the number 2 DeFi protocol by TVL, and I'm co-founder tech lead, so I guess I know a couple of things about staking. So for folks who are not really familiar with the topic, liquid staking is when a staker gets transferable voucher when they lock up their stake in a staking protocol. So like it's not, it can be used in DeFi, it can be transferred, sold, bought, collateralized, etc., etc. And liquid staking is a small but growing and pretty significant in size part of staking economy. You know, like all the staking economy without 80 billions, and liquid staking protocols together are about 8 billions or so. And if we add to the liquid staking protocols also liquid staking on exchanges, which I think we actually should count among the liquid staking options, it will be closer to 20 billions, I think. So large, but not overwhelming part of the staking economy. I'm going to, like, I'm not going to do any deep insights here. Like, don't pretend there is something I'm going to say that is not pretty obvious, I think. But I'm going to say it anyway. I'm going to make 3 predictions. Basically, one is that like protocol-based liquid staking will grow alongside DeFi ecosystem. When DeFi ecosystem grows, liquid staking protocols grow with it. When it doesn't grow, when it stagnates, that like liquid staking will not, protocols will not grow. Like there will be people will use staking exchanges instead. There will be a lot of options for liquid staking, but few of them will be winners. And who will be the winner, who will be the winners, will be determined by stakers. They will be the one who vote with their money about like what the future would look like. Now, in a bit of more details area of this statement, I'll talk about it. So, our experience at Lido building liquid staking protocols, many chains. We have like one on Ethereum, one on Solana, on Polygon, on Polkadot. The thing is, liquid staking protocol growth is driven by DeFi ecosystem growth. Whether when there is a low amount of DeFi penetration, liquid staking will also be pretty small. And when there is like a very strong economy like on Ethereum, liquid staking will be very popular. There are other factors, but like that's primarily the thing. Like when people want to use the Ether in DeFi, they will rather use some kind of staking liquid staking token in DeFi. When they don't want to use Ether in DeFi, they don't care about staked Ether, Rocket Pool Ether, etc., etc. So. And the main competition are the walled gardens of CeFi. Like exchanges have liquid staking since forever. It works very seamlessly. It's very easy for the user. They like just deposit the tokens that they used to if they are working with exchange, and it's automatically staked. It can be often used as collateral for margin trading. Like it has most of the users that people want liquid staking for. And if you don't care about being in decentralized finance, if you don't care about like these being not your keys, it's perfectly serviceable. So, and the product is just better than regular staking. The liquid staking is better for users than regular staking. The adoption barriers that like a major problem for liquid staking protocol growth is smart contract risk, governance risks, and sometimes tax implications. The smart contract risk and governance risk, on one hand, they go down with time. So like with time, people starting to trust more the protocols for good measure because they haven't been hacked. They are like less likely to be hacked in the future. Same about governance. And still, it's not worth it. Like if you're not using to use the token in DeFi, like if you're not using to not going to trade it or collateralize it, you don't want to take this additional risk. And there are like multiple options for building liquid staking protocols, and like liquid staking in general, not just protocols that are exist already or will be existing going forward. And to talk about them, we need to understand what is liquid staking as a product, like who are the users, what do they want. And there are 3 kinds of users, like 3 kinds of stakeholders for liquid staking. One is the stakers. They are most important here. And they want staking rewards, they want security, they want liquidity and usability in finance, basically. Protocols community want the best validator set for the protocol that is decentralized, censorship resistant. And node operators in protocols, they want to run a stable staking business if they are professional. And if they are hobbyists, they want to be, like, I don't know, respected. They are not rational. They just do it for the fun and for the feeling of contributing to decentralization, which is great. So, and the options that are available, will be available in the future, are broadly it's custodial option, the exchange-based liquid staking or custody-based liquid staking. It's protocol that are based on risk management. It's protocol that are based on bonds for security. They're hyper-compliant protocols and marketplace type protocols. So I'm listing them in the order of adoption. Custodial liquid staking, like exchange liquid staking, is like the largest one. If you combine, like even on Ethereum, but if you combine together all the exchange staking options, it's like a lot of market share. They are exchange or custody based, very simple to use for users, because like centralized solutions are like very good for you for user experience. Usually you can do a lot to make it simpler. They have no additional risk if you already trust the exchange in question with your capital. Often have included the options for margin trading, lending, money markets, etc. And because the operator of custodial liquid staking, like exchange or something, they are double dipping, so they're getting staking rewards and like fee on staking rewards, and they are also getting fee on trading, on maybe custody fees or something like that. They can offer very competitive rates compared to others. Like this option will likely win on profitability going forward. It's not the case right now because like Coinbase takes a lot of fees, but they have much more options to go lower on fees because they can double dip in vertical integrations. They have usually subpar validator sets, so like they don't provide like that much value for the like as much value as they could for the protocol, because they select few operators with little diversity in jurisdictions, physical locations, etc., etc. And it's not transparent, and they are susceptible to regulatory capture because like CeFi solution are like extremely regulated. Risk management-based protocols, they are non-custodial. They manage slashing risks protocol-wide by creating creative validator sets that like minimize slashing risks. Therefore, they are usually capital efficient, so they're easy to grow, they're easy to accept stake, and for like for the competitive advantage on user side, they rely on DeFi ecosystem. So like when DeFi ecosystem is better than any single wallet garden of exchange, they can offer a good alternative to centralized exchanges. Validator set they have are like very different in design because and in quality. They can be big, they can be small, they can be like consist of one operator, which is like the same, the protocol operators basically, and they that's because like the managed protocol set is the validator set is basically the major part of the product here, and that's where they differ very much. It can be good, it can be bad, it like depends on the protocol. Bonded protocol are also non-custodial. They manage slashing risk by acquiring validator bonds. That makes them capital inefficient because validators, like the good like the not operators community, they don't usually have a lot of money. And when they are required to provide bonds, this is limited by basically the amount of capital of operators or the amount of debt they are willing to take from outside sources. And the validator set management is left to the market. Like basically, if you have capital, you can participate as an operator, you can provide your own validation, and that's the only thing that is required, which I think at scale delivers centralized validator sets because capital is centralized. Like if you take a look at Gini coefficient of Ethereum, for example, which is like one of the best ones, it's really high. Like most of the whales are vaulted by like few dozens of whales. When the protocol is at scale, that they are either providing a loan or they operate themselves at scale and take the majority of the validator set. This option of hyper-compliant one is not very different in tech side from risk management. It's a different approach because like its selling point and main feature is that the validator set is extensively KYC'd and certified and regulated, and they are likely to not deliver validator sets that the protocol community want. And I don't think there will be much liquid or usable because like usability in DeFi requires like they made clients are people who are like very scary of regulations. I think that's like selling through lawyers type of things that are averse to participate in much of the DeFi. So, and the last type is marketplace, is when there are multiple options for staking in one place, different risk profiles, features, and costs. And when they do a liquid staking token, they have to fund it in some way, like either they do risk management on options, like to make a fungible basket of different options in the marketplace, or do the bond type, or just do a naive, like assuming every risk profile is the same. Current state on Ethereum is that risk management is the largest protocol, like it's Lido, it's risk management type. The second by size is custodial, but it will very quickly jump to 1 by 1 when withdrawals are possible, and any exchange can be staked more safely than right now. And the third type is bonded, it's Rocket Pool, it's the third position. And by growth speed right now, Coinbase liquid staking token grows the fastest. Lido has the second place, and Rocket Pool is the third. So this is the current trend. I think that the only non-custodial trust minimized options can be designed with the can't do evil principle in mind. So liquid staking protocols that are sufficiently limited in what they can do, though, like to stake, to validate a set selection, to force or like entice operators to operate in a certain way. When they are limited in that, they can be entirely harmless for the protocol and not a threat. Custodial solutions can't do that because like they can act like with their values, but they are extremely susceptible to regulations, which can be not aligned with company's value. I think the only risk management based protocols can deliver a good validator set at scale, because at scale, the main thing that you deliver for a protocol is a good validator set. And if you don't have an opinionated selection algorithm that says that like the good validator set should be defined, like should be diverse in jurisdiction, in should be pretty flat in distribution of stake, should be diverse geographically and like in cloud and on-premise operations, etc., etc. That's essentially what like risk management is. You manage the risk for the protocol as well. So I think there are two possible outcomes for the future of Ethereum. One is that like most of the stake is in the risk management protocol that provides a good validator set. minority is in custodial, and bonded is like the on the third place. And the beta outcome is vice versa, when most of the stake is custodial and the rest is in protocols. So anyway, whatever I think on that, it doesn't matter much, because I'm not the one who decides who will win and like who will lose and like what will be the best the largest options. It's the stakers who decide that outcome. Like not operators. They are agents. They operate like either very small amounts of their own stake or like large amounts of other people's money. They do not decide like who is going to be the winner. It's not stake aggregators like protocols or custodies, because users, stakers actually decide which aggregator to use. It's not protocol researchers or developers, because they design like a neutral protocol that can be used by other people, which are stakers, to have the desired outcome. It's not voices on crypto, Twitter, or like protocol governance. It's going to be the stakers. Current state of Ethereum staking is the direct result of stakers making the choice in the past. Like why is Lido big? Because people staked with Lido. Why is like Coinbase big? Because people decide to stake with Coinbase. The future will be a result of stakers making the decision going forward. So what I'm asking you folks is to select the best stake based on your ethos, your needs, your capabilities. Like if you want and you can run your own node, run your own node. If you see a good option for staking with the protocol, like stake with the protocol or with the node operator you trust or something like that. Because like stakers will be deciding the future of validator set on Ethereum, like how the Ethereum will be operating in the future. As a bonus thing, I made a few predictions, but there are a few curveballs that can invalidate all of that very unexpectedly. One thing that like is obviously can change the landscape very much is regulations. Like regulators can force most of Ethereum stakers, and most of like a lot of Ethereum is like in regulated jurisdictions. A lot of Ether is holders are in regulated jurisdictions to comply to local regs. And if local regs say them to stake in a specific way, they will likely comply. The funds, the custodies, etc., they will have to. The second curveball is restaking. Shout out to Angular. It's basically using the same stake on multiple protocols. The main idea is like you can stake either in Ethereum protocol and then can use the voucher to the stake tether, like stake tether token or like a RES token or something, as a stake in a different protocol that does something different, and it's subject to additional slashings if something goes wrong. That leads to a combinatorial explosion in potential risk and rewards profiles. So right now it's pretty easy to funge the unfungible the staking positions. Like you manage the risk and rewards, and like you can get liquid token out of it, like or make it bonded or something. When there is a lot of options for getting additional rewards for taking additional risks, which is going to happen if Angular takes off, that makes the space very, very diverse and for possibilities of using your Ether in different ways, and it's becoming much harder to funge than fungible. And it makes risk management-based protocol harder to design, and marketplaces more suitable to the state. When there is a lot of differentiation in different options for staking, marketplaces are better suited to that than risk management. And the elephant in the room is second-order effects of MEV, because like that's a very field with emergent rules. We don't understand how it works until it works in a specific way. Usually, we can predict some things, but not all things. And it's hard to see the future clearly, and it clearly has a lot of requirement for latency and benefits a lot from exclusivity deals, which can force centralization somewhere in some place. And it can happen that it will force centralization like on protocol management, like on stake management level, or like on staking layer, or like wherever. We don't know yet. Like at least I don't know. I don't quite understand how it will end up, and I think we will see it when we'll see it, not before. I think the best way to counter that on staking level will be to transform validators and protocol to dumb pipes that don't make any decisions basically, or make as like can opt out of making decisions at least. Something like PBS design with CR lists, for example. But like as I said, it's curveball. I'm not completely sure with how it's going to play out. So that's it. Thank you for coming. I'm really hyped with seeing such a good crowd. Any questions?
Hello, sorry. You mentioned in Lido's the risk management reference of LSDs. How is this related to the insurance of Lido in relation to the TVL?
I don't quite get the question. I'm going to answer as best as I can. So Lido is a protocol that takes stakers Ether, and it distributes to a validator set in a specific way. This validator set is selected in a way to de-risk the staked Ether holders, so like reduce slashing risks, and to make the validator set of Ethereum better as well. So like we try to distribute in a way that will be increase the diversity of validators and like the stake distribution, make better stake distribution. We don't require operators to bond the capital to operate, and that makes scaling for Lido really easy because all the operators need to do is to upload some more keys into Lido and like accept more stake. And that's why when there was a lot of demand for staking in the ecosystem, it went to Lido and not say to Coinbase. When the growth is limited by not operators having enough capital or having enough like cheap loans options or something like that, it's not being able to ride these waves of like staking demands. So I guess like the TVL of Lido is direct results of the design. Can't hear you. The mic doesn't work.
Okay, I was wondering, like one of the curveballs that maybe could happen is, what if it becomes dramatically easier to operate nodes? Like it's pretty complex to like spin up your own like beacon currently, but what if it was much easier? How would that impact the overall market, in your opinion?
So I think that it's not going to become dramatically easy for a long time. The reason is like before protocol classification, it's really hard to maintain the nodes in like in a good state because there are a lot of grades and like hot fixes and stuff. But imagine it is becoming dramatically easier. Then on liquid staking, I think the result will be that there will be more solo operators, and like every protocol will that will be big enough will converge on some hybrid model of having most of the stake and risk management and less stake and bonded solution for permissionless operators, just to promote the solo stakers. And the removing of barriers will lead to more solo stakers and like a bit more importance for to have this feature. That's my guess.
Hello, Vasily. It's really nice to meet you. I have two questions, actually. First one, I would like to understand what do you see as the biggest risk for the liquid staking industry or the staking industry as a whole right now? And second one, what do you see as the biggest risk for Lido right now?
I think the answer to both is smart contract risk. Like DeFi protocols are like very robust. I think it's the most bugs-free code in the world. Like right now, like better than aerospace, better than medical code, etc., etc. But it's like existing in a very toxic environment where any mistakes gets exploited like very fast. So smart contract risk is probably the major risk. And on a more like economical side, I think like I'm really thinking that exchanges, wallet guard like CeFi are really like a very strong competitor to protocol-based liquid staking, because centralization is more like it's cheaper, and people care a lot about APR.
So I have some statistics on the Lido tokens emission. It's kind of like outdated, but it's something to minimize. So the token incentives that the emissions in the last 7 days is 5 million in terms of TVL, while the revenues is only 600K. Do you think it's that people actually value the governance of Lido itself as a liquid staker, or it's kind of like being overvalued? Do you see any attack factors like governance if it were to like if it kind of like go down if people don't value it as much as it right now?
Let me rephrase and say if I understood it right. So you're saying that we have a lot of incentives, and Lido's TVL is probably because of incentives and not because of like people, because of the fact that people want it, right?
Okay, while the token incentive is 5 million.
So the incentives are not that big in the overall protocol, like compared to overall protocol revenue, and they are needed to maintain good liquid pools for liquidations to happen. That's the only reason they exist. The staking rewards are the main reason people have staked it. There is like of over like 4 million of Ether in Lido. I think about between 200,000 and 600,000 of staked Ether is locked in. Maybe 700, I don't know, is locked into incentivized pools. So I think that when withdrawals are in, that will be completely unnecessary and will change everything. Like the incentives will be slow, but the protocol will be just as useful.
Hi, everyone. Welcome to the Flowers Room. And we're very excited. We have a great lineup today. Our first speaker is John Stevens from Veradice. And he's going to be asking us a question at the back of all our minds. Are your zero knowledge proofs correct? John.
All right. Okay, as was previously mentioned, I'm John. I'm also the CTO and a co-founder of Veradice. And so today, I just want to ask you a question. Are your zero knowledge proofs correct? Why don't we find out? So, just a little bit about Veradice. All of us come from an academia background. So on the slide right here, you can see some of the main members from Veradice. So on the top, those are the co-founders, including myself. And on the bottom, you can see some of the other people that we have here at Devcon. So if you have any questions, please come and find us, ask us questions. They're also right there in the third row. But yeah. So just a little bit more about us. We are a security company. So we provide audits, and we also provide tooling in order to find vulnerabilities in all aspects of the blockchain. And so basically we build tools to help ourselves and other people find bugs in DeFi applications, blockchains, and what we're going to be talking about today, zero knowledge circuits. And yeah, we're very interested in making our tooling available. And so today I'm going to talk about specifically our open source tooling and not about the tooling that we're providing in our security as a service suite. So to begin with, I think that would be useful to talk about what sort of bugs we actually see in zero knowledge circuits. And so the reason why we want to do this is because these circuits are extremely prevalent, especially in L2 blockchains. And so that means that you can see these circuits integrated into smart contracts themselves, like Tornado Cash and Semaphore, in blockchains, and also there are a number of libraries for circuits as well, like the Circom lib. And so one of the interesting things that we've seen is these circuits present new challenges, especially for people who are interested in security. And the reason why we want to do this is because we've seen a number of exploits in all aspects of the blockchain, from smart contracts to the blockchain itself. And these zero knowledge circuits are a relatively new domain. And so while we haven't seen very many hacks in the circuits themselves, other than luckily the ones that Tornado Cash found before it was exploited, we want to make sure that people are thinking about the security of these circuits as they develop them. And so the way that we want to do this is for Veradice, we want to provide tools. And so I think that the best way to start is to talk about some general types of bugs that we see. And to do this, I need to kind of establish the model of the zero knowledge circuit that we're assuming here, just because these circuits can be fairly complex. And so here's a simplified model of the circuit. So basically what happens is there's going to be a witness generator. This could be a blockchain or a smart contract or something like that. And it's going to take in a set of public and private inputs. It's going to generate a witness. Then this witness is going to be provided to the prover, along with some additional information, which will generate a proof. And then finally, that will go to the verifier. And then the verifier is going to say, yeah, it's correct, or no, it's not. And so when someone wants to create one of these circuits, there's a couple of ways that they can do so. In the simplest model, they simply write a single application. So this would be their circuit application written in something like Circom or Cairo. And then that will generate the witness, so your smart contract, for example. And it will also generate a set of finite field constraints, which is later used to generate the prover and the verifier. And so the interesting thing that we see here is you have a single application which is used to generate two different applications which do slightly different things, and more interestingly, they can be out of sync. And so one type of bug we see here, obviously, is if someone doesn't implement their circuit correctly. So if that happens, then we have a functional correctness violation, and it basically just means, you know, someone needs to go back and rewrite their circuit in a way that's correct. The more interesting bugs, though, are when the witness and the constraints are not in sync with each other. And so this happens because generally these languages provide ways for you to put specific logic in your witness and put specific constraints in your finite field constraints. And so if it turns out that your constraints are less permissive than your generator, you could reject valid interactions with the application. So for example, if you have a blockchain, it's possible that in this case you could have a denial of service where the blockchain wouldn't be able to process transactions, which, you know, wouldn't be great. The worst case, or the more dangerous case though, and I should say under-constrained, is an under-constrained circuit. So what happens with an under-constrained circuit is the constraints are more permissive than the witness itself. And so the reason why this is more dangerous is because while the witness might be correct and it might provide all of the interactions you want, and they're all accepted by the constraints, everything seems great. However, an attacker could then come in and they could provide an alternative witness, which might be used in order to get some alternative transaction or logic accepted by your constraints and then proven. And this would necessarily be bad because let's say one of the constraints, which didn't end up in your finite field constraints, was equivalent to the sender is equal to the admin, right? Obviously, if someone was able to bypass that, then bad things could really happen. And so the way that we deal with this in Veradice is by using a field in computer science called formal methods. And so formal methods provide a way of automatically reasoning about software. And so it does this by understanding the semantics of the underlying program and iterating over that program in order to determine information about it. And so basically what we're going to do is we're going to use formal methods in order to find bugs and create proofs that the software is correct. And so within formal methods, there's basically 3 different fields. So there's automated testing. So if those of you, or for those of you who have heard about fuzzing, that falls into this category. And so basically, in that case, someone is just going to run the program on a bunch of inputs. And so this is useful for finding bugs. Next, we have static analysis. We'll see a static analyzer in this talk, which is going to analyze your source code for a particular class of bugs. And the important thing about these static analyzers is if they can't find the bug, it has proven that the bug does not exist in your program. However, you know, the more interesting case is if it does find a bug. And then last, we have formal verification. Some of you might have heard about this. There are multiple ways to perform formal verification, but at Veradice, we're particularly interested in automated formal verification. And so basically what this is going to do is it's going to analyze your software and make sure that a specification, where a specification is essentially a way of expressing the intended behavior of your application, it'll make sure that that specification holds for the application. And so that means that after using a formal verifier, 1, you can verify custom correctness properties, and 2, you will have proven that that property holds or that your implementation is correct. And so as we go across the spectrum, it takes more effort in order to both build and run the tool, but it also provides much stronger guarantees. And so we're going to be looking at some of the open source tools provided by Veradice that fall into these categories. And so first we're going to talk about a static analyzer which performs common vulnerability detection on Cairo or SORCOM programs. So basically what I'm going to describe, this is the type of bug that is found by a static analyzer that we created called Picus. And so basically what it's going to look for is uniqueness bugs. And so what a uniqueness bug is it happens, or it occurs, when a constraint allows a single input to map to multiple outputs. And so what I mean by this is if you look at this circom program over here. You don't have to understand what it does, but basically there's a bug that's circled in red. The reason why that's circled is because it constrains all of the outputs except for one very specific output. So decoder is supposed to simply zero out all of the bits except for a single bit that is specified by imp. And so what happens here is if you look over on the right, you'll see that the constraint specifies that that multiplication has to be equal to 0. But there's two ways that it could be equal to 0. It could be equal to 0 because the output is equal to 0, or it could be the case that imp minus I is equal to 0. And so all of the cases where imp and I are not equal to each other are constrained, but in the case where imp is equal to I, we find an unconstrained bit. And so what does this mean? This means that an attacker gets to decide what the value of out at imp is. So it could be the desired value, which is 1, or it could be 0. And so why does this matter? Well, because of the reason that I told you about earlier, it means that depending on how this circuit is used, someone might be able to leverage this uncertainty in order to violate some assumptions that you have made and hack your protocol. So what can we do about this? Well, I already told you that we're going to be using static analysis. And so there's two types of ways that we can solve this problem. One is we can just perform straight static analysis. And so what this is going to do is basically we'll just look at the inputs and outputs, and we'll say that if the output is a linear combination of the inputs, then it must be constrained. So that works. However, it also produces a lot of false positives, which is undesirable because then you have to go and you have to determine, is this real or is this not? So instead, you could use something called SMT solver. So what an SMT solver is it's simply a program that can solve mathematical formulas. And so because you have constraints, you can encode this mathematical formula that states whether or not a particular output is constrained. The problem is, normally there are many constraints. And so if you tried to send that to an SMT solver, it would quickly bog down, and it most likely would not be able to solve uniqueness for large circuits. So basically, we see that static analysis is scalable, but not precise. And we see that the SMT solver is precise, but not scalable. And so what we have done is we've developed Picus. And so Picus is going to take in your constraints, and it's going to output one of three things. So it's going to output, yes, this particular circuit is entirely constrained. No, it's under constrained, or I don't know. But the way that it does this is by using a combination of static analysis and SMT. And so what I mean by that is we're going to have two phases that are going to iterate. And so basically in the first phase, what we're going to do is we're going to take those constraints and a set of signals, which we've already proven are constrained, and then we're going to compute a new set of constrained signals. And so this will give us a set of constrained signals that we already know are constrained. And so if we end up finding that all of the output signals are constrained, great, we're done. Otherwise, if there are some output signals that we haven't been able to determine if they're constrained, we can go to the next step. And so the next step is the SMT phase. So what happens in the SMT phase is we take the signals, which we have already proven are constrained, and then we, again, take the set of constraints, and we use an SMT solver in order to try to find additional output signals that are constrained. And so if we happen to find that all the output signals are constrained again, great, we've solved the problem. If we find an output signal that is unconstrained, because we can prove that in this case, then we say, all right, you have an under-constrained signal, and it's specifically this one. And then otherwise, if the SMT solver fails for some reason, so basically that happens if k prime is equal to k, then that means that we've basically stalled, and we'll instead just return, I'm not sure. So the last case is if we ended up making progress, then the important part is we can go back to the static analysis case because we have now proved more cases are constrained, and so that means that the static analysis phase might be able to make further progress. And so basically we'll do this in a loop, and we find that in this case, Picus is able to scale much better than the previous attempts that we saw. So basically, we evaluated this on a set of circuits, and Picus was able to solve, I believe that comes out to 98% of the circuits that we threw it at. Whereas if we look at static analysis and SMT, static analysis returned a bunch of false positives, and SMT timed out on a lot of the benchmarks. And so this is the first tool that we look at. So the important part is you provided a circuit, and then Picus does all of the work for you. You don't have to provide it any additional inputs, and it will give you a list of possible problems. The next thing that we're going to look at is a verifier. So this performs automated verification. So what I'm going to talk about next is a tool called Magi. So what Magi does is it performs automated verification on Cairo programs. And so the way that it works is you will provide Magi with your source code and a specification. And as I stated before, the specification just specifies the intended behavior of your Cairo contract. And then Magi will spit out either yes, or more interestingly, it'll spit out no, and it will tell you why. And what I mean by why is it will provide you concrete evidence of why your specification does not hold. And so the way that it does this is it's going to take your specification in your program. It's first going to translate it into a symbolic representation. And so what I mean by a symbolic representation is rather than having, you can think of a symbolic representation as being unconstrained. So basically, any value in your program could map to any other value in your program. And so then, once it does that, it's just going to run this through, it's going to run your program symbolically. And I'll show what that means in a little bit. And more importantly, it's going to interact with an SMT solver in order to generate proofs that your, as it runs your symbolic program, it's going to use the SMT solver to prove that your behaviors are consistent with the specification. So let me get a little bit more concrete about this. In order to do this, you need a little bit of information about symbolic execution. So basically, the way symbolic execution works is looking at the very top, you can see just a set of variables. And so we start with these variables being mapped to any possible value. So unlike testing where you say, like, in this case, u is equal to 5, we say u is equal to some symbolic value. So it's going to map to any value within the range. And then when we symbolically execute the program, what we're going to do is we're going to essentially just run through your code and generate case statements. So for those of you who remember, your proofs class, basically we do case splits whenever we come to like conditionals. And so here what you can see is starting at the very top, we have everything unconstrained. But then once we enter that first if statement that you see, you'll see on the left-hand side that u is equal to 5. But then we also need to consider what happens if you don't enter that if statement. And in that case, u is still some unconstrained value. And the important part is at the very end of this, after executing the entire function, we end up getting a set of symbolic equations, which we can then send to an SMT solver to make sure that it's consistent with your specification. So some of you may have noticed that it seems like there's a fairly large spread. So if we look back at this, you kind of get this tree-like structure with a lot of breadth. And so in order to make this actually scale, what we do is we have to perform a basically intelligent merging. So essentially what you can consider is after we execute an if statement, once control flow joins back, we can also join those states. And so if you don't understand what this means, that's okay. Basically, all I'm saying here is that in order to improve the scalability of this tool, we push some of the work off onto the SMT solver, and you basically have to balance the work that your symbolic execution engine is doing and the work that the SMT solver is doing. So let's look at an example of how this actually works. So here you can see the move function in MakerDAO's Cairo implementation. And so the specification that we're trying to check is basically that move transfers funds correctly. And so the specification that you see on the right-hand side basically says that after the move function has executed, the DAI balance at the destination should be greater than or equal to the DAI balance at the beginning, and then the DAI balance of the source should be decreased by an appropriate amount. And so the interesting thing here is Magi reports that this is not sound. This specification does not hold for the code on the right-hand side. And specifically, it says that it does not hold when RAD, which is the amount that's being transferred, is equal to some specific value. And so the reason why it reports this is because in Cairo you have this interesting case where because of the size of the large primes, they are going to be less than the size of a UINT 256. And so Cairo ends up splitting your UINT 256 into two parts, the lower 128 bits and the upper 128 bits. And so importantly, the reason why Magi reports there's a violation is because the MakerDAO developers here forgot to constrain the value of RAD. And so the way that you do this is in Cairo, they provide a specific function in order to make sure a UINT 256 is properly constrained. And if you leave that out, that means that your UINT 256 is not well formed. And so once we add that check back in, and then we send this back to Magi, Magi will report, yeah, everything's right. The specification holds. And so in this case, we have properly guaranteed that this move function transfers funds correctly. And so this was just a very simple case. However, we've been working with the MakerDAO people in order to verify their Cairo implementation of their protocol. And so as we've done this, we've ended up finding, I think, at least one bug that the MakerDAO people have merged into their implementation. So that's all I have for you today. If you are interested in learning more or seeing demos of these tools in about an hour or so at 3 o'clock, we will be down at the ZK Community Hub, just giving a demo of these tools and a couple of other ones. Also, on the left and right, you can find links to the repositories for Picus and Magi. So if you're interested in trying them out, please do. And there's also a Twitter link. So if you want to follow us on Twitter, that would be fantastic. Okay.
Hi, thanks for your talk. Just a question. When you're talking about these Cairo contracts, and could you say, if I didn't have access to the source code, and I just had this circuit that's, like, how easy is it in practice to exploit these, kind of arithmetic errors or constraints?
So if you're an attacker and you don't have access to the source code, how easy is it to figure this out? Yeah, that's a good question. Attackers are very good at looking at low-level code and figuring out how to exploit it. And so I would say that, if you were trying to get security through obscurity, that's really not going to work for you here because generally your code is going to be public somehow. And so if someone is able to gain access to even the low-level implementation of your code, then they could possibly figure out how to exploit it. And on top of that, we've seen cases where even if someone doesn't have access to your code, but they're able to query it, they can also find potential exploits. Any other questions? I think there's one over there.
I want to know what kind of bugs
or issues cannot be found by those two tools?
So what kind of bugs cannot be found by these two tools? Okay, so for Picus, because it's not performing functional correctness checking, it can only find under constraint bugs. And so that means that it won't be able to find like if your program is written incorrectly. For Magi, because it is verifying functional correctness, it relies on the quality of your specification. However, if we assume that you have specified the behavior of your program properly, it should be able to find any potential bug in your program. So for example, one thing that we see is if you write a specification that says, let's say the die is transferred correctly, but then it turns out that due to an under constraint bug or a uniqueness bug, it doesn't end up being transferred correctly, Magi will point that out. However, it depends on the quality of your specification. And yeah, it also won't find bugs in anything other than your Cairo contract. So if you perform interactions, let's say with other applications that Magi doesn't have access to their source code, Magi won't necessarily be able to check and make sure that everything is correct. It has to make simplifying assumptions, basically.
So thank you, John. We'll be starting the next session in 4 minutes, so please be seated by then. Thank you. Hi, everyone. Welcome back. So our next speaker is Brian Wilkes, and he'll be comparing the performance and security characteristics of some zero-knowledge proofs that are commonly deployed in the Ethereum ecosystem. So, Brian?
Hello. Wow, that's loud. So, who are my data scientists in the room? Raise hands. Very few. Devs out there? Lots of devs. Nice. Investors? Degens? Yes. Put it down. How about expertise? Who's a beginner in zero knowledge? Just got the basics. Cool. Who knows what's going on but has not written a circuit before? Who's a true ZK expert? Knows a ton about ZK? You. Perfect. All right. Thanks for having me. My name's Brian. I am a grantee with the Ethereum Foundation Privacy Scaling Exploration Team. So today I'm going to be talking about ZK proof performance and security characteristics. So what's in the docket for the day? First, we're going to go over some background. So we'll just give some background on what ZKPs are, try and work through what they actually mean for on-chain data. Then we're going to look at how to actually find those zero-knowledge proofs and verifiers, circuits on and off-chain. Then we'll look at some of the characteristics behind those and what they mean. So, unfortunately, Waldo's not going to be with us today, so this is the second best piece of art I've ever done, so I hope you appreciate it, everyone. So what are ZKPs? For a high level first, we'll go through this quick and then move on. But we have Alice. Alice wants a drink. She's a prover. We have Bob. Bob is the bartender, is a verifier. Alice does not want to give all of her information to Bob. And so therefore, she can put in her birthday. The circuit will output a proof. Bob can verify that proof is correct, that she's old enough to drink, and the cerveza will flow. So what's important for this is you have a prover, you have inputs, you have the circuit itself, you have the proof popping out, and then Bob decides if it's true or false, and then does an action based on whether that verification is true. So why do we need zero-knowledge proofs in Ethereum? So the first thing that we struggle with is scalability. So right now, we can do about, on main chain, 13 transactions per second, and we really need to get into that 13K transactions per second, if not significantly higher, to get in the Visa range. So how zero-knowledge proofs help us? They can take fully separate chains, and they can impart the full security of Ethereum to those chains. So privacy as well is something that's a hotbed issue to me. Ethereum's public. If you're a data scientist, as a few of you are, you can go online, or you can go on Ethereum and see everyone ever does. I don't want to live in a world where you have scalability and everything sits on that platform without having the privacy behind it. So let's talk about on-chain. So this is what it looks like. You have your layer 2 blockchain here. They have the blocks going. You aggregate some of the transactions together, and then you batch them into a ZK circuit. So you take those transactions, they go into the circuit produces a proof. This is all off-chain. So then you have your Ethereum main chain, where things are expensive. So you're able to take your proof and post that to the verifier smart contract, and then the layer 2 state, source of truth, can get updated. So that's what happens with the scalability side of things. Now let's talk privacy. It's very similar. I won't have reveals for you. I'll just go right to it. There's a secret. There's the ZK circuit. You put the secret through. It produces a proof. And then that proof goes on-chain to the verifier smart contract, and funds are released. So that's very similar. That's going to be your mixers, your channel caches, different things. What's important for both of these two is that you have off-chain and on-chain. And on-chain is where the verifier and the proof gets posted. And off-chain is where the circuit and the proofs are. So this is the best piece of artwork I've ever done, so appreciate it while you can. So let's find some ZK proofs on-chain and figure out where they're at. So this is called the search for verifiers. So why are we searching for verifiers? The important characteristics of a zero-knowledge proof are in the circuit. So the circuit's going to generate, they're going to have the different characteristics that are important to us. Let's look at a particular ZK sync transaction flow, for instance. So between September 26th and September 20th and September 26th, there were 2,170 blocks, 265,000 transactions, which were batched together into 214 inputs, proofs brought on chain. So what you want, the ZK circuit did not change, but those inputs and the proofs did. So each circuit has a unique verifier on chain. So for each circuit or circuit systems, they have their own unique verifier that's there. And if you want to know about circuits and you want to use on-chain data, you need to go through the verifier. So going through the verifier, you use the L1 chain data. So let's talk about how to find verifiers. So the first section is, if you guys haven't used BigQuery from Google, I highly recommend it. It's a great tool. It allows you to search through lots more data than things like Dune do, as much as I love Dune. So different queries that time out within 30 minutes for Dune will go in about 2 seconds for BigQuery. So check it out. The 3 tables that I used for this project were contracts, traces, and transactions. Since you're almost all devs, I won't go over traces versus transactions, but the start versus end of things. So, okay, so the first way to try and search through bytecode is to go for constants. Constants will show up in bytecode as a big hex. So if you can get a big enough number that's unique enough for what you're looking for, you can take that and search with very simple SQL queries in through the bytecode. So this is both a big and unique value. It's the finite field. So the finite field is the range at which you modulate over when you're doing different cryptographic things for zero knowledge. So this is it in hex form. It's massive. So the first way that I looked through the data was to search for this finite field. Unfortunately, it didn't exactly give me all the verifiers, so it gave me a lot of different noise. There's 558 contracts that have the finite field constant, and after checking every one of them manually, most of them were not verifiers. So I moved on to trying to get into method IDs. So the second tool that I think is really important, and apparently it's new according to Etherscan, is the transaction decoder. So the transaction decoder, what it does, if you look through it, is if you go through and look at a transaction, it will tell you the exact flow of what happened through that transaction. So looking at this here is another ZK Sync example. First, it proves the blocks after going through some proxies. And then in the verifier contract, it calls a function called verify aggregate block proof. So after doing some modular addition down below, it outputs true and the state gets updated. So method IDs. The method IDs are the first 10 characters or 4 bytes that come through with any input or transaction call for traces or transactions. So just going through them briefly, you can see that this function here is for Starkware, and it's a fry verifier. So this is what is actually verifying the proofs. So if you want to know what the method ID is for this particular function here, then you take out all the chaff, if you will, from inside, and then you run the kcac 256, and you take the first 4 bytes plus the indicator that it's hex. So that there, the OXE85A6A28 is the method ID. It'll be the first 10 characters in any call that when you look through the data. So a great resource, again, I like to show the resources that I get to use. The 4byte.directory is fantastic. You can input any method ID, and it will tell you what the text signature for what it should be is. So now, what do we find? Essentially, there's about 65 confirmed verifiers on main chain. Now, there's probably a few more, maybe 30 more that are not verified public contracts. So and those 65 confirmed verifiers have done over 600,000 verifications. So of those, There are about 16 that are active still. That's active according to me, and some of them are very minor projects. If you're trying to squint, it's because I made it small, so you'd have to go on the GitHub at some point, so sorry. I was surprised by how few verifiers there are actually on main chain. But moving on to the characteristics. So we'll look at proving systems. So your proving systems here that are actually being verified on main chain, you have your classics. I'm sure you guys have all heard of these, but your Groth 16 from 2016, that runs your Tornado Cache, your Hermes, your loop ring, and a bunch of other different privacy functions. You have Plonk, which is Aztec Connect, ZK Sync. Then you have Turbo Plonk, which is the original Aztec. Aztec Connect uses Turbo Plonk before it gets on chain, but then it uses Plonk on chain, if that makes any sense. And then you have Halo 2, which is coming out. Zcash uses it, and then also Scroll is going to deploy with it. Most people I talk to are really moving towards that Halo 2 move. It seems like it's a really good proving system. So it's not on main chain yet that I've seen. So then you have your Starks, and that includes all your Starkware projects. So Starks versus Snarks. Snarks, the succinct, non-interactive argument of knowledge. And then there's Starks, which are scalable, transparent arguments of knowledge. And the major difference between the two, there's a bunch of them. These are the base level for what happens, but quantum computing is probably going to be able to take down Snarks, but Starks will probably be resistant to it. So what is quantum computing? When will it come? I have no idea, but if it does, this is what will happen. So looking at these different proving systems, you have Groth 16, which is in blue, really taking off. That's on the back of Tornado Cache, as well as Loopring. And then you have, down below, you have your Stark / Fries that are coming through. Those are the Starkware projects. They have really taken off. DYDX posts a lot of data to chain often. And then you have your Plonks, and unknowns are probably Plonks, but I wasn't quite confident enough to say that. So. Okay, let's talk about trusted setups. So a trusted setup is where on the elliptic curve you should evaluate the different ZK proof. So it's kind of an agreement in a spot that a prover and a verifier can kind of verify through what that snark's going to look like. So I like to think of it like a trust fall. How many people have done trust falls before in their life? A couple? Yeah? It's scary. So you get up there on a big standing, and then you fall backwards, and as long as one strong person below you is there to catch you, then you should be good. So as long as the trusted setup is kind of similar. If everybody's toxic waste gets collected together, if everyone gives their secret out and doesn't want to catch you or is distracted, then the snark can be, then the trusted setup will not work, and someone will be able to write proofs that will be false positives, and they'll be able to take money from you, if that makes sense. So this requires one honest participant from the MPC ceremony. I also like to think of it like Thanos. If you have enough Infinity Stones, if you have them all, you can destroy the proof, and it'll be good. So bad, actually. Okay, so what are the trusted setups? We have Groth 16 over there on the end. It has a two-phase trusted setup. And then the universal setups came in, and that's Plonk and Turbo Plonk. And that only requires one. So whereas Groth 16 needs a new ZK circuit, or needs a new trusted ceremony for the each circuit that it produces, Plonk and Turbo Plonk have a universal setup, and that allows them to only have one total ceremony. So if anyone here wanted to create a Plonk, you could use the universal ceremony that's already been created and already been done. And then you have Halo 2 and Starks. They do not require trusted setups. So that's obviously, you want the least amount of trusted setups as you can. So moving on, the actual projects themselves, you have Groth 16s are Loopring, Polygon Hermes, their withdrawal, and then Tornado Cache. Those are the major ones that are currently being in operation. So these are trusted setups. They use the perpetual powers of Tau, which is basically an on-chain step one for the different trusted setups. And then they had a step two. That step two, these are the number of participants that were in those ceremonies. So If you can get to 16 people from the loop ring that did it, if they all compromised, then that will not be a valid trusted setup. Then those funds will be able to be taken. So you have 16 for loop ring, you have 6 participants in the Polygon Hermeses, then Tornado Cash had a whopping 1,114. Moving on to Plonks, so like I said, you only need one trusted setup ceremony to be correct, and then anyone can use it. So they're all using the Aztec Plonk Universal Setup. It is all these you can see attestations on GitHub to see how they worked, but they had 176 participants in that. So that's all your ZK Sync, your ZK Space, Aztec Connect, Aztec, all the way down the line. And then you have your Starks, which do not have any trusted setups. We'll talk about recursion. This is the other major thing that people are looking for performance. So as you go through performance, recursion is the ability to take a big computation and break it up into a bunch of little ones and do them together, and then recursively prove back to the top. So what this allows you to do is parallelization of proof generation. So you can decentralize and have a bunch of provers doing this in parallel. So get out your ASICs, because you just got rid of them for the merge. And then it also lets you do proof chaining. So you can have the output of one proof be the input for the next proof. So what provides recursion? Pretty much everything but Groth 16 is now doing recursion, and they're doing it in better ways, I guess, as you move forward. So that was why would anyone use Groth 16 if you can't do recursion and you have a big trusted setup? It's faster, and it's cheaper to verify. So it's the OG, it's been there for a long time, but people are moving on because of those two problems mostly. So now I guess we can talk about my favorite topic, which is data availability as a data scientist. We'll talk, this is going to be about L1s and L2s. So for the purists out there, L2s would only be rollups, but I'll use both back and forth. So ZK Validiums. Validiums, they have their state root is on the bridge contract, and then they have their state reconstruction that's off-chain. It goes through a data availability committee to go on-chain to be able to make it so you have that data, but it is permissioned on that side of things. Then the alternative, which is supposed to be gold, it kind of looks like bronze, so forget that, is you have your state reconstruction and your state root for the ZK rollups down on the bridge rollup, or down on the bridge contract. So that allows you to always have that data to be able to generate a proof in case you do escape. So why would you do a Validium over a rollup? It's many more transactions per second. So your IMXs and your different StarkX projects are able to be a lot cheaper. So moving forward, let's look at your Validiums that are currently operating. You have StarkX, which is Immutable X. You have Runify, SoRare, Apex, other ones as they're coming out. You have ZK Porter is coming out from ZK Sync. And then your rollups, I'll run through these because you guys probably all know them, but you have DYDX, Loopring, ZK Sync V1, you have ZK Space, StarkNet. So I'll pause for the camera. And then moving on, there's a couple more that are the newer ones that are coming up for rollups that are exciting. You have ZK Sync V2, which I think is under 30 days now, which is exciting to mainnet. You have Scroll, which is going for a higher level of EVM compatibility. And then let's see what's next. Then you have all of Polygon's projects, which are all exciting in their own right. So let's talk about what it means to be a rollup. So everyone talks constantly about how the full security of Ethereum is being inherited by these rollups. So what does it mean to have the full security of Ethereum? You need to have the right to be able to force exit from that chain. So if you have, on your layer 2, if they have decide to be against you, you need to be able to submit your transactions directly on layer 1 to the Ethereum bridge contract and get your funds. So right now, you have your happy user down here. That's from Walmart. It's kind of creepy, actually, the more you look at it, so don't stare at it too long. That the transaction goes to this, the happy sequencers here, they put the transaction into the layer 2. Those transactions are batched into the ZK circuit. It produces the proof, and it goes to the Ethereum bridge contract, as we talked about before. So this is how it's supposed to function. So let's say that the sequencers become evil and start smoking cigars. You get unhappy. So your transactions can't make it to layer 2, and your funds are frozen. So what do? You take your transaction and you go directly onto layer 1 to the bridge contract. So when you take your layer 2 transaction, go directly to it, then the validators have a certain amount of time to actually include your transaction into the layer 2s. So usually it's between 7 and 14 days. So if they don't do it within that amount of time, then hell freezes over and the chain freezes. So your layer 2 cannot update state on layer 1, and the zero-knowledge circuit, then you, as a user, can produce a proof from the circuit. Then that proof will provide you the ability to get your funds back. So it sounds great, but it's also kind of difficult. How does the average user, especially when these proofs are off-chain and usually sometimes proprietary, how do you generate that proof? There's a few things that you have to really do to inherit full Ethereum security. So let's go through them. You have to have the available data on layer 1. So if you don't have that available data, then you can't reconstruct the state proof, and therefore you won't be able to properly get your funds back from the L1 contract. Secondly, you need to have functional and accessible force exits. So those force exits have to be in code, and they have to be accessible for the average person. They need to be able to generate those proofs. They need to be able to take that data and pool and directly send it to that L1 contract. That for a lot of devs, it's not a big deal that the front ends are all centralized, but we need decentralized front ends to allow people to escape in the case of one of the sequencers going evil. So, and then thirdly, you need time delays for the L1 contracts. So if the layer 1 contracts have time delays, or if they're immutable, then it gives people the chance to actually exit from that layer 1. But if they don't have time delays, then they can just change the contract and everyone's funds will be frozen from there. So, and then last is, this is a nuanced one, but the amount of money that you can secure from L1 is really based upon the amount of locked funds on layer 1. So if everyone force exits, then the layer 1 contract, which is the bridge contract with all the assets, they will impart all their assets to the people. But if there's more total locked value above on layer 2, then somebody's going to be out of luck. So the best way to think about this is a lot of the L2s are starting to get traction with direct transfers to them. They might even have their own state from different contracts and native tokens. If you have a native token on an L2 and you don't have assets backing it up on the layer 1 bridge contract, then the ability for you to inherit Ethereum security and take your assets off isn't there. So it's really important that as we move forward, that any state that is native to the L2 is known as for that risk that it has. So now let's get into, I guess this is the end of my talk, so I'm going to try and implore you to get into the data directly. Don't be like Waldo and be sad because other people tell you what's true and what's not. So we have, I tell you, I'm very impressed with these projects. I think you guys should all check them out. They're all open. You have BigQuery, you have Dune. The Dune's getting better and better, and then the BigQuery is a public database that has all of Ethereum layer 1 posted there. They'll give you $300 credits to go query through it, and you can really differentiate yourself, especially as a data scientist. You have the project that I actually completed. Please check it out. There's the QR code for it. I'll have it at the end too, so if you miss it, it's no big deal. But please go check out the data tables, all the SQL queries, any of the different things. Please feel free to let me know what I screwed up, and it'll be good. And then L2Beat is just such a great resource. I'm sure everyone's heard of them, and I'm sure you've been to their booth yesterday. But they categorize a lot of risks and a lot of specific things happening within these different projects, and I just can't recommend them enough to check them out. They're doing bridges now too, which is exciting. And then the layer 2s. I haven't got to the data on layer 2s. So it would be really great for everyone to check out the different, we're going to a different layer, modular blockchain, where you have layer 1s, layer 2s, and layer 3s. And these layer 3s are going to be deployed on layer 2s. And the privacy things already are for like Semaphore. So I highly recommend that. I would really like to see somebody check out layer 2s and be able to do the same data type projects for that. So I have some thank yous I'd like to get ahead of. So I'd like to thank the Daily Glay Discord channel and podcast for being so great. That's my favorite Discord channel there is. If you need to know things, there's so many helpful people. There's the Zero Knowledge podcast. It's so good for all the new pressing things. I highly recommend them as well. L2Beat, I'll show them again. And then the Ethereum Foundation Privacy Scaling Exploration Team. That's not their symbol, but I think that their new logo for Devcon is really cool, so I put it up there. And then I'd like to thank Justin Martin for all of his help in getting me into this. And I'd also like to thank Mark for all your help getting me through this stuff and really brainstorming through it all and trying to get through all those issues. So, so I got. Thank you very much. I will take yes, please. Sure. Yeah, they'll have a mic for you. Unless you're really loud, then you can just go for it.
I was wondering if you comment a little bit more on the security considerations when dealing with native assets on L2s. Like, I get that you can't withdraw the funds on the L1, but
sure.
Can you double spend, or can the validator like forge a balance or things like that, given the state's rolled up?
No, I don't think that those are concerns to do double spends and things, but I do think because your state the state source of truth is really sitting on layer 1, so you're not going to be able to, one of the reasons they do some of the delays and things, I believe, is to stop double spend from happening, but and that's why they freeze the state root on layer 1s. But I don't think that, if you understand, I won't go back over the ideas of, but if you have tokens that are here and the value's more there than on the bridge contract, then you won't be able to get your money back off of that. So if that makes sense. Good enough? Cool.
Hello.
Sure.
When you're talking about state on layer 1, have you had any thoughts in regards to upcoming state expiry?
Not yet, but I would love to. I'd love to hear your thoughts on it at some point. I'm kind of practical on the side of things as far as what that should look like and what you believe in. Yeah, please go ahead.
Sorry.
So
yeah, I don't have any particular thoughts. Just that I think current plans are to expire state after a year or so, and
Sure.
then you'd need some other way to get the state.
My understanding is there will be, zero knowledge proofs that will be able to construct that and prove that that's true. But then you'll also have, so you're kind of using the same different technology, but I'm not going to speak too out of turn on what I don't know a ton about. It's a great question though. I can look into it and get in touch with you about it. I think there's one over here if he still has this question. Please. I think it's too late. Thank you very much, guys.
Thanks, Brian. Our next session starts in 2 minutes, so
thank you very much.
Find your seats. welcome back. Our next speaker is Chance Hudson, and he'll be talking about how to build an identity ecosystem on Unirep. And Unirep itself is an anonymous reputation system. So, Chance.
Thank you. All right, so thank you all for being here. Whoops. I'm excited to talk to you guys today about a protocol I work on called Unirep. So before we get into it, this is a quick roadmap of how this presentation is going to go. First, I'm going to give a semi-technical overview of what Unirep, the protocol, is. Then I'll talk a little bit about improving the user experience of ZK and blockchain applications in general. And then I'll talk a little bit about how we can scale ZK on the blockchain and sort of where we're at with the capacity right now. Right, so let's dive into it. Unirep is short for Universal Reputation, and you can think of it as two different things. First, it's an identity system that gives you anonymity, and it does this by creating public keys that change over time. The second component is this attestation system. Within the system, we have attesters, which you can also think of as applications or just smart contracts, and these attesters give reputation to users. And you can think of an attester to reputation like ERC20 contracts to tokens. They create the system, define how the reputation is distributed and spent and destroyed and everything like that. And so we define reputation as two different integers, positive and negative reputation. And we do this so we can represent negative reputation, like net negative reputation, in ZK proofs and in smart contracts without having to deal with signed integers or wrapping around unsigned integers or anything like that. So that's one component of the user state. The other is this graffiti value, which the attester can use for anything they want to within the application. And this is just 32 bytes. And yeah, the attester can use it as they like. And so one example use case of this is an attester can allow users to register a username. And so the user requests a username, and then the attester attests giving the hash of the username as graffiti to the user. Now, when the user takes an action or makes a proof, they can prove the pre-image of the graffiti and move from anonymity to pseudonymity. So that's one example use case that's relatively simple. A more complex example would be storing the state root of a Merkle tree inside of this graffiti. And then the attester can extend the ZK proof system to prove things about the contents of that tree that's in the graffiti. So for example, they could use an incremental Merkle tree to give achievements to the user or to track actions the user has taken, anything like that. So very extensible system. So the two main properties of Unirep are anonymity and non-confidentiality. That means we can see everything that's happening inside of the system, how much reputation is being transferred and whatnot, but we don't know who's doing what. So let's talk a little bit about the Unirep identity system. We build on top of a system called Semaphore, which is also developed by the privacy and scalability team. And with Semaphore, we have this public-private key system. That's the most simple explanation. It has two secrets, a trapdoor and a nullifier, and we define a public key as the hash of those two secrets. We also call this an identity commitment in Semaphore talk. And we use the Poseidon hash function to calculate these values, which makes it a ZK-friendly protocol. And that means that you can extend it to do arbitrary things. So in this example, we have just a public-private key system, which isn't particularly useful. But using a ZK proof, you could extend it to do signatures, for example, by writing a proof that proves the secret values, as well as the hash of some data that you want to sign. Yes, you can extend ZK proofs in arbitrary ways like this. Another way you can extend it is by building something like Unirep. So we have these public keys that change over time, and we call these epoch keys because they're valid for the length of one epoch. And this is some amount of time that is set by the attester in question. And so the epoch key is the hash of the nullifier, attester ID, epoch, and nonce. And so as you can see, because the epoch is part of the hash, it changes every epoch. We also have this nonce value, which is a value between like 0 and 2 by default. And it allows us to give the user multiple epoch keys for a single epoch. So if a user wants to commit an action and then wants to commit another action but doesn't want to link their identity between the two keys, they can use different epoch keys and still be able to prove the same amount of reputation and whatnot. And just like Semaphore, this system is ZK-friendly and therefore extensible. So if you wanted to make a signature system using these epoch keys, you would use the exact same approach where you prove control of the nullifier and the public signals, and then you pass in whatever you want to hash, and it all gets output. Yeah, so now I want to talk a little bit about data structures that we use in UNREP. So we have like this identity system, but how do we assign reputation and graffiti to users in the system and then like continue to prove it? So we really have two structures. We have this state tree first, which controls or measures whether or not a user is a member of the current epoch. And as you can see, it's an incremental Merkle tree that we store completely on chain. And the leaves themselves are the hash of this private identity nullifier, the attester in the epoch, and then the reputation the user has at the start of the epoch. So this tree has leaves that a user inserts into when they join the current epoch. So for example, when a user signs up, we insert a leaf, or the user makes a ZK proof and then creates a leaf with 0 positive and negative reputation because they're just joining the system, so they start with 0. The other structure we have is what we call an epoch tree. So the state tree tracks the starting balance for the epoch, and the epoch tree tracks the amount of reputation that was received during the epoch. And as you can see, it's a sparse Merkle tree, and we store only the root of this tree on-chain. And we use ZK proofs off-chain to insert and update leaves in this tree, and then we just post the new root along with the ZK proof to the chain. And you can see that the leaf values in this tree are the hash of the total reputation owned by this epoch key. And so we determine the index of the user's leaf in the tree using the epoch key. So in the previous slide, you saw that the epoch key is just some hash of some arbitrary data, and we're able to we're able to determine a leaf in the tree by taking the modulus of that hash across the number of leaves in the tree. So if we use this exact tree, we would take the hash modulus 2 to the third, because it's only 3 levels deep. But of course, if we did that, we would have lots of collisions. So when we operate this tree in production, we use a depth of 128. So we take the hash modulus 2 to the 128th, and now everyone gets a unique epoch key, and we have 128 bits of collision resistance. So the whole idea behind UNREP is users have these identities that are valid for an epoch, and then at the end of that epoch, they pack up their reputation, and they move to a new identity in the next epoch by inserting a leaf into the new state tree. I didn't say this before, but we have a copy of these trees every epoch that we use. Right, so let's change gears a little bit and talk about the user experience for zero-knowledge applications. So we have these proofs with UNREP, and we want the user to be able to make these proofs inside of like their browser, for example, on a computer. So here we have a graph of the proving time for proofs of various sizes on a few different devices. And yeah, you can read it pretty well. So you can see that there's a sweet spot below 30,000 constraints where any proof you make is going to take less than 5 seconds on most modern devices. That purple line at the top is an iPhone from like 2016. So like older mobile devices can still do that in less than 10 seconds, which is pretty acceptable performance. So where's UNREP, where are our proofs on this graph? The first proof we have is a sign-up proof. It's very small, it's 700 constraints, and all it does is output a hash value. So less than 1 second. A little bit bigger, we have an epoch key proof. This proves control of an epoch key and also proves a leaf in the state tree. So it's a little bit bigger, 3,000 constraints, still less than 1 second on most devices. And then way over here, we have this user state transition proof. And in this proof, we add up the value in the state tree leaf, as well as the values in all of the epoch tree leaves, and output a new state tree leaf with the sum of the reputation the user owns. So we have to do multiple Merkle inclusion proofs over trees that are quite large, but we still end up with about 29,000 constraints, so less than 5 seconds on modern devices. And we can also execute this proof in the background so the user doesn't have to know about it and doesn't have to wait. Right, so I think a good goal for ZK applications and for blockchain in general is users not being aware that they're using the blockchain while they're using the blockchain. So a lot of you probably use websites or applications like Spotify or Twitter or Reddit or Stack Overflow. Just raise your hand if you know what kind of database those applications are using. Right, no one raised their hand. Okay, one person raised their hand. We have at least one nerd in the crowd. But for the most part, users don't really care about the data structures that are backing the applications they're using. And blockchains are really the same. They're just databases with different properties. And so the user shouldn't have to be aware that they're using the blockchain. So this is the architecture of a traditional dApp. And as an engineer, I really like this architecture because it's simple and it's sort of unprecedented before blockchain. But for the reasons that I like it, I think that users kind of hate it because they have to learn about the blockchain, and then they have to learn about wallets like MetaMask and transactions and gas prices and Gwei and Ether, and they have to get Ether. And it's a whole thing, and it's a lot for them to learn just to use a single dApp. So luckily, if we use ZK identities instead of wallets, we can build this more traditional 3-tier architecture where we introduce a relay that bundles the transaction and sends it. So the flow would be the web app generates a ZK proof, gives it to the relay creates a transaction, and then posts it to the blockchain. And the economics of why the relay would do this are there are a lot of different schemes you could build, like subscription models or just like free trial models, all sorts of different things you could do. And so one note about like this architecture, the relay is not a trusted entity. The relay can censor transactions that can go offline. It doesn't matter, the web app or the user can always send their ZK proof with a different relay or broadcast it to the blockchain themselves. The relay also can't compromise the ZK proof itself because if they change anything about it, the proof itself will be invalid. And the proof determines what the user wants to do on chain. So I think a good goal for this would be, from a user experience perspective, a user clicks a button, and then in less than 5 seconds, we show a loading animation, and we generate a ZK proof, give it to the relayer. The relayer then packages it into a transaction and gives it to an L2 node, who then returns an instant finality guarantee. And at that point, we can stop the loading animation on the front end and say, OK, your action is complete. And even if we get a weak economic guarantee from this L2 node, we can still do this on the front end and then have an alternate code path where if the sequencer doesn't include the transaction, we show a notification saying, oh, this action failed, or do you want to try again or not? And hopefully that code path is relatively cold and sequencers include transactions as they say they're going to. Right, so how can we build an ecosystem using like ZK proofs in this sort of abstracted architecture? One approach, I think, is sort of detailed in this diagram. You can see there are 3 different attester applications and a user's browser. And each attester application is managing a unique identity for the user inside of the browser local storage. And the advantage to this is we can treat these identities more like Web2 authentication tokens and less like Bitcoin or Ethereum private keys. So instead of prompting the user for permission to do a signature or make a transaction, we just, in the background, make these ZK proofs and give them to the relayers. And at the same time, when we use different identities for each of these websites, if one of the identities gets compromised because the website injects some malicious JavaScript or does something like this, the damage is contained to that single attester. But at the same time, we want attesters to be interoperable. So if, for example, this review attester wanted to get a proof from the cyber resistance attester, how could we do that? And the answer is basically OAuth for ZK. So in this example flow, I'm trying to sign up for this review attester, and the review attester wants a proof that I am a human being in the form of a reputation proof from this cyber resistance attester. And so in this flow, I create the sign-up proof from the review attester, and then I get redirected to the cyber resistance attester, and I get prompted to make a proof from this identity. And in this case, we shouldn't operate silently. We should definitely request that the user make this proof because we're going to hand it to a different third party. And so if the user says yes, then we prove that we have like the reputation, and we sign the hash of the sign-up proof to prove that we're the same person. And then we get redirected back to the original application, and we can continue sign-up. So using this flow, we can get ZK proofs from different applications into different sort of origins. OK, so this is part 3 of the presentation. How can we scale ZK? So first, I want to talk about like where we're at right now and the limitations of our current infrastructure. So when we talk about scaling ZK, there's 2 limitations. One is the call data itself, and 2 is actually executing the verification on-chain. So let's talk about call data first. So for Groth16, we have about 130 bytes per proof, and for Plonk, we have about half a kilobyte per proof. So assume that we're talking about EIP, like a post-EIP for a world, and we have 2 megabytes per block that we can use for blob data. So at that point, we're able to do 1,300 Groth16 proofs per second and 330 Plonk proofs per second. That's not terrible. So let's open door number 2 and look at the verification costs. So Groth16 and Plonk both cost about 250,000 gas to verify. This isn't totally true. Groth16 is a little bit cheaper, and they both scale up with the number of public signals in the proof. But for this example, we're just going to say they both cost 250,000. So the Ethereum mainnet is doing 2.5 million gas per second right now. They're doing 30 million gas every 12 seconds, which comes down to this. So we get to verify 10 proofs per second on Ethereum mainnet. So on Arbitrum and L2, for example, they're doing 7 million gas per second. So that number is bumped to 24 proofs per second. So we see an obvious bottleneck here. It's the verification cost on chain. And these numbers are also extreme upper bounds. This assumes that we're filling entire blob blocks with 2 megabytes of ZK proofs, and we're filling entire blocks with verification of ZK proofs, and not even factoring call data. Right, so how can we scale Unirep, and how can we scale ZK proofs in general, given those bottlenecks? So this is a proof from the Unirep system where we're generating a user state transition. And as you can see, there's, I think, 7 public signals. And for every user that wants to join a new epoch, we make one of these and put it on the blockchain and verify it. So how can we make this a little bit more efficient? We can do recursive proofs. So we have the user make a proof, and then it gets sent to an aggregator, and then the aggregator proves that 4 proofs are valid and outputs 1 proof, and so we're able to reduce it by, in this case, a factor of 4. There are other things we can do, like to reduce the public signals as well, like queue the ZK proofs on chain, and then form a hash chain of the public signals and the proof stuff to reduce it so that we don't have to output all of these public signals at once, which will also reduce the verification cost. And so recursive proving is really important because it changes the approach from scaling the throughput of decentralized network to instead scaling off-chain computational power, which we're much more able to do. Like Intel and AMD do this every year. We can also build ASICs to make proofs very quickly. And then we're able to see the sort of improvements that we want to see. Like if we're able to bundle 10 proofs at a time, we get a 10x improvement, 100x, et cetera. And this does introduce a little bit of complexity because we have to deal with a proof aggregator, and now the user potentially has to like wait on that or potentially optimistically evaluate the aggregator. But this is a decent approach to scaling. Right, so now that's most of the presentation. I'm just going to talk about like some attester ideas that I think are kind of cool that we can build with Unirep, or yeah, the Unirep protocol. So the first is just like ZK DAOs. We can keep the balance hidden, or the balance controlled by a user hidden within the DAO. We could also do things like vote for proposals anonymously. A lot of interesting ideas, or a lot of interesting things that can be done with this. The next is anti-Sybil reputation. I used this as an example in one of the previous slides, but what you could do is basically take like proofs that you have a Web 2 identity and give reputation for that, or potentially use like BrightID or proof that you have like POAPs, for example, and just get reputation and then use that to sign up for other attesters. The third is like really simple and generic, but just a recommendation system as a web app. Everyone has things that they use or that they would want to recommend to other people. Having like reputation for good recommendations seems like a good use of the system. And then the final one is one that I thought of when I was given the Devcon POAP. I really hate claiming POAPs on chain because I'm just giving people a history of like the places I've been in the real world, which I think is kind of weird. So we can use Unirep to like claim POAPs anonymously, and then we could make a proof that you have like a POAP in a set. Like for example, I could prove that I have 2 POAPs from the set of all Devcon POAPs, something like that. And then just some nice to have things for sort of the ecosystem, like infrastructure-wise. The first is like a ZK directory. This just a directory of the hashes of proofs and human-readable descriptions of what the proofs do. And this would be really important if we're going to OAuth between different applications and request ZK proofs, because they're potentially requesting just random proofs that are specific to their application. And so applications should have a place where they can request information about a proof and then return it to the user. The next thing is Plonk. We already have this, but I just want to talk about it a little bit more. The most important part of Plonk, to me at least, is we don't have this phase 2 trusted setup that is circuit specific. So with Unirep, we want people to extend the proofs that we've written and write their own to build their own functionality. And with Gross 16, that's very difficult to do because they have to run a trusted setup ceremony for the circuits that they build. And this is a huge amount of coordination and effort you can't really expect most developers to reasonably do. So with Plonk, we cut all that out. We get to just use some phase 1 trusted setup made by some trusted entity or some trusted entities, and then you have secure proofs. And the last thing is easier browser proofs. So we have proofs in the browser using Snark.js, but you have to like configure Webpack really specifically, And it also uses like Zkey and a WebAssembly file and a second WebAssembly file for a curve. And it would be much easier if we had a tool that just sort of bundles all of that into a single WebAssembly that we can run in the browser. Just pass in the signals and get the proof back. This would give us like free asynchronous operation as well. Yeah, it would just be a nice thing to have. Yeah, that's pretty much the end of the talk. We have a few events happening related to Unirep. So first we have a Unirep workshop on Friday at 10:30 a.m. That's going to be on the first floor at the ZK Community Hub. We also have a demo at Thursday at 3 o'clock in the same place. Big thank you to 0xPark for putting on those events and inviting us to participate. And then if you want more information about Unirep, you can go to github.com/Unirep, or you can scan this QR, and it'll take you to our organization homepage where you can find documentation links, links to our Discord, and a link to a demo application that we have running on this protocol. Yeah, that's it. Any questions?
First of all, cool presentation. Thank you for all the information. I was wondering from a product standpoint, or maybe from the user perspective, how do you explain the need to sequentially create new identities in order to remain anonymous? And also if there's a way to abstract that, maybe save it in the session, in the browser, you know, abstract the user away from such an involved mechanism of creating like a pseudo-anonymous name every epoch.
Sure. Yeah, so the reason we do this is because they need to have, they need to be able to prove a leaf in the epoch tree to claim reputation. But I would say it's not as involved as it might seem. We can do this silently in the background in the browser. So like the user enters the web page, and then the web page checks if they need to generate a new identity. And if they do, they generate a ZK proof in the background and submit it to a relayer, and it's done. Yeah, there's not a way to make that less manual without changing the architecture of the system like pretty substantially, though.
Hello. So how often do you see the state transitions happen? Is it going to be per epoch, or maybe there can be some trickery there to maybe avoid this heavy load in computation?
Yeah, so the state transition happens anytime you want to move to a new epoch. So if you are participating consistently, then yeah, it's every epoch. We can adjust, or testers can set the epoch length themselves, though. So this could be like pretty short, maybe 1 hour, or it could be like a week, or it could be a month, anything like that. And we're also planning to make it so testers can set the max nonce value to change like the number of keys the user has per epoch. So that would sort of make it so that the epoch key proof is longer, but you also have like longer epochs. So there's sort of a lot of tuning we can do with that.
Any thoughts about using DIDs and VCs standards in this implementation?
Any thoughts about using what?
Decentralized identifiers and verifiable credentials from the W3C?
No, no, I'll have to look into that. I'm not aware of actually that, but thank you for that.
Okay.
Quick question. You talked about Groth16 verification after EIP 4844. I would be curious to understand if you have like more detailed thoughts. In particular, two questions I was thinking of was like one, if you don't have your, I guess, proof in call data and instead it's in the blob, you would have to verify either some batch proof, right? Opening your Kate polynomial inside a snark and then doing recursive proofs? Or I guess what is the exact setup you're thinking of?
Do you mean Groth16 or do you mean Plonk?
Either one, I guess.
Right. So, sorry, the mic's a little bit hard to hear, but it's just like a question about how do we aggregate these proofs or how do we sequence them for aggregation?
In a post-EIP 444 world.
Right, yeah.
The right way.
Yeah, so I sort of touched on it a little bit, but I didn't talk about it much. But one approach is users can send the public signals of the proof and then the hash of the proof onto the blockchain, and then we form a hash chain on chain, and then the aggregator is able to make a recursive proof using that data and only put a hash chain on chain. But this still involves like the aggregator receiving the full proof and then like calculating the hash. We honestly, we haven't gotten, we're not really close to doing that yet. Like we're Plonk proving, especially for like solidity provers, are a little bit far out. But yeah, it's probably going to be some sort of optimistic system so the user experience is pretty good. Thank you. Thank you all.
Welcome back. So up on stage we have One Sob, and One Sob's gonna tell us about ZK Opera and the journey and the public goods and experiments that they've experienced in the course of developing ZK Opera.
Hello, everyone. Thank you so much for joining today's talk. Today's talk is mostly about the public goods and experiments. So it is very for beginners. I think you don't need any knowledge about some ZKP or some difficult math. So I think you can just listen my talk very easily. Okay, so let me start the talk. So today, a lot of our PSC team members are having presentations at Devcon. I've been in this team from 2019, and actually today, I want to share my experience during the team. I'm sure that we've been keeping our own ethos pretty well from 2019. I can say like our ethos, I mean PSC team's ethos is focusing on public goods and doing experiments. Let me rephrase it. We do public goods that others will never do if we don't do. And we do experiments because sometimes experiments are expensive and they are not, it is not affordable for some other teams. But actually, it was pretty hard to keep the faith. I mean, because there are so many fun things in the Ethereum world. We had gone through the DeFi summer, NFT boom, and maybe if you are some technical guy, you can launch a layer network something. So our team has been working with a lot of talented and outstanding people. But during those summer seasons, we could see that many of our friends, close friends, becoming millionaires, some of them like billionaires. And actually what we are doing in the team is kind of a very difficult thing and also one of the most advanced technologies. So maybe a lot of the teammates could get some very big rewards if they go to market. So many people left the team. So in the team, there are left only some types of people. Someone who really loves the cryptography research and the achievement, or someone who truly loves the public good. And maybe someone like me who has a strongly aligned value with the team. So today I want to share about my case. Actually, this is kind of a personal stories. I just founded a startup in 2012 with my friends, and actually it was acquired by another a little bit bigger startup in 2014, and I swapped all my equities to the new one. And after the acquisition, I tried to work very hard there because I swapped all my equities to the new one. But I felt most of the other team members were not like me. And I just found that, oh, yeah, I think there is some incentive problem because the founders have like more than 50% shares. And just imagine how much you can give to the 10th member if you're a founder. It's like, I guess, less than 1%, usually like 5.5%. Then actually it's kind of 100 times, it's kind of exponential, smaller incentive for the teammates. So yeah, actually that was what I found. And just to disguise this incentive problem, founders usually should have to do lots of sweet talks to motivate the team members. And for me, these kind of situations were pretty exhausting. So yeah, actually, I'm not saying that founders are greedy, because founders should take all the responsibility to build a product and to build a company. actually, it pretty works well for some rocket speed venture companies. But for me, it was very exhausted. So from that time, I just started to explore open sources and getting deeply into that culture. So, and interestingly, what was very inspiring to me was the contributors are giving up their commercial incentives of their source code. And in our society, source codes are the most powerful means of production. Doesn't it sound like very communistic? No worry, I'm from South Korea, not the North. So, yeah. By the way, there is a very, very big difference. That is freedom. In the open source society, the contributors give up the commercial incentives of the source code by their own freedom. And we do that to run the software and to study the software and modify the software and share the software by our own freedom. So this value-driven community was so fascinating for me, and because it was very, very totally different with the startup community that I was in before. So, and I just started to get to know about the value of sharing. And then finally, actually everyone knows which community is the most crazy value-driven community. Yes, we are. Yes, we are. Ethereum is the world of freedom by the Ethereum people, where we can do everything by the code. I just dived into this world and just to enjoy and explore the freedom with this lovely community. As a result, throughout a few years of journey, now I am doing the public goods and experiments for the freedom in the team. Yeah, maybe now it's a time to talk about Zico Pro. Yeah. By the way, then what kind of freedom I'm talking about here now? Let me give you another story. Once I traveled with my friends before, I just sent stable coins to my friends to split the bill. And actually, my friend just added my Ethereum address to the watch list of the Etherscan. And when my MakerDAO position got liquidated, he just messaged me, "Oh my God, where's my freedom for the privacy?" So actually, this was the start of the Zico Pro project. So I started to write a privacy protocol to keep my right to be free from unwarranted publicity. At first, I just tried to implement some Mimble protocol in the Ethereum, just as a layer 2 protocol, using optimistic rollup. Mimble is just a simple Schnorr signature application, but because of that, it couldn't hide the transaction graph. And also, it had some problems like it needs an interactive transaction building process. So from 2019, with Barry, I started to write a new specification to implement Zcash on Ethereum, just using the optimistic approach. So we achieved pretty low gas cost, cheap transaction, and also the compliance compatibility using the spending key and viewing key of the Zcash scheme. And a lot of people and teammates contributed to this protocol. Barry, Chance, Weijie, Kobe, Thor, Jeff, Jean, Rachel, Takamichi, Charlie, Gio, Kimi. A lot of people contributed to this protocol. So finally, we could ship this protocol in 2020, our first version, and we could ship the second version in 2021. During the development, we had a lot of discussions about the growth strategy. The first option for us was about just spinning out, just like ENS team. But when we thought about our philosophy that we do public goods and researches what others will never do, what others never do if we don't do, in this point of view, actually spinning out didn't make sense that much because already many teams like Aztec, Tornado, Polygon Nightfall, and a lot other teams were already trying to ship the private protocol. So then what's the thing that others will never do? So because other teams have their own shareholders, and because of the many things should be related to the business stuff. Therefore, sometimes the source code also becomes the means to maximize the profit only for some people. So what we've decided to do is shipping the reference. We ship the reference specification, and we ship the reference implementation. And also we ship the reference example applications on top of our protocol. And what we do is encouraging you to fork our reference and ship your own thing for your own target customer, because we believe the power of open source. And we are very ready to help you, everyone who wants to fork and ship your own product. This is how we think about the public goods and our own ethos. To be more detailed, actually there are some reasons, good reasons that you need to fork ZK-Pro. The first thing is like ZK-Pro's goal is just seeing everyone uses crypto payment in our daily lives, like when you pay at a restaurant. But when you pay at a restaurant, if we have the private transaction, the government cannot tax you. So we need a compliance compatibility. So if you ship this protocol for your own country, then actually you can ship a great crypto payment network for your own country, which is pretty big business, right? However, because the current version 2 is pretty outdated compared to the recent advancement, we are going to write new specification with everyone. So we are looking for participants who will join this journey together. So what we are going to do to write the new specification is like the first, for the new specification, we're going to include a recursion scheme and a better membership proof scheme. Also, we're going to support various types of token. And also, for the consensus part, we're going to use hybrid finalization scheme using ZKP and also optimistic approach. And then we're going to ship the reference implementation. If many parties join this journey, then maybe PS team might do only some coordination, just like Ethereum 2.0, I mean the consensus layer. And we're going to ship the ZK-Pro to the public. And we want that other commercial party do this together because we won't do the commercialization. Yeah, so it's almost end of the talk. Today, I am very, very happy to share our PSC team's own ethos and our own culture with you all. So I just want to define, because this is my personal opinion, I just want to define PSC team's own ethos as we do public goods that others will never do if we don't do. And we do the experiments, which is not affordable for many teams. And also we work for value of Ethereum, personally, which is freedom. Okay, thank you everyone. This was my talk. Thank you so much. Any questions?
Is this working? There we go. Thank you for the talk. Not super familiar with ZKO Pro, but when you say it's intended to be forkable, do you envision, I guess I'm curious what you see as like a project potentially forking it? Like, is it an application specific, or is it like a potential layer 2 project looking to like build off your stack as like a foundation for their L2 or L3 or beyond?
Yeah, actually, we are trying to focus on the examples. Like the first one is actually, we are trying to many experiments. The next talk from Takamichi is about the experiment we are doing, which is kind of private exchange. So because using the private exchange, we can prevent the map. Actually, we are not sure that it can be usable for just like Uniswap, but we are just doing these experiments if others wants to use it. And also the other example that we want to see is the merchant service. So shipping the crypto PayPal or shipping the crypto Shopify on top of Zcash Pro, because Zcash Pro has a private atomic swap feature. So you can exchange an NFT, which is a digital good, with your token. So this is the examples that we want to see, and maybe we are targeting these users.
Great talk. Just one quick question. I was curious if you have any thoughts on Polygon Nightfall or other sort of more commercialized versions of Zcash Pro.
Yeah. Actually, we were very, very happy that when Nightfall team launched their project, because they gave us a credit. They just said they inspired from our project. So actually, that was kind of our first achievement in terms of our ethos, like because we want to ship the reference, and actually Nightfall team inspired by us and shipped the project. So we were very, very happy. And actually, including Polygon Nightfall team and any other team, if any team wants to work together, then we are really happy to ship the reference, specification, and implementation together.
Great talk. I just want to ask, how do you achieve a balance between experimenting and not wasting resources while still preserving those resources and trying to maximize the innovation that comes out from that? And thank you.
Yeah, maybe I think that our support designer, Rachel, might be a very good person who can answer this one, because we were trying to do a lot of that we can do some experiments without shipping it. We can do some experiments with some papers, right? So we are trying to do some methodologies like that, and our designers are doing that really well. So I'm really happy for it. Okay. Thank you, everyone.
We'll be starting up again in 10 minutes, so see you back here. Welcome back. So we have with us Takamichi Tsumi, and he's going to tell us about a private exchange application that was built on top of ZK Opera.
Thank you for coming. My name is Takamichi. Today, I'm going to talk about the private exchange. Yes. I'm software engineer at the Privacy and Scaling Explorations team at Ethereum Foundation. And yep, today, I want to explore a privacy-preserving decentralized exchange on ZK Opera. For this project, we are aiming for more private peer-to-peer exchange system. And private exchange consists of 3 different zero-knowledge protocols to protect users' privacy. And in this talk, I'm not going very deep on the technical details of the protocol, but I will show how those protocols works and how the protocols are used in private exchange. All right, before diving right into the private exchange, let me start with one question. So, why do we need privacy? I think there are many reasons for many different people and for many different use cases. So I'd like to share my opinion on this today. The privacy is important because it can contribute to censorship resistance. Like on public blockchain like Ethereum, like the transactions on all the transactions on the blockchain are all visible to everyone. So it can be censored, mostly like in the smaller networks. Because the number of the validators and the block builders are relatively small, so the censorship likely to happen more often. For example, if you want to spin up a minor rollup on Ethereum, this is the case. And for second, it also can mitigate the MEV or front running. If the privacy of the transactions can be kept at work to prevent the MEV and front running. But most importantly, it is a human right. The privacy is a human right. Here is a quote from the Universal Declaration of the Human Rights in Article 12. So my opinion is we don't need any reason to work on protecting privacy. We need privacy because it's human rights, and we should care when we're building an application. And today in this talk, I will walk you through how we approach to protect privacy when building a decentralized application like private exchange. All right, let's get into the interesting part. What is private exchange and how it works? So what we are trying to achieve with the private exchange is to make exchange process more private. Yes, very simple. And don't let users to expose their information or intentions. That's our goal here. So what exchanges do? Exchange let users exchange their tokens. In this diagram, Alice sends 1.0 ETH to exchange and gets 1,500 DAI in exchange. There are more functionalities, but I'd like to focus this one function today. And there are 2 popular constructions in decentralized exchanges today. The first one is automated market maker. In this kind of exchange, users can exchange their tokens without a counterparty. This means that Alice just interacts with a smart contract and doesn't need to anyone else doing an opposite trade. The price is calculated automatically in the smart contract, and Alice can exchange tokens on that price. The second approach is an order book. In order book, Alice posts something called an order to an order book, and the order contains information such as token pair, amount, and a price. In this example, Alice wants DAI in exchange of ETH, and the amount she wants is 1,500 DAI, and the price is 1,500 DAI per ETH. And if there happens to be some other order by Bob who wants to do the opposite trade, sending 1,500 DAI for 1 ETH, then the order book attempts to match the orders and executes the swap transaction by sending transaction on-chain. And one thing to note is that order books can be on-chain or off-chain. If the order book is on-chain, Alice posts an order to the smart contract order book, then Bob finds the order on the smart contract and takes it by sending transactions. And if the order book is off-chain, there's typically some intermediary order book provider that collects all the orders and trying to match the orders. But in either way, the orders Bob and Alice sends includes the information that order book provider or smart contracts can find a pair. Okay, now it's time to think how we can execute the process more privately. In order to make exchange process private, we come up with a relatively simple peer-to-peer exchange system. And it is somewhat similar to an order book construction here, but it tries to keep information private as much as possible. So let's look at the order book diagram again. Here we can see the parts that are not private in this diagram. The contents of the orders Alice and Bob sends to the order book are not private. And the transaction that order book sends to the blockchain is not private. So how do we make this more private? Here we use 3 zero-knowledge protocols: blind find, and socialist millionaire problem, and zk-oproo. Okay, firstly, let us think of how we can make orders more private. In the order book system, order book is the one who collects all the orders from users and make matches. So Alice and Bob needs to send the order data to the order book provider. But if they can compare prices and make a match in more P2P way by directly sending messages to each other, then they don't need to reveal the data to the order book provider at all. But wait, how does Bob reach out Alice in peer-to-peer network? We use blind find protocol here. Blind find is a network that peers have neighborhood lists, and Bob can look up Alice. and prove that he can reach to Alice in the network. But importantly, Bob can search for Alice in the network, but without revealing that Bob is the one who is searching for Alice. So the neighbors that receives a message from Bob will never learn that Bob is the one who is searching for Alice. So in this way, Bob have like some privacy of that. He have some intention to take the Alice's order in the public board. Now, Bob can reach out to Alice to execute the peer-to-peer order matching. Thanks to the socialist millionaire problem here, we can do the private peer-to-peer order matching. Socialist millionaire protocol is used to check the equality of two values, but without revealing the actual values. So the idea is that they have some numbers in mind. Let's say Bob have X in mind and Alice have Y in mind. Then they don't directly send in the original values, but instead they derive some values by calculating some mathematics, and also they use some random values and exchanging messages. Then after the exchange complete, they can test that if the original values that Bob has in mind and Alice has in mind are same or not. But here, Bob cannot calculate back using the received value to Y, and Alice cannot calculate X from the derived messaging values. And we use this protocol to check if the prices that Bob wants and Alice wants match or not. And here's how things work in private exchange. So firstly, Alice creates information to public board, but without a price. We call this an advertisement. And Bob finds the advertisement on public board and search Alice in the blind find network. If the price matches, they proceed to create transactions. In this way, we could omit the intermediary who acts as comparing the price and making a match and preventing posting the prices they want to public. Now, the order is partially private because they can post an advertisement without a price. And now, we should think about how we can make these transactions, right-hand part, private. So here comes ZK-Oproo. ZK-Oproo is an abbreviation of zero-knowledge optimistic rollup. We use ZK proofs for privacy and optimistic rollup technology as a layer 2 technology protocol. And in essence, we can make secret transfers with cheap fees. We can prove that those transfers are valid using ZK proofs, but without revealing the contents of the transfers. But there is another thing. A secret atomic swap. So there is a feature called atomic swap on ZK-Oproo. And let's say that Alice and Bob agreed on some price using socialist million problem, and they can create, they want to create the transactions called atomic swap. Atomic swap transactions are a pair of transactions and has to be included in a same block. So in this case, Bob sent Alice 1,500 DAI, and Alice sends 1.0 ETH to Bob. The two transactions have to be included in the same block. And if not, it's not valid transactions anymore. And of course, the transactions contents are secret. Even block builders called coordinators cannot see the contents of the transactions. So using the secret atomic swap, the transactions sent on the blockchain is private now. So here is a diagram, complete diagram of the private exchange. All right, so let's go over the private exchange flow again. So firstly, Alice and Bob joins the network called Blind Find so that they can reach to each other, but without revealing that they are finding someone in the network. Next, Alice posts an advertisement on the board, but without a price. And next, Bob finds the advertisement, and Bob searches for Alice in a blind find. If they successfully, Bob finds the Alice, he starts executing socialist millionaire problem to compare the price that they want. And if the price are same, they can create atomic swap transaction and send it to ZK Opru. In this process, advertisement is partially private, and price matching is done privately, and peer finding is done privately, and transactions contents is also private. So, what I've talked today is one simple example of a privacy application. And what I talked was, firstly, I started with what does this application do? So in our case, it is an exchange. So the exchange let users to exchange their tokens. And in that process, which part of the exchange process should be private? In our case, it is an orders and transactions sent on chain. And lastly, I talked about how to make those informations private. We use 3 zero-knowledge protocols, Blind Find, and Socialist Millionaire Problem, and ZK Opru. And as a result, the private exchange does not reveal transactions content, and it does not reveal price of the orders to public, and it also does not reveal the peer-to-peer routing in the network. But at the same time, there are challenges in these constructions. Firstly, socialist millionaire problem can check the equality of the values. Therefore, it's not easy to compare, for example, to use a range to create a match. So in the application, it's harder to find the counterparty like Bob if the SMP can work only this way. Secondly, an advertisers needs to stay online while waiting incoming socialist millionaire problem messages. So Alice, after sending advertisement on public board, she has to stay online until Bob shows up. And finally, users need to join blind find network before starting the process, and also run the blind find process while in the application. So these are the challenges, and it directly affects to the user experience of our application. But some of the challenges can be mitigated on the application layers, but some other needs improvement of the cryptographic protocol layer. So in privacy and scaling explorations team, we do many privacy projects like applications and also cryptographic protocols to improve privacy in this blockchain space. If you're interested in those projects, please take a look at our homepage and Discord. And I want to give a shout out to the ZK Opera team, Wonsap, Jane, Kimi, Gio, Chance, Chelly, Rachel. Thank you. Questions, please?
First quick question, is the SMP interactive or non-interactive?
It's interactive.
So you have to basically, so like if there's a list of N advertisers, a user will have to communicate with every advertiser, right?
Yes.
So this doesn't really scale well as N increases. Is N squared like complexity for?
Yes.
Okay.
So that's yes, that's also our UX challenges as well.
Yeah, sort of on the same vein, one question I had was, because, you still have to do the SMP to find the price, you sort of know a general idea of the price because you have other markets that you can measure the price from. And so is there any prevention mechanism for like a mass de-anonymization of the price, the ads, in a way that somebody could just keep trying to discover the price and build up an order book that sort of matches the expectation of the ads, because there's no obligation to actually trade on any of these ads, right? So you could just try to brute force, figure out the actual order,
Yeah. So for current implementation, we don't have like such features, but as you said, it needs like the many times of SMP trial to find the price matches, and also we don't have like to prevent such DDoS like types of attacks right now. So yeah, we need to work on that UX implement as well. Thank you.
we'll be starting back up in 6 minutes. See you back here in 6 minutes.
It's one of those times in life when you just know that it's right. It's one in a lifetime. For the first time in my life, I'm right on the edge now. I'm looking down. No matter how hard I try, can't see the ground. I'm on the edge now, taking the leap, taking a chance. 'Cause all I need from you, my angels, to catch me when I fall for you. All I need from you, my angels, to listen to your heart. 'Cause all I need from you, my angels, to catch me when I fall for you. All I need from you, my angels, to listen to your Baby, you know that I will give it all I've got. I'm losing control tonight, but I hope you'll do what's right. I'm right on the edge now, I'm looking down. No matter how hard I try, can't see the ground. I'm on the edge now, taking the leap, taking a chance. 'Cause all I need from you, my angels, to catch me when I fall for you. All I need from you, my angels, to listen to your heart. 'Cause all I need from you, my angels, to catch me when I fall for you. All I need from you, my angels, to listen to your
Welcome back. Next up, we have Uri Kirstein, and he'll be telling us about the different ways formal verification proofs can go bad. So, Uri?
Hello everyone, I am Uri from Certora, and today we're going to talk about bad proofs in formal verification. Many times people think of formal verification as the holy grail or highest insurance against bugs. And yet sometimes we still see that even projects that have been formally verified still contain bugs. For example, this is a high-profile case where we in Sortora have formally verified a specific thing about one of our customers, and it still contained a bug in deployment. In this lecture, we're going to see how that is possible, how it happens, and how can we prevent that. In general, the lecture is going to be divided into a few different parts. At first, we will say what is formal verification, what are the proofs that you get out of it, and what does it mean for a proof to be bad. Then we will showcase two different types of bad proofs, and we'll also show you how you can sometimes tell if a proof is bad or not. And at the end, we'll show you a real-life example, the same example I've shown you on the previous slide. We'll delve into it deeply and understand it. Let's go. Formal verification is the process where we take a piece of software and try to see if it behaves according to some predefined set of rules. We call those security properties or rules, we call them specifications. And they're one of the two inputs along with the code that we want to check that we need to feed into the software that executes the formal verification. In this case, for example, the Sortora prover. And then after the prover gets those two inputs, it can give us 1 out of 3 possible outcomes. 1, a proof. That means that in all different cases, ways, behaviors, or states, the program behaves as intended. Another is that it doesn't always behave as intended, and then we get what we call a counterexample, which is often showing us something that is hard to find and very often a bug in our program, an unintended behavior. And also the tool can time out, and that in that case we don't know if the software is behaving well or not. Let's show that with a simple example of a Solidity pseudocode. This is a transfer function. We're transferring some amount of tokens from one address to the other. And an example of a specification that we can give to the software that does the formal verification is this invariant that says that the total supply of the token is equal to the sum of the balances of all addresses that hold that token, which makes sense. If we feed those two inputs to the prover, we will get a bug. We get a counterexample, a specific scenario where that invariant doesn't hold anymore. Here we can see that when we pass an amount of 18 from the address of Alice to the address of Alice, we get a violation. We see that Alice's balance grew by 18 tokens, which it shouldn't have. Now the invariant is broken, and that's why it's a bug. However, if we try and fix that Solidity code, let's say to this implementation, which doesn't contain bug, we'll actually get a proof. And what does that proof mean? It means that the sum of the balances of the token for all addresses before and after the transfer is equal. And then we can be sure that it's true no matter which addresses we chose and which amount we've chosen. And that's one of the key advantages of formal verification. It is exhaustiveness. We're not checking for a specific set of inputs, but instead we're covering the entire input space. That way we're able to find bugs that are often or sometimes missed by humans. Another big advantage is that whenever we get a violation, it's very easy to verify it. We get specific numbers, specific addresses, and we can see and run it ourselves and see if we get a violation or not, and try to track and see exactly where the problem lies. And also we can get a proof of correctness, which is something great that we can't really get through many other security methods for smart contracts. However, Those proofs are very hard to verify. Obviously, we cannot go ourselves through all the different inputs and see that it's true or not, else we would have done that instead of trying to prove it, right? And actually, sometimes our proofs don't actually mean what we think they do. Sometimes we're proving something completely different from what we've intended. And those proofs are bad because they can give us a false sense of security. And if we have a false sense of security, we might upload code prematurely that might contain bugs. Let's look deeper into those specifications I've been telling you about. This code that you see on the screen behind me is written in a specific language called the Sartora verification language, used for writing specifications, but the same principles hold no matter how you represent your property. The general anatomy is divided into 3 different parts. The first is the precondition, then we have an operation, and then we have a postcondition. And if we look at this specific example, here we check that the transfer function behaves as intended. The way that we do that is that at first, our precondition, we check the balance of Bob for a specific token. That's our precondition, and we keep that number. Then we do the operation. In this case, it's the transfer function. And after the operation, we check the postcondition. We check the balance of the tokens of Bob after the transfer and see if it is indeed equal to the balance Bob had before the transfer plus the amount of tokens we've transferred to Bob. Let's look at it more visually. When we define a property, we define a starting state by the different constraints that we give, and that's the circle. The arrow represents the operation. And then we want to land within one of the desired states, one of the states that satisfy or in which the assert expression that we had holds. Okay, so the desired behavior is that every state that is within the starting states, if we do the operation, if we draw the arrow, we end up within the green circle. And all of them live within the space of possibilities. When we get a violation, we get into a counterexample that means that we started from one of the starting states, we did an operation, we have an arrow, but that arrow doesn't land within the desired states. That's a counterexample, that's a violation, that's what might be a bug. And the interesting thing to note is that if the tool cannot find a counterexample for the specification or the property that we provided it, then it will output us a proof. And that is because in logic, we define a false statement as a statement to which we can give a counterexample. That part covered the first section of this lecture, what are the proofs and what is formal verification. And now we'll look at 2 different types of bad proofs. The first type is what we call a vacuous rule or vacuous proof. Vacuous is something empty or meaningless or insignificant. And this is better shown by a real-life example. I am 29 years old and I don't have any children yet. And I'm claiming the following statement. If I let my children drink Colombian coffee, they will sleep better at night. Is that statement true or false? So if we want to say that the statement is false, we need to provide a counterexample. So we need to start from one of the starting states, meaning you need to choose one of my children. Then you need to do the operation, meaning let them drink Colombian coffee, hopefully not too hot, not to injure them. And then you want to see that they actually do not fall asleep at night. Can you do that? You cannot do that since I don't have any children, and therefore there is no counterexample to that claim. If we don't have a counterexample to a claim, the claim is true. Here it's true vacuously. We don't have a starting state, so it's true. However, I can also say something that apparently seems completely contradictory. I can say that if I let my children drink Colombian coffee, they will not sleep at night. Sounds completely the opposite. Yet the same principles still hold. You still cannot provide a counterexample here. I still don't have a child. And therefore, that statement is also true. If we look at it visually, we just don't have any starting states, and we don't have any arrows, and therefore we cannot have a counterexample. Let's look at a code example. This balance of function belongs to a token of OpenZeppelin. And the interesting part about it is that we require that the address that we check the balance of cannot be address 0. One of Certora's employees was working on OpenZeppelin contract and was writing a rule, a property that he thought should hold on the tokens of OpenZeppelin. However, that rule, that specification, contained an error. You see, in the middle of the rule, we have this requirement that the balance of the address 0 for a given token must be 0. That can never happen because every call to the function balance off for the address 0 will revert. And if it reverts, in particular, it never returns back the value 0. Therefore, nothing can satisfy this requirement. If nothing can satisfy this requirement, we don't have any starting states. This is a vacuous rule. And therefore, it doesn't actually matter what appears later in the rule after that requirement. It will be true no matter what we do. And in fact, I could try and assert something completely ridiculous. I can assert that 0 is greater than 1. And that would still be true because you cannot still give me any counterexamples. And when a rule is vacuous, we can prove anything we want. Unfortunately, vacuous rules are not just an academic concern. Formal verification has been used a lot on hardware along the years, and studies have found that about 20% of specifications written on hardware on the first time are actually vacuous. And whenever they are vacuous, they hint at a real problem, either at the code that you're trying to verify or at your specification. So this is a pressing problem, but fortunately, we have some ways to try and catch them. And one of the ways that we use in Certora is doing what we call a reachability check. What we do is that we take the same specification as before, exactly as it is, and add something at the end. We add an assertion of false. Obviously, assertion of false is always false, so we expect the rule to fail. We expect to get a counterexample, right? Because nothing can satisfy false. However, if we do not get a counterexample, if the rule is proven, that means we didn't actually reach that last line of the specification. We didn't reach that last line of the specification because that requirement erased out all the possible starting states. It doesn't matter, we never reach that last line, and that's how we check that. We say something absurd at the end, and we see if we fail or not. If we don't fail, that's the problem. That's when we know that a rule is vacuous. For completeness, I will say that usually when we have vacuous rules, it's not due to one precondition, one requirement that is never satisfiable. It's usually due to a combination that their intersection is actually empty and not satisfiable, but each part by its own makes sense. For example, here, if we require that x is smaller than y, maybe we can prove the property. Let's say we add another requirement, y is smaller than z. Now we limit the starting states only to be the intersection. And if we add this third requirement that z is smaller than x, then we have no intersection anymore. Here by transitivity, we say that x is smaller than itself, and that's never true for any number. Therefore, we don't have any starting states, and this rule is vacuous. But note that some combination of those requirements could make for a sensible rule. Moving on to the next type of bad proofs. We're going to talk about tautologies. A tautology is something that is always true, and therefore is actually not telling us anything useful about the code that we're trying to prove things on. For example, let's look at this rule. And this rule tries to check, again, the integrity of the transfer function. We check that the balance of a recipient is 0, then we transfer some positive amounts of tokens to that recipient. Then we assert that the balance of tokens for that recipient actually grew. However, this rule on the screen is wrong because we didn't check the balance of the user before and after the transfer. We check that the balance of the user after the transfer is not smaller than itself. And this is something that's always true for any number. And that's a problem, because in this case, we didn't actually check what the transfer function is doing. We're checking something that is always true. The transfer function could burn all the tokens, could send all the tokens to me, or it could do something entirely different and not move any tokens around. We don't know. We didn't actually check that. If we look at it visually, a tautology, something is always true, so it encompasses the entire space of possibilities. So here, the arrow representing the operation lands somewhere within the space of possibilities, and therefore it's true. The problem is that we could have drawn any arrow, we could have done any operation, and it would still be true, so we didn't check anything specifically about our code at all. One of the ways that we find tautology in the insert aura is that we will remove all the preconditions and all the operations, just leave the assertion at the end, and see if it still passes or not. If it passes, it means that it does not depend on the requirements and the operation. It's something that is just always true, and therefore it's a tautology. So here in this example, we just remove all the lines but the last two, and in this case, this rule would pass, it would always be true, and that hints that it's a tautology. And now it's time to delve into the real-life example I've shown you briefly at the beginning of the lecture. Before that, I need to introduce you some new notion, a notion of an invariant. An invariant is something that is always true. In particular, it's something that is kept after doing some operations. In our case, it's calling functions of a smart contract. The way that we prove invariance is by induction. And you might be familiar with it from school. It's similar to proving by induction things about natural numbers. We have the base of the induction. We're trying to see if the condition is true right after calling the constructor. And then we're doing the step of the induction. That is, we assume that the invariant holds. We operate some function of the contract that must be public or external. And then we check that it's still true after. The same condition is true after. If we do that, we get that the invariant is true, the same way that induction proves that things are true. The interesting thing here is that we check for every possible function of the contract. And this example belongs to Notional, which is one of Satora's customers. And they were using our tool and writing a specification. And we'll go over it. It's a more complex example because it's a real-life example. What they tried to prove here is that an asset in their system, and their system allows lending and borrowing at fixed rates, by the way, an asset cannot be counted both as a bitmap asset and as an active asset. And here we see that they try to reach that conclusion at the end. The highlighted line at the end says that the same currency can't be both active and bitmap. The first line here is just a natural requirement on the index of the asset and is not very interesting. And the rest is where it starts to get a bit more complicated. Here we see we have one statement that says that the bitmap currency cannot be 0. And that will always have to be true. Then we have another statement that has an or sign. And if we look at the first part of it, we see that we require that the active unmasked currency is equal to 0. So if you look just at that part of the or statement, we see that the bitmap currency is not 0 and the active currency is 0. So 0 and non-zero are always different. So the conclusion is true, trivially true. What happens if you look at the other part of the OR statement? Here we require that the active mass currency is 0. In notional system, assets are represented using 14 bits plus 2 more bits for a mask. So the mask encompasses all 16 bits, and the unmasked encompasses the lower 14. But if the mask currency is all zeros, it means that the unmasked currency must also all be zeros. Therefore, it follows that it is 0 itself, and we have actually reached the same statement as we've reached before. Meaning, if the bitmap currency is not 0 and the active currency is 0, then they must be different. And that's always true because 0 is always different than non-zero. And in total, we get that this entire statement, although complex, is just a tautology. Hard to see, and you can understand why the person that wrote it could make that mistake. It's not apparent, but this is indeed a tautology. And unfortunately, the code was deployed thinking that it cannot contain that bug. And unfortunately, it did. The bug lied in this specific function, enable bitmap currency. And it's a bit hard to see the bug itself, so I'm just going to show you the exploit scenario. The exploit scenario goes like this. We enable the bitmap currency for an account, let's say ETH. We deposit a second currency for that account, let's say DAI. And then we try to enable DAI now as the bitmap currency. Due to the bug, now DAI will be counted both as an active asset and as a bitmap asset. That means it will be counted twice. It means that the user collateral will be larger than it truly is, and therefore we could borrow more money than we should, and therefore we can drain funds from the system. Fortunately, this bug was found by a white hat, so no real damage was done. Notional had to pay the maximal bounty amount of 1 million USD, but no real damage was done. The interesting thing is that this invariant I've shown before is pretty close to the correct one. The correct one, the fixed invariant, will look something like this. Actually looks simpler in this case. And the interesting thing to see is that if we run this invariant on the buggy version of the code, we get the exact same counterexample, where you set one token as a bitmap currency, deposit another token, then move the bitmap currency to be the other active currency. We get this exact counterexample. Notional used some of the top auditors in the field and formal verification and missed it. However, it's interesting to see that if they use formal verification correctly, they could have caught this critical bug. So not only can we catch the bug with the fixed rule version, we can also verify the fix, right? Because the specification doesn't change when the code changes, so we can run it again. And more importantly, this incident was a catalyst for Satora to invest in ways to catch bad proofs and ensure quality of specifications automatically. And today, you could have caught that the buggy invariant was a tautology using the method that I've shown you before, meaning that we just take it and require this condition without having the precondition, without having any operation. We would have seen that this would hold because it's a tautology, and therefore this mistake would not be possible with our tool today. And we're still working on more ways to ensuring qualities of good specification and catching more possible bugs and bad types of proofs. To sum it up, specifications are written by humans just like code is, and they're equally or even harder to write. This is something you have to keep in mind. You shouldn't expect your specifications to be perfect like you don't expect your code to be perfect. Therefore, you should always check your spec. It's good if another person reviews it, if an expert reviews it, and also even better to use some automatic checks like we in Satora provide you. You should always suspect what the tool gives you, like you would any other security tool. When you get a bug, it's always a good result because you can always check it and see if it's good or not. However, when you get a proof, you don't have a good way to verify it, and the best course of action is to be suspicious of it. Don't take it blindly and just upload your code. And obviously, we could have seen that writing the correct specifications, you can still find bugs that are worth millions or billions of dollars. Thank you. I would like to take some questions.
Thank you. So great presentation. So it seems from what you explained that when you have a bad proof that is vacuous, you can just detect it just with a coverage report, let's say, in which part of your specification was never reached. So it's like immediate. But when you have a tautology, it's more difficult because you will need to remove, let's say, preconditions. And removing preconditions, you can have like 10 preconditions, or you don't know which one, perhaps a combination of this. So what is your view on this? Is it correct that it's easier to detect vacuous than tautologies?
Okay, so one thing I want to emphasize, the checks that I've shown you don't catch all types of vacuities and not all types of tautologies, just catches only the simplest types, and I've chosen to present them to you because they're the easiest to explain in a 20-minute slot. There are actually more involved checks that try to cover more and more cases. We don't cover all of them currently. It's an ongoing effort in Certora or in formal verification at large. Maybe it was not clear, so I'm just going to say something simple. The removal of all the preconditioned operations is done automatically by Certora. It's an automatic check. So in that sense, it's not harder. So if I understand the question correctly, you say, how can I fix it? Which part of this statement causes it to be a tautology? And that is indeed sometimes more difficult, but it's something that you can do systematically. Say, your expression is an OR expression. You can check each part of the OR independently and see which branch of the OR is something that is always correct. If something is always correct, it means the entire statement is always correct. Therefore, this thing causes a vacuity. And this is actually a feature that's very close to production in Certora. Maybe I'm wrong, it's already in production. Maybe I'm not so keen on the details, but it's really close to production. So if you have an implication, same thing. You can see that maybe the premise, that's the part before the arrow that comes before the conclusion. If it's something that's always false, you will have a rule that's vacuous. So depending on the structure of your conditions, you can learn more intelligent things about them that can guide you. It's still not perfect, but this is something that we're actively working on. There's time for another. Thank you all.
Good? All right. Hello, everybody. So my name is Jonathan Alexander. I am CTO at OpenZeppelin. I'm the co-founder of Thorda. And in this talk, I'll be covering research and development on decentralized threat detection bots. There are a number of contributors to this presentation whose work I'll be citing here. A lot of the information and research has been conducted by these individuals. It includes Christian Seifert, who is researcher in residence at Forda, Mariko Wakabashi, who is lead machine learning engineer at OpenZeppelin, Dario Lobulio, who is security researcher at OpenZeppelin. We have a number of independent researchers, and we also have teams at Nethermind and LimeChain who have contributed to some of the techniques that we'll be discussing here. And so I'm going to start with a little bit of background. We are starting to see increasing acceptance in the space that security needs to be end-to-end, and that part of end-to-end security includes runtime monitoring and threat detection. We have multiple leading security audit firms, OpenZeppelin, Chain Security, Halborn, Mixbytes, who are beginning to make recommendations along with their audits for smart contract monitoring that can be done post-deployment. The recommendations include covering protocol assumptions and invariants, critical protocol variables, known protocol risks that have been considered acceptable, the use of privileged functions and the transfer of privileges, on-chain and cross-chain synchronization and oracles, and keeping track of the state of data that's meant to be kept in sync across these different environments, and also external contracts and protocols that your protocol may rely on, as well as identified attacks that may follow certain patterns that are already known. And this monitoring is meant to cover the knowns, the things like specific attack patterns that we might see. So that's one thing we want to monitor. The known unknowns, which would be places in the protocol where you know you're not sure what might happen, and you might want to monitor that. And then, very importantly, the unknown unknowns. So we might have things in our protocols that we think are invariant and will not change, and yet if something could happen that was unexpected, we would certainly want to know about that. So the challenge, though, with runtime monitoring is if you take that whole list, it's very difficult to implement the full set of monitoring that you might want, especially when you get into some of these areas that are not the responsibility of the protocol team themselves, such as other protocol implementations and their risks and updates to those, as well as things like the different attack patterns that have been seen in the ecosystem, but also maybe new and emerging, and we see new attack patterns emerging all the time. So we, at OpenZeppelin, we started working on post-deployment tools and specifically monitoring a few years ago, and this led us to the realization of the challenges here, and we decided to build, and along with a number of partners now, have launched a decentralized network for runtime threat detection. It's called Forda. I'm going to be citing some of it in this presentation, and a lot of the research that's here has been done by people working in and around Forda. Forda, you can go check it out. It's a decentralized network of scan nodes. There's thousands of scan nodes running now across number of mainnets, and the way it works is that you build bots, threat detection bots. They are deployed as containers onto the network. They're run on multiple scan nodes, and it is those results then that are brought together to detect threats. So, and the idea here is that for protocol teams, we, and sorry, am I like literally standing right in front of the slides? For protocol teams, back to the prior slide, the challenge of trying to do sufficient and real end-to-end monitoring and threat detection now is not just the team doesn't just have to do it themselves. They can take advantage of a community of threat detection. We can work together to have a real complete solution. So first of all, I'd like to share with you some observations from research that's been done on threat detection that hopefully you'll find a little bit interesting. The first thing is that as we look at the history of attacks, we begin to see a very common pattern of a set of stages that an attacker goes through. And this starts with funding, obtaining funds that will be used to carry out the attack. It moves to preparation, and there's a number of steps that are common in different kinds of attacks. It may involve deploying a smart contract, which is going to be used to carry out the attack. It may involve token impersonation. It may involve the transfer of privileges or making use of privileged functions. And then there are different kinds of fraud techniques that we see being carried out to prepare for stealing funds, and we'll get into some of that a little bit later. The next stage is exploitation. That's where the actual attack occurs. In this stage, we may see flash loans, we may see private transactions, we may see reentrancy, minting, anomalous transfers, anomalous functions, large balance changes, things like that. And finally, we have the phase of laundering, which is where the attacker takes the funds that they've obtained and they move them to try to hide the trail and exit with funds. One of the other interesting things in the research is that looking at quite a large number, over 180 attacks over the last 3 years, specifically in DeFi, we see that over half of the attacks are have been non-atomic. And what that means is that in the exploitation phase, it is more than one transaction, and typically many transactions that's used to carry out the completion of the attack. And why that's important is it means there is a time frame over which the exploit occurs, and therefore early detection could be useful to taking action and possibly mitigating the full effect of the exploit. So that's another interesting fact. Another observation is that attackers often use more than one account. This may be obvious, but as researchers have looked at this, and you may have seen this in some other presentations, we can use heuristics to associate attacker accounts and then by associating attacker accounts into clusters, we are able to track an attack through those stages I just talked about, even if many accounts are being used as part of that. We have examples of using heuristic-based approaches, such as a connected component graph algorithm, which would allow us to kind of graph together these connected accounts and then track them as a cluster. Another observation, in over 40% of the attacks, the attacker deploys a smart contract to execute the exploit. These attack contracts differ from benign contracts in very clear ways. And here, on this slide, I'm citing some research conducted where over 10,000 smart contracts were sourced from Luabase. 155 external accounts were identified as tagged as having an exploit in Etherscan, and then those accounts were associated to a set of smart contracts that those accounts deployed. So we had a set of benign contracts, and we had a set of malicious contracts using a classification of the top 100 opcodes in each of those smart contracts. We see incredible success in being able to identify contracts that are benign. So in this case, of the benign contracts with 98% accuracy, the classification algorithm is able to say that is not a malicious contract. And in the case of the set of malicious contracts, in this case 21 malicious contracts, the classification algorithm was able to identify 17 of those as suspicious or likely malicious. So this shows promise in the ability to just identify among a smart contract if it falls into the category of potentially malicious. Taking that a step further, we also see that when we get into the details, not just kind of like which opcodes are used, but we look at the patterns of the opcodes in use in these smart contracts that are used for attacks, we see that they follow very similar patterns. And so if we look deeper into the patterns, in this case, taking an even more advanced kind of approach to classification, where using techniques from natural language processing, grouping together opcodes into groups, collections in order, and then analyzing the use of those different groups, again with classification. In this case, the researchers looked at over 12,000 benign contracts, over 100 malicious contracts, and then using the TF-IDF NLP technique of grouping, feeding it into the classification. Now we get even a higher level of precision, in this case 88% precision, where the technique and the classification would predict that a contract was malicious. When it predicted that, it had a fairly small rate of error, so 88% accuracy. And also, in this case, the researchers went back to a number of known attacks that have been historically analyzed and carried out via smart contracts, and some of them are cited here: the Wintermute, Audius, inverse finance exploits. And in that case, this technique was able to predict in almost 60% of the cases that the attacking contract was malicious. So again, promising areas of research that we can identify malicious contracts. The last observation I want to share with you relates to fraud. Fraud is an attack that is usually carried out with social engineering or some kind of Web 2 attack, where in the case of, as the examples given here, ice phishing, an attacker will trick users into signing approval transactions that give the attacker control over their tokens. These also produce detectable on-chain patterns. And so in this case, we can use heuristic-based approaches just to look for these patterns of, accumulation or repeated kind of actions that might be carried out by a single account, or again, a cluster of connected accounts that are carrying out some kind of fraud attack on a lot of users, and then going to steal those users' tokens. They might do it. We've seen this happen in certain cases. We've seen attackers who do all the preparation up front and then they carry out the attack all at once. We've seen some cases where the attack just continues over time. But in this case, using a heuristic-based technique and then using public data about ice phishing attacks that occurred over a 1-week period in the month of September, this technique was able to, with 95% precision, predict that an ice phishing attack was underway. So in this case, it made 12 predictions that there was an ice phishing attack, I probably have the data wrong. It's probably like 13. But it was 95% accurate, so very low number of false positives. And of the 21 ice phishing attacks that were known publicly to have that we could see historically had occurred that week, it actually predicted 12 of those. So again, these are promising this is kind of the research that's going on and some of the things we're seeing. So now what I'd like to do is share with you some threat detection bot techniques that can be used to detect some of the various kinds of threats that we're seeing. There actually will be a workshop tomorrow on FortiBot development if you're interested. I think it's tomorrow afternoon. I don't have the exact details, but it'll be useful for you to know just up front that, because I'm going to reference it in a couple of cases, that FortiBots, you implement handlers, you can implement in JavaScript or Python. One of the things you can do is initialize. You have your own environment, it's a Docker container, and then you kind of subscribe to either handle transaction or handle block, and you can pretty much do whatever you want. You can also look up other alerts that have been emitted by other bots. And ultimately, what a bot does is if it has a finding, if it finds some kind of threat or something it wants alerts on, it shares that, which then gets published, and again, other bots can take advantage of that, or users can take advantage. The first technique that I want to discuss, and I have 3 techniques I'm going to talk about, and in each of these I'm providing some examples of bots. These examples, if you go to the documentation on Forta, you'll be able to find references, or if you go to the Forta Explorer, you can also look up bots by name, and most of them are open source and you can link. There are templates that mostly are what I'm covering here that have been provided by either the Forta network or Nethermind or LimeChain. So the first technique I want to talk about is multiple bots working together in a group to track attack stages, and then with increasing confidence as an attack goes through stages, be able to express that there is potentially attack underway, going all the way to complete confidence that an attack has occurred. This is done with having a set of bots that atomically detect some of those things that occur in funding, in preparation, in exploit, in laundering. You can have individual bots looking for individual things like suspicious contract creation, contract spoofing, ice fishing, large transfers, money laundering. You can also have bots that identify clusters of accounts, and there are example bots now available where you can see the source and how to do that. And finally, once you have these bots who are each kind of making an individual discovery, then you put that together with pattern matching on the various alerts, and being able to then declare with some level of confidence, this is what's going on, this is the possible attacker, and eventually this is the party or parties under attack. And so there's some bots that you would be able to find. The technique in the Forta community has been referred to as a combiner bot. The second technique that I want to discuss is simulation. In this case, you can have a bot that literally, while it's executing, forks mainnet with Ganache, with something else. You can fork mainnet and then run simulations to detect issues. There's kind of 2 techniques that have been used here. One is, if you have a known protocol and you know that if certain things happen on the protocol, then you would know that there must be something wrong, perhaps an attack underway. You could execute those in simulation after every single block that's been mined, and alert if the transactions failed. An example here is a liquidity tester. This is a bot that's been written to take a DeFi system, identify the top 10 current liquidity holders, and simply execute their ability to exit their position after each block. And in the case if any of them were not able to exit their position, it would alert. The other technique here is to test contracts, and we have a couple of bot examples, one that uses fuzzing, one that doesn't. But in this case, the simulation is to take a deployed contract, fork the network, and then basically try to execute every single method, knowing nothing about the contract itself, just detecting it through code and trying to execute it and looking to see if any execution results in, let's say, a large funds transfer or some other kind of unusually anomalous occurrence that would say there is something, this this contract is trying to do something, or it seems to result in a big transfer of funds, and therefore is suspicious. The final technique I want to talk about is the use of machine learning in bots. In this case, you can take a machine learning model, you can serialize it to a file. In the case of Forta, you can deploy models with the bot, and you can use the initialize function to load a model, and then in your bot, you can execute the model. This has been used successfully already in a number of bots that do anomaly detection and also malicious contract detection. So in this case, for example, there is a smart change detector bot that I've referred to here, and a time series analyzer that they use machine learning algorithms. I know one of them is a library that actually the Meta team developed that is very good at detecting outliers and deviation with a limited amount of false positives. So it's pretty good at saying, you know, this is a real outlier, and this is, there's a price change that occurs here if we're looking at on-chain prices, or there's, if you're looking at, let's say, the balances or certain values in your smart contract variables, it can detect over a period of time an outlier that is perhaps meaningful and something you should look at. And then in the case of the machine learning for smart contracts, there's a bot called the contract destructor, and some other bots that do similar things where they literally take a deployed smart contract address and they decompile it to get the opcodes for the smart contract, and then they use these machine learning models, kind of that I referred to before, to analyze and classify that smart contract and therefore predict whether the smart contract is malicious or benign. So these are all techniques that are already now in use, and further research is underway on how to improve these kinds of bots. So I want to wrap up just with a couple of challenges, and you might have been thinking about some of these as I've been speaking. There are challenges here that we're all dealing with. Atomic attacks are obviously a challenge. So I said that, well, we have history to tell us that more than half the attacks are non-atomic, but of course that means that 40 to 45% of the attacks are atomic. Also, private transactions can be used, and so this is a challenge for threat detection and monitoring. Another challenge is that there are teams who want to monitor in secret that would prefer not to monitor in public, and they may have good reason for that. For example, if there is a known vulnerability and you're in process of trying to deal with a known vulnerability, you may want to do that privately and not on a public system. And then finally, we have the challenge of response latency, which goes to how quickly can we alert, but also can we respond, and is there even anything we're able to do once we've detected? These are things that Forta's working on. There are already some things available for private, but these are also areas for future research. Latency, by the way, on the Forta network is about 40 seconds from mind block to alert. But things that are being looked at are possibility of trusted private scan pools for people who want to monitor in secret, pre-submission or mempool transaction scanning, on-chain alerts, which would provide a possibility for on-chain reaction, and other systems that can be used for automated action and follow-up. OpenZeppelin's working on these things. Forta community and many of the contributors I mentioned are starting to work on these things. And to wrap up, I would say, if you are interested, bot developers, security researchers, data scientists, please go to forda.org and you can learn more and find ways to get involved. And there's various grants and incentives available for people to get involved. And with that, I'm done. And if there's time, I'll take questions.
Thank you for the Thank you for the talk today. I find the bots incredibly useful for teams, but what I'm curious about is what happens once the bot alerts a team. What does the team have to do to then make a fast impact, right?
Yeah, well, I mean, in this presentation, I wasn't so much getting into that, but that's obviously a big topic of conversation for everybody. I think we are starting to see, we have seen many attacks in the wild where teams have paused their smart contracts, and we even saw a chain pause the whole chain. We are seeing more discussion about that because I think we're definitely headed down the road where emergency response capabilities may be an acceptable thing to have on your protocol, but it needs to be contained. It needs to be limited. We need to kind of have some level of delegation to a set of responders so that they can maybe do fast response, but with limited control, right? So we're starting to see protocols implement this and teams talk about it publicly. I think you may have heard some of the leading DeFi protocols are starting to discuss this. So pausing and then having some capability to deal with the attack is kind of a base point, but there's a lot to get into there because even pausing, depending on the nature of the attack, may not solve the problem, right? And I think the important thing here is that we all have to start thinking about this, because if you go back to the unknown unknowns, it's just impossible that we're going to catch everything up front. And so, yeah, but it's not solved. That's the true answer, yeah.
Right. Thanks for your talk, Jonathan. Speaking of things that you do after the attack, what is OpenSibling doing today with that information? How does OpenSibling harness that information to transform that into knowledge? That is the first question. And the second question, is there anything to do beside a smart contract audit in terms of things that you can do before the attack happens, like scanning the mempool or having some heuristic in there?
Well, two parts to your question. The first one is that OpenZeppelin is, in our audit practice, we are now, when we do an audit, we typically also make recommendations about what should be monitored, because the auditors have good insight into, we're training our auditors more and more in how monitoring can help. So then the auditors also understand the protocol, and they can say to a team, these are things you should think about monitoring in production, because if our audit didn't catch anything, or these may be just live risks you're going to be exposed to. OpenZeppelin is also working on tooling to automate the creation of monitoring. And we have, if you've seen our contracts wizard, we're going to be starting to build in things that if you use OpenZeppelin contracts, will auto-generate monitoring templates for you. And then we have a product platform called Defender, where we're working on how to automate those responses that we were talking about, like how you could at least get to where you could pause as quickly as possible, as an example. So we're doing all those things, and we're collaborating. I know Forda has multiple, I mentioned Chain Security and Halborn and Mixbytes are all doing some similar things, I think, yeah. We're good? Thank you.
Oh, sweet. Can I start? Awesome. You might want to turn down the volume slightly because I'm quite loud. Is it good? Yeah, this is a lot better. I'm not going to blow your ears out. Sorry, guys. My name's Heidi. I'm a part of the special investigations team at Coinbase, and I am super excited and also very honored to be able to present to you guys at DevCon Rug Life using blockchain analytics not only to detect illicit activity, but also to track stolen funds and hopefully stay safe. And I really liked the previous presentation actually right before mine because it was all about sort of detection, right? But this is about once your funds kind of get stolen, what do you actually do? So, quick TLDR. I know we all don't have time to be sitting around a panel all day. So if you've got places to go, TLDR is be paranoid. Be paranoid. That is literally the end of this presentation. The rest of this presentation is going to be full-on paranoia mode. You're going to want to lock down everything, throw out your computer, and just give up on things. But if you want to stick around for the rest of it, let's go for it. So first and foremost, we need to find what illicit actually is, right? There are a lot of people who say, oh, scammers are illicit, dark markets are bad, thefts are also bad. Shrewd traders, who do market manipulations, they're also bad. OFAC entities, more recently, also bad. Like, we've got a whole swath of different terrible bad actors out there. But today, we're only going to be concentrating on one, which is thefts. I personally believe that thefts are the worst thing that can happen with this ecosystem, right? First and foremost, you see millions and millions of dollars. Like just last night, we saw $100 million being drained out of Mango Finance, right? That's horrible for the entire ecosystem. Doesn't matter what chain it happened on, right? Not only that, but it also drives more regulator scrutiny. Do we really necessarily want that? We want to be able to develop, right? We want to be able to build without having to even consider things like that. So this is why we need to start thinking about things like, how do we prevent this kind of stuff? Now, I don't want to spend that long on this, but I think we need to talk about different theft typologies out there. Now, I largely bucket into 3 different sort of categories. First and foremost, you have the dev/team initiated thefts, right? AKA, we all know these, rugs, right? What does a rug actually look like? First and foremost, you've got some token dumping, you've got unlimiting or even limiting usually of functions, as well as cashing out of any and all proceeds possible. Now, sometimes with rugs, what will also happen is websites will 404 and obviously social media accounts will go totally dark. Now, the biggest bucket, though, are third-party thefts, right? And those I actually put into 2 different categories. First and foremost, you've got hacks, right? Third parties hack into places all the time, right? For example, let's think of the different sexes that have been hacked in the past couple of months, right? And also, you've got another thing called market manipulation, as we all know, like with what happened with Mango last night. Now, what exactly do we define as a hack? Well, a hack is very similar, actually, to a rug, right? The only difference, I would say, in this very generalized sort of rule of thumb, is that with a hack, you usually don't have the website of the team, the social, I don't know, I think it's not working, this media of the team also going down. So you don't have that actually happen with a hack. Now, but what you do see is obviously the cashing out of proceeds extremely, extremely rapidly, and obviously the dumping of funds. Now, in terms of market manipulation, what usually happens there is usually a flash loan will be taken out 9 times out of 10, and what will happen is a certain pool is manipulated, right? Where one token's price is arbitrarily pushed up, for example, what happened last night with Mango, right? Price automatically gets pushed up, then suddenly a dumping of that Mango, right? And then in exchange for tokens that, actually have value. And finally, there's another bucket of thefts, right? And I'm not going to go too much into these, but these are sort of more third-party service attacks. So think of, for example, when you're in a Discord, right? You're managing a Discord. You probably have a whole bunch of different Discord bots out there, right? They're doing a whole bunch of different things. But sometimes those Discord bots get exploited, meaning that, people who are investing in your project sometimes fall for those exploits, and then unfortunately you get their funds siphoned off of them, and then they blame you, which isn't really fair, but it definitely happens. Now, I actually want to go into detection methods. Like, how do we actually detect this kind of stuff? How do we find this stuff, right? And so there are a lot of ways to do detection. Forda just did an amazing presentation on how they go about doing detection. But as a protocol, what you want to do is you want to actually just set up alerting for large flows of funds. That's actually something that Forda does. Another thing you can do as well is use various different platforms that I have listed on here to actually start, alerting you for when any sort of strange activity happens. Finally, another thing you might consider doing is following a whole bunch of auditors online, because chances are on Twitter, the auditors will alert you probably before even your most avid Twitter followers alert you of something strange happening. Now, unfortunately, this is all fine and great, but once a transaction is broadcast to the blockchain, you're screwed, right? You're done for. So this is great. We can detect this all day, every day, but we need to actually prevent this stuff, right? And so what we need to actually do is we need to start detecting this sort of weird kind of activity before any money starts to move, right? And so if you're a dev, there are a couple things you can do. First off, you want to constantly audit, right, your debits and credits. And I know this sounds super effing. Oh, I just went out again. I know it sounds super boring, but for example, Nomad, they would have been able to detect some strange stuff happening going all the way back to July. And they could have probably prevented what then ended up happening at the beginning of August. Now, another thing you might want to do too is monitor who's transacting with your contract. What are they actually doing with their funds, right? And finally, another thing too is you want to be monitoring your site's back end, but also your site's front end. For example, Seller Bridge. That's actually how they were exploited more recently, right? Is their front end was attacked. Now, this is all great, but if you're an investor, right, this means nothing to you. Like, you're not going to be debiting and crediting a particular, like, protocols, smart contracts. That's not your job, right? So what should you be doing? Well, one thing you can do is make sure you know what contracts you're actually interacting with, right? So when you're on MetaMask and you are trying to do a transaction, before you click that button, make sure that the contract is indeed the contract you want to be transacting with. Finally, or next rather, revoke cache. So for example, when you interact with a contract, right, before you interact with that thing to send your tokens anywhere, you have to allow those tokens to be moved, right? Now, when you allow those tokens to be moved with that contract, you're granting that contract license to move them. You want to revoke those every once in a while, because chances are those contracts you interacted with back in 2021 or even 2020, they might not even exist anymore, right? You don't want to have anything to do with them, right? So revoke those. I would say just clean them out probably every once a month or so, probably. And last but certainly not least is you want to monitor the social medias of your projects, right? And as well as all of the wallets that you hold. I know this is exhausting and annoying, but it's also one way to also stay a little bit more safe. Now, I want to get to the most fun part of this presentation, which is actually tracking the funds. So let's say your project is wrecked, right? Like suddenly all the funds have been siphoned off, or let's say you're an investor and you invest actually in a project and, oh damn, their money's all gone. What happens? Like, can I even do anything, right? So I'm not going to be boring you guys with many more bullet points on slides. Don't worry, this is the last one. But first and foremost, you want to learn how to read Etherscan, right? There's no point in like pretending to track funds if you can't read Etherscan, right? And I know Etherscan is painful to read as Arbiscan is, as Snowtrace, and all the other ones are, but it's super, super, super important to learn how to read a block explorer. Another thing too is once you learn how to read a block explorer, you're going to be much more savvy with blockchain analytics tools like Dune and Blocksy and whatnot, and they're going to be able to help you track on those funds further. Now, there are a whole bunch of other tools out there that I haven't listed on this slide, but yeah, these at least, at the very least, are free and open source. Now, another thing you can also do as well is leverage Twitter investigators, but I say that with a massive caveat. So there are a lot of really amazing Twitter investigators out there, right? And I think we probably all know their names, right? But there are also some overzealous researchers as well. And I saw this, in fact, actually last night with a Mango exploit. There were several people who called out several different addresses that were indeed not related to the Mango finance exploit. So yeah, it's kind of frustrating at times for people like me when I'm going through this and I get pings from all sorts of people about things. So yeah, leverage them, but do it cautiously. The biggest point on here, though, that I want to make is if you do have a project that gets hacked, right, or if you're a part of a project that gets hacked, what you want to do is immediately reach out to law enforcement. So IC3 is with the FBI, and you can file a complaint with them, and they're quite good at tracking down funds. This is regardless of whether or not you're US-based, because chances are you probably have an investor somewhere in there in your project who might be US-based. So I would go ahead and file it with them, as well as obviously whoever your local law enforcement is. Now, the next biggest point on here is if you are a dev and your guys' project gets hacked, you want to communicate, communicate, communicate. Because the worst thing is you're silent, right? And then all of your investors are sitting there like, what the hell is going on? Oh my God, oh my God, oh my God. And then immediately the FUD starts. And immediately people are like, oh my God, the project got rugged. And then all the rumor mill begins, right? So you want to communicate as much as possible, as much as you possibly can. And I know you're going to probably hire lawyers and whatnot, but try to communicate as best you possibly can. Now, I want to get you guys prepared for my favorite thing, which is story time, because I want to actually give you guys a good case study. And unfortunately, this is not going to be a nice story time. This is going to be a nightmare story time. We're going to be talking about the Ronin theft that happened earlier this year. I'm sure we all know about it, but about $600 million was stolen from the Ronin Bridge. And what effectively happened was these guys stole all this ETH and as well as USDC from the Ronin Bridge. I think it was like 173,000. And they had all this ETH, right? What did they do with it? First and foremost, what they did with it is they started cashing it out at various different sexes. Now, this was also around the same day where the Ronin Bridge came out and they finally announced that they had been exploited. And what do you think the attackers did? They had to immediately stop because the sexes then caught on like, oh dear God, we're being used to cash out of these terrible proceeds. We got to stop this. And of course, the attackers then also paused too, right? And then 2 weeks later, they start mixing funds through Tornado Cash, right? And all of this ETH flows through Tornado Cash. Now, one thing I have to mention is this was a ton of ETH, right? I just mentioned it's 173,000 ETH. This is a ton of money. I had never seen this much money flow through Tornado Cash. So the sheer volume was already unprecedented. But the other thing that was also crazy too was these guys were rinsing and repeating the exact same methodology over and over and over again, right? So what they would do is they would mix money through Tornado Cash, and then they would then swap it using the same DEX over and over again to REN BTC, which is a Bitcoin proxy, right? And then after that, what they would do is they would burn that REN BTC in exchange for Bitcoin. And this happened time after time after time, day after day. And I mean, we're all human, right? These attackers are human, right? And so we like a good pattern. And it's one thing that you'll notice in this presentation is that patterns get repeated all the time. And that's the part of doing analytics and tracing funds, right? Is you start to notice these typologies over time. Now, what happened with this Bitcoin? This Bitcoin was then sent on to Chipmixer. And you guys might know Chipmixer. Chipmixer is a Bitcoin mixing service. Now, when I look at Chipmixer, I think to myself, oh my God, that's so 2019. No one uses Chipmixer anymore. Like, there are so many better services out there, right? And of course, again, why am I saying that's so 2019, right? Well, what I'm essentially saying by that is there's no liquidity in there, right? You want a deep liquidity pool when you actually care about privacy, right? Because you don't want to be found out. You don't want people like me to go looking for you, right? And of course, these guys had a ton of money that was flowing through Chipmixer, right? So what effectively happened is unfortunately we could trace through it. And a lot of it went to an APAC-based SEX, but not all of it. So not all of the funds actually were mixed this way. This was only their pattern in May. And by the way, we're going to skip all of the patterns that happened in June and July, and we're going to go straight to the pattern that started in late August and is continuing to today. So some of that Bitcoin that they had, what they started actually doing, and this is late August, beginning of September, they started splitting it out into these weird increments of rounded 5, 6, 7, and 8 BTC, right? They split out all these funds. What do they do with it? Send directly to REN, mint some REN BTC, great, right? This is a very, very, very easy pattern to detect on chain, right? And from there, what they did was they used a DEX, they swapped it into USDT, and then they got a little confused midway. They wanted some ETH, go back into USDT, and they ended up cashing it out at OTCs and a bunch of sexes. And they continued doing this pattern, right, through September. It was it was very, very obvious, right? Even if you were to just look at REN BTC-based mints, you'd be able to find this stuff. What they also did is they got lazy in between and just cashed out directly from Tether. Now, one thing that you'll notice is that I have USDT and ETH written on here, right? And for those of you that are savvy, you're like, hey, wait a second, Heidi, what about gas fees? Did you get anything out of gas fees? Yes, the gas fees actually originated from those sexes right here, right? So it's a very roundabout pattern that we end up seeing. So what also ended up happening as well is they had this large sum of Bitcoin and they got super, super lazy and they started just cashing it out directly to sexes. And then they decided to get unlazy because unfortunately some people found them. And they decided to go back to the REN BTC route and then do the same thing over and over again, right? Now, what am I trying to take away with this case study? That was a lot, right? This was overwhelming. Now, what I'm trying to tell you with this is Blockchain analytics ain't easy, it's quite complicated, and trying to recoup stolen funds is no joke, right? It's not only extremely costly, it's very, very, very time consuming, right? I've been tracking these guys literally, or yeah, March, right? And not only that, but the amount of funds that, the whole like crypto community has been able to recoup has been so limited, right? So you don't want this to happen. Now, luckily, we do have the transparency of the blockchain right now, which allows us, obviously, to trace funds, right? The fact that it's permanent, it's immutable, right? And it's fully transparent, it's awesome, right? But it doesn't change the fact that tracing this money is a lot more work down the line than actually trying to prevent the bad activity. Now, let's go into actually what we can do about this, right? I hope I scared you guys enough. Now we've got the crazy slide that I actually want to take a pause on, and I want you guys to actually take a picture of, because I'm not going to be talking about it, because I want us to actually talk through case study examples. So on this slide, we've got lots of different recommendations in terms of general stuff, blockchain stuff, social media, email stuff, and doing your basic due diligence, i.e. DYOR. Cool. We all got our photos? Awesome. Okay, worst case, I can share the slides with you after the fact. Now, I want to share a couple examples with you guys, and I want to share an example of being impulsive and not checking the contracts that you're interacting with before you interact with them. Now, back in April, Bored Ape Yacht Club's Instagram was hacked. I'm sure you guys remember this, right? Their Instagram was hacked. Suddenly, there was like this announcement of like, oh, we're giving away this land. All you have to do is, if you hold an ape, is mint this land token. And of course, people fell for this, right? They didn't actually look at the contract that they were interacting with. And what happened? Well, sure enough, you can imagine what happened. All of their most prized NFTs were ripped from them, right? And one thing that was very noticeable when looking at this initial contract is that there was this set approval for all function that kept on being called by these addresses that had been phished over and over and over again rapidly. And when you see this on chain, run from that contract, right? Because what that effectively, that contract's being run by some sort of phishing person who's doing phishing. Now, these NFTs were immediately sold for ETH on a whole bunch of different marketplaces, right? And then after that, the ETH was cashed out at a bunch of sexes immediately, right? Really good. Then also, it was sent to the Ukrainian Armed Forces. That's interesting. Maybe that tells us about where the threat actor might be. We'll see in just a second. And then we also see that they're sending money to a carding shop. So they're clearly buying fake IDs, right? Probably using those fake IDs to sign up for those sexes. Interesting, right? Now, remember how I talked about those gas fees? Those are something you want to look at when you're initially interacting with a contract, right? So you can see, where do they initially get their funds from? And if you take a look at that ETH, right, that paid those, topped up that address to initially get those gas fees, you'll actually find that that address indeed also did a whole bunch of different phishing and made a ton of money, right? Great. What else can we find out about this address? One thing that I found that was really interesting with this particular address, it also cashed out a whole bunch of sexes as well, was that it also sent money to this very interesting social NFT marketing page, right? So essentially what you could do is you could pay this money to market your NFT project on various different social media websites. Interesting. I don't think that's Ukrainian right there, right? And my perspective actually is these guys probably actually just donated to the Ukrainian armed forces in order to probably throw people like me off of their tracks, right? And so this is one very, very easy way to do it, because as we all know, that address for the Ukrainian armed forces is tagged on Etherscan, right? So it's very, very obvious. So this is an example of being impulsive, and this is what you don't want to do. So take those 2 minutes, literally 2 minutes, right? And look at that address before you interact with it, right? Look at what those other addresses that are sending funds are actually doing, right? Are they actually getting something for it? Are they actually minting any land? Or are they getting nothing out of it, right? Now, I also want to talk about an example of social engineering. This has nothing to do with blockchain analytics yet, but it will, right? So here's a great example from Polyplay, and they were amazingly transparent about their exploit that happened last year. This is actually from one of their tweets. As you can see here, the Binance team reached out to Polyplay in order to pretty much list their token, right? And as you can see, looks pretty, legit in terms of a, LinkedIn page. He's got like 400 some odd followers. This seems like a pretty legit email or whatever it is. But there are a couple funky things with it, right? First off, they're saying, hey, please donate to the Binance Charity Foundation. That's a little weird, right? And they're asking donation in Bitcoin too. I don't know, that's a little sus, right? So it's one thing that you want to kind of look at, right? When you're looking at people who reach out to you, is verify indeed their identities, right? For example, if you look up Teddy Lin right now on LinkedIn, I'm sure this isn't the only Teddy Lin at Binance you're going to find, right? And so it's one thing that you're going to want to do. You're going to want to verify with these teams before you start interacting with them, right? Because the worst thing is you get down the line, they send you over documents to agree to, you download that document, and that document includes a whole bunch of malicious code, and your whole project gets screwed over. Right? And what's interesting about this particular social engineering incident is that Polyplay ended up getting hacked, right? Because of all of this. And what happened? Well, if you looked on chain, you'll actually find that the Polyplay hack is related to the BZX hack that happened back in November, and also linked to the MGNR.io hack as well. And if you look hacks up, what you'll end up finding is all of them fell for very similar social engineering tactics. So this is a common one used by many nation states, actually, one in particular, and you guys can guess who that might be. Now, one thing we talked about before is what's the difference between a hack and a rug, right? But I actually want to talk about what is the difference between an actual dev team cash out and a rug. Because a lot of times, dev teams need to cash out of their funds, right? They make money, they need to be able to move their money around and do things that maybe not isn't crypto. Right? How do they actually do that? And I want to give you guys an example of how a legit team looks like when they're cashing out versus an illegit team, because I think the comparison is quite stark. So in this example, what we have here is we have 10KTF, which is a very large NFT project. They get proceeds, right, from their NFT sales. And you can see that on chain. And all of those are then sent to the 10KTF deployer address. That deployer address then sends on to their Gnosis multisig. Fine, that seems fair, right? Another thing that we also see, too, is Renga deployer. They also send funds onto their Gnosis multisig. So if you weren't following projects, which I wasn't, I had no idea these projects were intertwined, actually, until I was looking at their Gnosis multisig and actually found, oh, wow, they're clearly a part of the same ecosystem, right? And if you take a look at their Gnosis multisig, and by the way, this is a great practice, right? You want to see a project using a multisig and keeping their funds locked up there. They sometimes will actually cash out directly to FTX, right? But they do this over time. Right? Their website is still active. Their social media is still active. These guys are still clearly involved with the community, right? So nothing weird is going on here. This is the kind of activity you want to be seeing when you're analyzing on-chain, seeing where devs are cashing out at. Now, what do you not want to see? This is exactly what you don't want to see. So I'm sure you guys heard about the Squid Game rug pull last year, but essentially the Squid Game token launched right on the BSC network, and what effectively happened was you couldn't trade this Squid token. So you could only trade it, you could only buy it with BNB because it was on PancakeSwap, but you couldn't sell it. So effectively what happened was the price was driven up to like $2,500, right? And suddenly one day the website 404s, all social medias are deleted, right? And suddenly then the Squid token is swapped for BNB and fully dumped, right? Suddenly the Squid token now is valueless. Now, one thing the devs did right here, though, is they decided to unlimit that contract so that suddenly you could actually sell your Squid. But of course it was worthless, so who cared at that point in time, right? And so anyways, you had this BNB. Right? These guys then decided to rapidly send that BNB through Tornado, right? And again, this was a very high volume going through Tornado at that point in time, so it was kind of traceable. Now, there's one thing to note about privacy protocols. Privacy protocols are incredibly important. I'm not trying to be a proponent here in this presentation to say, oh, we can demix everything, or whatever. But what I am trying to say about privacy protocols are that unfortunately, illicit actors, while they do use them, it is quite easily traceable to see where they're moving funds to, because usually they move a ton of money at once. And why do they do that? Because they're paranoid. They don't trust anyone with that money but themselves. So the sooner they can get that money out, the better. Right? Privacy protocols are incredibly important, and I think we're going to still continue seeing them in the space. In fact, I've been super excited to see all the ZK Stark discussion here, right? But effectively, all these funds then went through Tornado Cash, and again, these guys rinsed and repeated the exact same transaction patterns, because once they got that BNB out, what they immediately did, and this is all in one single transaction every single time, was they would swap that BNB for DAI, right? And this is still on BSC, and they would bridge that DAI through any swap. swap then into ETH-based DAI or on other stablecoins, right? And this was a very, very, very particular pattern. So it was super, super obvious. Now, once they had this DAI in this ETH-based DAI, what they end up doing with it? Well, this ETH-based DAI, they ended up swapping for ETH, and then they sent it through Tornado one more time on Ethereum, right? And they could not be more paranoid, right? But of course, they're moving this money through super, super fast. Again, super obvious. Now, one thing I've noticed actually about these attackers more recently is, and especially in the Squid Game situation, right? As you guys remember, this particular rug was super, super known, right? This was all over mainstream media, right? So this guy was super hyper paranoid, right? So what he decided was, oh shit, I'm just gonna sit on this money for a while. But he just didn't want to sit on that ETH. No, 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 no. He wanted to earn some yield. So he decided to swap that money into USDT and lend it to the USDT ETH pool. And then he also lent it out to Compound. And from there, he sat pretty for a while and then slowly started cashing out to 2 different APAC-based sexes, right? And this is actually a pattern of activity that I've continued seeing quite often, unfortunately. Now, it's unfortunate but also fortunate, right? Because once they're sitting in these pools, we can still see that. That's the beauty of the blockchain, right? And so because of that is once they exit out, right? It's kind of great because we can also potentially recoup all the interest that they've earned. So it's one thing to also think about. Now, I want to leave you guys with a couple predictions because I only have a couple minutes left. And by the way, I wrote this slide deck a week ago. This was before the BNB bridge attack. This was also before Mango Finance. But unfortunately, this is now reality. We see hacks and scams continue, even in the bear market, right? DeFi protocols, particularly those with high TVL, right, will continue to be perceived, unfortunately, as honeypots, right? And threat actors, as I was talking about before, they're mainly going to continue sitting on funds, right? That's actually what we're seeing with the BNB bridge attacker right now. He's just sitting on the funds. We see that actually with quite a few different attackers at the moment, right? And to possibly earn yield, right? For example, if you take a look at Mango Finance guy, what do you think he's investing in right now? I'm not going to say. You guys look it up. Anyways, some quick predictions, right? First and foremost, be paranoid, right? Hopefully this has been a lesson in paranoia here. And you want to protect yourself before something happens, right? You don't want stuff to be broadcast to the chain, right? That is the ultimate thing that you do not want to have happen, because once it's broadcast to chain, it's done, right? Money is gone, right? And of course, you want to do your own research. That should be obvious, right? Do not rely on other randos to do research for you and just believe them because they're anons on Twitter that what they're saying is correct. You want to verify. And last but certainly not least, definitely learn how to read a block explorer. Block explorers are extremely powerful, and all of this research I actually mostly did using Dune Analytics and just Etherscan, as well as BSC Scan and a couple others. And don't forget to set up monitoring. And that's all. Thanks, guys.
Hello, can you guys hear me? Perfect. Okay. All right. So I'll be talking today about time lock recovery factors. It's going to be kind of interactive. We'll do some thought experiments, and we're going to start with like a toy problem and then a toy solution. And let's see whether we get something that works. So what are we really talking about? What are we trying to solve, right? The main problem we're trying to solve is that C phrases are bad, right? And C phrases contribute to loss, theft, and even terrorism. And C phrases are like a very long password, right? They're easy to use, easy to lose, sorry, easy to compromise. And basically, when you write it down, it's like, writing a post-it note. That's you, basically, when you write down a C phrase. And what we should really be using is multi-factor authentication, right? MPC or multi-sig. And why we should use it is the outcome of decades of evolution in user authentication, right? Since 1986, people have been trying to push multi-factor authentication, and it works. It provides better security, prevents phishing attacks, and is relatively easy to set up. So hopefully you also use this after this talk. And let's just talk a bit about MPC and multi-sigs. So most of you guys are probably familiar with multi-sigs and maybe a bit about MPC. And both of them have very similar properties, right? They're both better than seed phrase. They are more hack resistant. You have to compromise multiple factors before you lose your account. There's better redundancy. So if you lose one factor, you're still okay. And there's also the possibility of additional checks, right? Like daily spending limits, for example. But there are some differences. So MPC is off-chain, multi-sig usually on-chain as a smart contract. So multi-sig can support much more complex access structures. Think like organizations, right? Thousands of people trying to vote for something. Whereas MPC usually costs less to deploy and operate because it's off-chain, so there's no gas. Multi-sig also have trustless access to on-chain state. For example, pricing from DEXs as well as like limits based on block time. Whereas MPC is cross-chain. But actually, you can use both, right? One is probably more useful in like a large setup, and one's probably more useful for personal setup. So MPC is probably more useful for personal setup. So I'll talk a bit, very briefly about MPC, because we need to understand this before we talk about even multi-sigs and how to use recovery factors. So first, we need to understand how to share a secret key, right? Imagine you drew a line, and the y-intercept represents your private key, right? Now you draw 3 points on the line, and then you erase the line, right? And with 1 point, if you only have one of the points, you can't redraw the line, right? It's not possible. Any number of lines could pass through it. But with 2, you can redraw the line and recover your key. This is basically Shard secret sharing, which splits a private key into multiple shares. And by tying each share to some user factor, we can get multi-factor authentication on private keys. And where does MPC come in? MPC does all of this, except there is no line drawing. And basically, it avoids a single point of failure. Because when you're generating a key, if your device is compromised at a point in time, the key could be stolen. Whereas MPC just does that in a distributed way. For today, we'll just limit the scope to personal key management. But of course, you can use MPC for other things as well, managing it in like an organization if you wanted. So the crux of the problem, and what my talk is mainly about, is there's this binary dilemma, right, between non-custodiality and custodiality. What do I mean, right? We say a key is non-custodial if a user has full control of the majority of the shares. So let's say you had 3 shares, right, and you require 2 of them to reconstruct a key. As long as 2 of them are fully owned by the user, it's considered non-custodial, since the user can easily move his key as well as use it, but no other person can control the key. Whereas a key is custodial if third parties, which we call custodians, right, have control over a majority of the shares. And it's pretty obvious that the above are exclusive properties, right? You can't have like 2 majorities. So either get non-custodiality or you get full custodiality. And there's some special cases, like if the user owns a share and the party owns another share, but let's not think about that for now. But realistically, wouldn't it be nice if we had something better? Ideally, right, what I really want is that my private key should be non-custodial all the time. Until I've accidentally lost all my factors or, touch wood, I die, then it somehow, transitions to become custodial, right? So that at least my crypto assets can be retrieved. Sounds impossible, right? Okay, let's try and solve the impossible. Time-locked secret shares. So firstly, before we get into that, right, what is a time lock? It's basically something that takes a long time to decrypt. There are multiple variants, right? If you guys have been following the merge, they use verifiable delay functions and all that. But we are just going to use the most basic one, which is repeated squaring. And realistically, it really doesn't matter what you use. Just think it's locked for a long time. That's what matters, right? And you know what? Let's just do this, right? Let's just have an extra share, right? We have 3 just now. You require 2 to redraw the line. Let's just have 1 more, right? 1 more that's time locked. And let's say your house caught fire, you know, and you've lost both your laptop and your phone, so you lost 2 factors. They're now ash. But luckily, right, you've prepared ahead of time. You generated a 4th share that's time locked for like 1 month, and you put it somewhere other than your house, so it didn't catch on fire. You put it in public. And in a month's time, it unlocks, and with your other share, which is like an email share, you can get back your key. Perfect. Not really, that doesn't work. So let's see why, right? The problem is that now you're just 1 compromise factor away from losing a key. So let's say there's a patient attacker, right, adversary, just waiting, right? He just waits a month. Well, your time lock share will eventually unlock, right, after a month. And remember, it's in the public domain because it's not your house, so someone could get access to it. And then they just need to steal any one of the factors, right, to get a key. So basically, you've gone from 2FA to really 1FA. So that's no good. Solution 2, let's improve that, right? Let's do time lock shares with key refresh. So once again, new concept, right? What is key refresh? For those who don't know, basically, key refresh is a way to refresh the shares of a secret share, secret sharing, while keeping the private key the same. The private key here is this star, right? It's this star. So there's a private key the same. And the way we do it is kind of, you just draw another line that goes through the same point, the same y-intercept, which is a key, and then you get rid of the old shares. Basically, all the shares are different, but your key is the same. And the point here is that as long as you don't lose 2 factors on the same line, right? You don't lose 2 factors before you did a key refresh, your key is safe, right? Because even if they compromise these factors, they can't redraw the line. It's not possible. And the 2 lines are completely unrelated. So that's what key refresh does. There are a lot of protocols that do that today. But please, don't do it like this. There's a lot of other stuff you can do. Please don't do it like in production. So now we have some idea of what key refresh does. What if we just key refresh before the time locks up? Right? So we do a key refresh whenever you use a wallet, maybe once a week. The time lock is like a month, right? So as long as you use it once a week, you're fine. So when you use it, you do a key refresh, you get rid of the shares. Even when the time lock share unlocks, right? The attacker can't get anything, even if he steals another factor, right? Because he can't get back the line. So he can't get back the same line. So it seems like a safe, right? And this seems to work, right? The setup seems to have a lot of properties that we want. During normal operation, attacker can solve the time lock, but I cannot use the other shares since key refresh has occurred. It's on a different line. There's an interesting property here. So if you guys have been following time lock research and like verifiable delay encryption, you'll know that there are some research being done. There's some research being done on homomorphic time lock puzzles and all that because it makes it cheaper. But in our case, actually, it's good that it's expensive. It's a feature. We want it to be expensive because we don't want attackers to be getting through the time lock easily, or even be able to do it parallelly. And in the case when you lose your key, you won't mind doing the work. So it doesn't matter. The expense is not that big of a deal. So during normal operation, you're fine. But if you have catastrophic loss, right, you lose all your user factors, you, I don't know, somehow lose all your user factors, then if the time lock share is reviewed and share refresh won't happen, right, because you didn't have your shares, so you can't share refresh, then you can use the custodial share with the email share and the time lock share to reconstruct the key. So it's kind of like a dead man switch of a smart contract wallet, except it's done in MPC. So we created a non-custodial setup that degrades into a custodial setup on loss. So that's it. Thank you. No, I'm kidding. This is for hosts. There's no way that's going to work, right? So firstly, what happens if a phone share is stolen? Then the time lock share unlocks. Let's consider that, right? So your phone share is there. It's been stolen, right? Someone just stole your phone. Well, what are you going to do? Well, you're going to key refresh, right? That's the only thing you have protecting your shares. You're going to key refresh. You bought a new phone, so you have a new share on that phone. Perfect. But the attacker and the hacker and thief who stole your phone is not going to actually delete the share. He's just going to hold on to it. And when a month passes and the time lock expires, he's going to be able to steal your key. Key gone. Terrible. Okay, maybe what we can do is stop making more shares, right? The reason why this person was able to get our key was because he had more cryptographic material. So what we're going to do is, instead of having more shares, the time lock share itself is just going to be my phone share, right? So this person stole my phone, and then he gets the time lock share, which is also my phone share, so he doesn't really get anything new, so I'm safe. Not really. If you stole your laptop, right, and the time lock share unlocks, you run into the same problem. So it looks like we're in a dilemma here, right? What really can we do? A new solution, right? Let's split the device share in two, a time lock share, and then a custodial subshare, right? So how does that look like? How does that look like? So what we're going to do is we have this initial setup, right? 2 out of 3 factors. You have an email login, a phone, and a laptop share, so they're actually stored based on these factors. And what we're going to do is split the phone factor into 2 subshares. We're just split it into 2. And one will be time locked, and the other will be encrypted in your email, right? So this way, let's say if someone steals any of the factors and they get a time lock share, they still have to compromise another factor, which is your email, right? So key recovery still works. If you lose everything, you still have, let's say you lose both your phone and your laptop, it caught fire in the house, right? You still have this time lock share and the email share, which you can use to reconstruct your phone share, and you already have email share, so you can redraw the line, right? So you're still safe from catastrophic loss, but adversary can't actually get your key unless he also compromises another factor. So you still get the 2FA properties, perfect. But there's also another problem. The email provider might not delete shares during key refresh. Let's see why that's a problem. What happens if, let's say, the email provider doesn't delete shares, right? So let's go back to the scenario, right? You do key refresh, right? And the email provider, instead of doing key refresh properly, and during key refresh, you're supposed to discard the old shares, he doesn't. He just keeps the email share. After all, why not? Why shouldn't he keep it? Well, after a month passes, right? So let's go back a bit. After a month passes, right? This is going to unlock, right? The time lock share is going to unlock. And he's going to be able to reconstruct the phone share on the previous secret sharing polynomial and reconstruct your key. So even though you refresh your shares, this is still a problem. As long as the custodian doesn't delete the share, right? You still have this problem where when the time lock expires, the custodian can get your key. Solution, right? Custodian's bad. No custodial factors. Let's just get rid of all the custodians and third parties. There's a problem there, though. We're trying to solve for the disaster case when you lose all of your user-owned factors. Do you really want all your factors to be lost? Because if they're all user-owned and something happens to you such that all your factors go away, there's going to be no way to recover a key. And this problem is really less of a problem than a statement. It's not possible to get recovery from catastrophic loss without third parties having at least threshold -1 shares. Let's see why, right? Fundamentally, if custodians only control, let's say, threshold -2, which is less than threshold -1, with a time lock share that unlocks after 1 month, they will only have threshold -1, right? So threshold -2 plus 1. So they only have threshold -1 shares, which is not sufficient. It's not going to meet the threshold. So because it doesn't meet the threshold, you need some other factor. You need some user-owned factor, and that's impossible in this scenario, since we're assuming that the users lost all their shares, so they can't access anything. So we haven't really solved the non-deletion problem. Remember, this solution of removing custodians was to get rid of the non-deletion problem, but it's a non-solution. So we haven't really solved the non-deletion problem, right? We still need third parties to hold threshold -1 of the shares, but we can't guarantee deletion. So in 1 month, the custodian might be malicious and they'll steal the key. We have a final solution for now. 1 out of n deletion. So there are many forms of trust, right? And the best kind of trust is like trustless, right? 0 of n. But there are also other trust vectors like u of n and 1 of n, and maybe it's like half, majority of n. And one way to do that is maybe there's a way to make it such that we can delete the factor if at least one of n of the parties follow the rules. So what we could do is, right, we could have the custodial subshare be further split across 100 independent custodians, like guardians, and trust that one of them will delete it during the refresh. As long as they do, the key material is gone. This isn't ideal, right? 1 out of n is not as good as 0 out of n, trustless, but it's close enough. And the set gets bigger, 1 out of 1,000, is actually pretty close to trustless. And also, doing n out of n secret sharing is very fast, so it's quite practical. So this is what a setup looks like, right? We have the 2 out of 3 setting. We split it into 2. One is time locked, like you saw earlier. And then this one is split in amongst a bunch of guardians, right? However many you want. And during normal operation, right, if you do key refresh, and at least one of these guardians deletes the share, you're not going to have enough pieces to reconstruct the phone share. So it's good enough, so adversary can get it. And neither can the custodial provider. But during catastrophic loss, when all user factors are gone, so your phone factor and your laptop factor is gone, at least there's some way to recover it because your email factor is still there. The time lock factor will unlock, and the guardians should, in this scenario, return the shares to you so you can reconstruct your key. There. A bit more complex, but much better than what we started with. So I have a demo, but it doesn't work very well on slow internet, so you guys can check it out on the slides below, or the link there. And if you don't like the solution, you can also just use a smart contract wallet or a date message. It's much simpler. Not everything needs MPC, really. So some open problems. The guardians can maybe grief you. So let's say a catastrophic loss, the guardians can just refuse to return the shares to you unless you pay them an exorbitant fee. There's also a problem of how should the guardians know when you've lost your key and return the shares to you. So these are some open problems we're exploring. So that's all. Thank you very much for coming to my talk. Hello? I think I'm a bit early, so does anyone have any questions? Yes, go ahead.
Hello. Oh, hi. So the time-locked piece is a bit of a magic box that just works. Are there any practical algorithms to run
so
this?
that gist that I need the. Oh, he's taking it away. But anyway, if you go check out slides online, there's a gist there. It's implemented in JavaScript, so you run it in Rust, it'll be even faster. But it's the most common and simple algorithm is a repeated squaring algorithm. So you can just look it up. It's quite popular and it works in this case. Yeah, it works for just this use case. You don't need anything very complex. Yeah. Sorry? Yes, it's ASIC resistant in the sense that it requires sequential steps. You can't parallelize it. So you could maybe build an ASIC for squaring, but it's not possible to parallelize the computation, so it's sequential. Yeah. Any other questions? Yes. Okay, so we're considering the scenario, the whole point of this setup, right, is complex, but the whole point of this is to protect against catastrophic loss, right? So during catastrophic loss, you're gonna have this issue where you've lost basically all your user-owned factors like phone and laptop. The email, we're just assuming it's custodial. There's always some way to subpoena the guy, There's always some way to get it. But what might happen, right, is the time lock share will unlock, but the guardians, knowing that you didn't refresh your shares, have now detected that you lost your factors. And now they're gonna grief you, right? They're gonna be like, if you don't pay me, half of what's owned by this account, I'm not gonna give you back the shares. And this is extra challenging here because you only need one guardian to grief since there is no redundancy here. Yeah, so there's one problem, there's an open problem to solve. Any other questions? Go ahead, yeah. Someone not deleting a share and someone keeping the share. The problem here is that the actors here are dynamic. They're not static. So I will delete my share if I'm pretty sure you refreshed, right? Then you're not going to, you haven't lost your account, so my share is actually worthless. But when I do detect, right, maybe you have no on-chain activity for like 3 weeks, right? A little suspicious, 3 weeks. Then I'm going to modify my behavior in accordance to that. So it's kind of hard to model it that way. I think a much more comprehensive way to think about a threat model is to think about the different types of attacks, because the number of ways you can attack is limited since there isn't much interaction between the parties. It's really just about factors. Yeah. Any other questions? All right. Thank you very much.